Welcome to the Data Science Full Course. Data science is one of the hottest skills in the job market today. And in this course, we are going to show you how to unlock its full potential. Imagine turning raw data into powerful insights that help businesses make smart decisions. That's what data science is all about. We will start by giving you a clear roadmap to becoming a data expert. You will dive into Python, the go-to language for data science, with a step-by-step guide through installation and the key basics. We will also introduce you to the large language models, a groundbreaking technology that changes the way data is used. Plus, we will walk you through common data science interview questions so you can confidently tackle real-world opportunities. Let's jump in and start your exciting journey into the world of data.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In our meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition, to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you.
Learning objectives. Welcome to Math Refresher, Probability and Statistics. In this lesson, we are going to explain the concepts of statistics and probability, describe conditional probability, define the chain rule of probability, discuss the measure of variance, identify the types of Gaussian distribution. Basic of statistics and probability. Probability and statistics. Data science relies heavily on estimates and predictions. A significant portion of data science is made up of evaluations and forecast. Statistical methods are used to make estimates for further analysis. Probability theory is helpful for making predictions. Statistical methods are highly dependent on probability theory, and all probability and statistics are dependent on data. Data is information acquired for reference or research via observations, facts, and measurements. Data is a set of facts structured in the form that computers can interpret, such as numbers, words, estimations, and views. Importance of data. Data aids in seeing more about the information by identifying possible connections between two features. Data assists in the detection of distortion by uncovering hidden patterns. Based on prior information patterns, data may be utilized to anticipate the future or predict the current state of affairs. Also, data aids in determining whether two pieces of information have any instance in common or not. Types of data. Data might be quantitative. That is data that can be measured or counted in numbers. Or it may be qualitative, which is data which is generally divided into groups or, in simpler words, which cannot be counted or measured in numbers. Let's consider an example. A customer information data of a bank may contain quantitative and qualitative data. Consider this snapshot where we have customer ID, surname, geography, gender, age, balance, has C or card, is active member. Amongst these variables, we can see surname is mostly qualitative as it cannot be counted and measured in numbers. Geography and gender are also qualitative as they cannot be counted in numbers and are mostly groups. Has C or card, that is, has credit card and is active member, although are containing numerical in form. But these are categorical. That means these have been divided into groups of 1 and 0 that represent yes and no as an answer. Hence, these two variables are also qualitative. Customer ID is again, although a numerical data. However, the significance or intuition behind customer ID is categorical. Hence, it may be kept in the qualitative data also. However, age and balance. These are numerical information which have been measured or counted, and numerical operations can be performed on them. Hence, these are under quantitative data categories. Introduction to descriptive statistics. Descriptive statistics. A descriptive measurement is summary measure that quantitatively portrays the most important features of a set of data, allowing for a better comprehension of the information. Data can be measured as different levels. The levels of measurement describe the nature of information stored in the data assigned to the variables. Qualitative data can be measured as nominal or ordinal. Quantitative data can be measured in terms of interval and ratio type. Nominal data. The data is categorized using names, labels, or qualities. For example, brand name, zip code, and gender. Ordinal data can be arranged in order or ranked and can be compared. Examples include grades, star reviews, position and race, and date. Interval data is the data that is ordered and has meaningful differences between the data points. Example, temperature in Celsius and year of birth. Ratio data is similar to the interval level with the added property of inherent zero. Mathematical calculations can be performed on both interval as well as ratio data. For example, height, age, and weight. Population versus sample. Before analyzing the data, it's important to figure out if it's from a population or a sample. Population is a collection of all available items as well as each unit in our study. Sample is a subset of the population that contains only a few units of the population. Population data is used for study when the data pool is very small and can give all the required information. Samples are collected randomly and represent the entire population in the best possible way. Measures of central tendency. The central tendency is a single value that aids in the description of the data by determining its center position. Measures of central tendency are sometimes known as summary statistics or measures of central location. The most popular measurements of central tendency are mean, median, and mode. The normal distribution is a bell-shaped, symmetrical distribution in which mean, median, and mode all are equal. The curve over here shows the bell-shaped curve or the normal distribution of variable x. The point over here that is x1 is the point which represents the mean, median, and mode of this distribution. Mean. Mean is calculated by dividing the sum of all data values by the total number of data values. It gets affected when there are unusual or extreme values. It is sensitive to the outliers. Mean can be calculated as summation over all the values of x in a collection divided by the size of the collection. For example, we have a collection where we have values as 7, 3, 4, 1, 6, and 7. We find out the sum of these values, which is 28, and there are a total of 6 values. So 28 divided by 6 gives us a mean value of 4.66. Median. It is the middle value in the set of the data that has been sorted in ascending order. It is a better alternative to mean, since it is less impacted by outliers and skewness. It is closer to the actual central value. Median is calculated differently for different sizes of data. Differentiated as if the total number of values is odd, or if the total number of values is even, if the size of the data is odd. For example, in this case, we have 5 elements. After sorting, whatever middle value we get. That means n plus 1 by 2th term in this case. 5 plus 1 divided by 2. That is the 3rd term, which is 4 is the median value. In case when the total number of values is even like here, there are 6 values. The average or the mean of the 2 central values is considered as the median. In this case, the median is the mean of 6 and 4, which is 5. Mode. Mode represents the most common value in the dataset. It is not at all affected by extreme observations. It is the best measure of central tendency for highly skewed or non-normal distribution. Mode for categorical data is determined by estimating the frequencies for each categories, and then the category with the highest frequency is considered to be mode. Like in this case, 7 has the highest frequency, hence 7 becomes the mode value. However, in case of continuous data or quantitative data, the calculation of mode is slightly different. The first step in calculation of mode is dividing the data into classes which are equal with, then getting the frequency of data points lying within that range of classes, and finally selecting the class with the highest frequency. Using the range of that class and the frequencies, we can get the final mode value. Using the formula L plus Fm minus F1 multiplied to H divided by Fm minus F1 plus Fm minus F2. Here L is the lower limit, or the lower observation of the mode class. H is the size of the mode class. Fm is the frequency of the mode class. F1 is the frequency of the class proceeding to mode. And F2 is the frequency of the class succeeding to mode. This gives us the final mode value. Mean versus expectation. Now let's talk about mean versus expectation. So in general, we use the expected value or expectation when we want to calculate the mean of a probability distribution that represents the average value we expect to occur before collecting any data. And mean, on the other hand, mean is basically used when we want to calculate the average value of a given sample. This represents the average value of raw data that we may have already collected. We can understand this by using a simple example. Now, to calculate the expected value of this probability distribution, we can use a specific formula from the previous discussion. This is going to be the expected value, where x is going to be the data value, and this px is the probability of value. For example, we could calculate the expected value for this probability distribution to be as shown. So here, it will be 1.45 goals. So this represents the expected number of goals that the team will score in any given game. And then if you talk about calculating mean, so we typically calculate the mean after we have actually collected raw data. For example, suppose we record the number of goals that a soccer team will score in 15 different games. Now to calculate the mean number of goals scored per game, we can use the following formula, where sum of x is basically the sum of all the goals divided by n and the number of records, or we can say the sample size. It is as shown on the screen. So this represents the mean number of goals scored per game by the team. Measures of asymmetry. The difference between the three distinct curves can be studied in this image. The central curve is the normal or no skewness curve. Here mean, median, and mode all lie on the same point. This normal curve is symmetrical about its mean, median, and mode. That means the left-hand side of the curve is a mirror image of the right-hand side of the curve. However, in case of negatively skewed data, the tail is elongated on the left-hand side, and the mean is smaller than the mode and the median values, or is on the left-hand side of the mode, hence indicating that the outliers are in the negative direction. On the other hand, in case of positively skewed, the data is concentrated on the left-hand side of the curve, while the tail is elongated or longer on the right-hand side of the curve. The mean is greater than the mode and median, or is on the right-hand side of the mode and median, indicating that the outliers are in the positive direction. Let's consider an example. The graph here shows the global income distribution for the year 2013, and a projection for 2035. If we see the global income distribution statistics for 2003, it is highly right-skewed. We can observe in the previous graph that in 2003, the mean of $3,451 was higher than the median of $1,090. The global income is definitely not evenly distributed. The majority of people make less than $2,000 each year, while only a small percentage of the population earns more than $14,000. Measures of variability. Measures of variability. Dispersion. The measure of central tendencies provide a single value that addresses the full worth. However, the central tendency cannot depict the viewpoint entirely. The metric of dispersion helps us focus on the inconsistency in the data spread. Measures of dispersion describe the spread of the data. The range, interquartile range, standard deviation, and variance are examples of dispersion measures. Range. The range of distribution is the difference between the largest and the smallest amount of data. The range, for example, does not include all of a series' positive aspects. It concentrates on the most shocking aspects and ignores that aren't considered critical. For example, for a set 13, 33, 45, 67, 70, the range is 57. That is, the maximum of this, which is 70 minus the minimum over here, which is 13. Variance. Variance is the average of all squared deviations. It is defined as the sum of squared distance between each point and the mean or the dispersion around the mean. The standard deviation is used as variance suffers from a unit difference. Variance can be computed as sigma square summation over x minus mu square divided by n, where mu is the mean of the data, x is the individual data point, and n is the size of the data. This representation is for a population data. For a sample data, variance can be computed as x minus x bar whole square summation over it divided by n minus 1. Here x bar is the mean of these sample data, and n is the sample size. The units of values and variance are not equal, so another variability measure is used. Standard deviation. Standard deviation is a statistical term used to measure the amount of variability or dispersion around a mean. The standard deviation is calculated as the square root of variance. It depicts the concentration of the data around the mean of the dataset. Standard deviation, as indicated previously, can be computed as square root of variance. For a population data, standard deviation sigma can be computed as square root of summation over xi minus mu whole square divided by n, where mu is the mean of the data, xi are the data points, and n is the size. Let's consider an example. Let's find out the mean, variance, and standard deviation for this data. The data values are 3, 5, 6, 9, and 10. To find out the mean, we first find the sum of all these data values. That is 33, and divide it by the count, which is 5. We get the mean of 6.6. To compute the variance, we start by computing the deviation. That is x minus the mean of x. Here 3 is one of the values of the data, and 6.6 is the mean. So 3 minus 6.6 square, and we do that to find out sum of all the deviations divided by the count, which is 5. We end up getting an overall variance of 6.64. Standard deviation, as we know, is measured at square root of variance. That is square root of 6.64, which amounts to 2.576. Measures of relationship. Measures of relationship. Covariance. Covariance is the measure of joint variability of two variables. It measures the direction of the relationship between the variables. It determines if one variable will cause the other to alter in the same way. Covariance between variable x and y can be computed as summation over the product of xi minus x bar and yi minus y bar the whole divided by n minus 1. Here x bar and y bar are the mean of x and y respectively. The value of covariance can range from minus infinity to a plus infinity. Correlation. Correlation is normalized covariance. It measures the strength of association between two variables. The most common measure for correlation is the Pearson correlation coefficient. Correlation between two variables, x and y, can be measured with respect to covariance as covariance between x and y divided by the standard deviation of x and standard deviation of y. The value of correlation ranges from a -1 to +1. Types of correlation. Correlation can be either a positive correlation, zero correlation, or a negative correlation. The first picture over here represents a perfect positive correlation, wherein a straight line with a positive slope is representing the relationship between the two variables. Zero correlation means that the line representing the relationship between the two variables is horizontal to the x-axis. Perfect negative correlation can be represented by a straight line with a negative slope. Correlation equals to 1 implies a positive relationship. That is when one variable increases, the other variable also increases. A correlation value of -1 implies a negative relationship. That is when one variable increases, the other decreases. The correlation coefficient of 0 shows that the variables are completely independent of each other. Let's consider an example. Here, we have two variables, height and weight. To compute the correlation between height and weight, we use the correlation formula as covariance of x and y divided by standard deviation of x and standard deviation of y. Here height is the x variable and weight is the y variable. First, to compute covariance, we compute the x minus x bar and y minus y bar values, and then the product of them. We then compute x minus x bar square and y minus y bar square values to compute the standard deviations of height and weight respectively. Correlation, as we know, has been defined as covariance of x and I and y divided by standard deviations of x and y. This can also be represented as summation over x minus x bar multiplied to y minus y bar divided by square root of summation over sum of squared deviations. That is x minus x bar square multiplied to square root of summation over y minus y bar whole square. That is sum of square deviations for y. Now, let's find out values to put into this formula. First, we find out the overall sum of height to get the mean of height, which is 5.14. Similarly, we get the sum of weight to get the mean of weight as 50. We now get the summation over x minus x bar multiplied to y minus y bar to get the numerator for the formula. Then we compute x minus x bar square summation and y minus y bar square. That is sum of squared deviation of x and y respectively. Now we put in the values in this final correlation formula to get a correlation value of 0.889. This indicates that height and weight have a positive relationship. it is evident that as height grows, weight also increases. In this module, we will be talking about expectation and variance. So the expected value, or we can say mean of a given variable, that we can denote by x is a discrete random variable where it is a weighted average of the possible values that x can take, and each value is going to be according to the probability of that specific event occurring. So usually the expected value of x is denoted by a simple formula where we can define the expectation based on the x parameter, which is going to be the sum of each possible outcome multiplied by the probability of the outcome occurring. So in more concrete terms, the expectation is what we would expect the outcome of an experiment to be on average. We can take an example for the coin. If a coin is being tossed 10 times, then one is most likely to get 5 heads and 5 tails. Same logic can be discussed if we talk about another example of rolling a die. So there are 6 possible outcomes when you roll a die. 1, 2, 3, 4, 5, 6. And each of these has a probability of 1 by 6 of occurring. So we can say that the expectation is going to be 1 multiplied by the probability of that happening, which is going to be 1 by 6, plus 2 by 6, plus 3 by 6, plus 4 by 6, plus 5 by 6, plus 6 by 6, and that is going to give us 3.5 as an output. The expected value is 3.5. So if you think about it, 3.5 is halfway between the possible values that I can take. And this is what we should have expected. Next, we talk about the concept of variance. So variance of a random variable allows us to know something about the spread of the possible values of the variable. So for a discrete random variable x, the variances of x is going to be denoted by using a simple formula that is going to be var x equals ex minus m, the whole square where m is basically the expected value of the expectation of x. So this is more like a standard deviation of x, which can also be represented by using this formula. So the variance does not behave in the same way as expectation when we multiply and add constants to random variables. So now there are 2 different types of variance that we can have a fair understanding on. First of all, we have low variance, and then we have high variance. So low variance simply means that there is a small variation in the production of the target function, with changes in the training data set, and at the same time, high variance, as we can see here. High variance shows a large variation in prediction of the target function, with changes in the training data set. So a model that shows high variance learns a lot and performs well with the training data set. And it does not generalize well with the unseen data set. And that's why, as a result, such a model gives good results with training data set, but shows high error rates on the test data set. And since the high variance a model learns too much from the data set, it leads to an overfitting of the model. So model with high variance will be having a couple of issues, like it may lead to overfitting, or it may also lead to increase in model complexities. Next, we have skewness. So skewness in simple terms is basically a measure of asymmetry of a distribution. So distribution is asymmetrical when its left and right sides are not the mirror images. Right now, this is a mirrored image, and a distribution can have right positive, or we can say negative, or it can have 0 skewness. So right skewed in this scenario is basically the distribution is longer on the right side of its peak. And a left skew distribution is going to be, we can say, where it is longer on the left side. So we can see we have this one as a part of right side. It is more elongated towards the right side, and this one is more elongated towards the left side. So we can think of skewness in terms of tails. A tail is long tampering and the end of a distribution. So it simply indicates that they are observations at one end of the distribution, but that they are relatively infrequent. So a right skew distribution has a long tail on the right side, as you can see here, so the number supports observed. Let's say we have a data on a per year basis. So again, we can have a more skewness towards the right side, where data is being dropping as we continue to increase the number of years. For example, we may have a high sales towards the beginning of year, suppose in 2022. But again, as we proceed to 2023, second half we are seeing the dip in performance. So that is rightly skewed. And same way, let's suppose if we started with the sales figure, it was really less in suppose 2002. But again, as we proceeded to 2023 now, our sales have been gradually increasing. So it's more like skew towards the left section as a part of negative skew. Next, we have kurtosis. So kurtosis is basically a measure of the tailedness of a distribution. So tailedness is how often the outliers occur, and acts as kurtosis is the tailedness of the distribution related to a normal distribution. So a distribution with medium kurtosis is called as mesokurtic. A distribution with low kurtosis like this one. This is called as the platykurtic, and then distribution with high kurtosis like this one. This is called as the leptokurtic. So tails here, they are tapering ends on either side of a distribution like this. So they represent the probability or the frequency of values that are extremely high or extremely low to the mean. In other words, tails here represents how often the outliers occur. So there are three types of kurtosis. We have platykurtic, which is negative, leptokurtic, which is a positive towards the upper end, and then we have mesokurtic, which is a normal distribution. So mesokurtic is the medium tail. So normal distributions, they have a kurtosis of 3. So any distribution with a kurtosis of a prox value of 3 is going to be mesokurtic, and kurtosis is described in terms of excess kurtosis, which is kurtosis minus 3. And since normal distribution, they have a kurtosis of 3-axis kurtosis, makes comparing a distribution kurtosis to a normal distribution even easier. Introduction to probability. Probability theory. Probability is a measure of the likelihood that an event will occur. Let's consider an example of coin toss, where the chances of getting heads on a coin are 1 by 2 or 50%. The probability of each given event is between 0 and 1, both inclusive. Sum of an event's cumulative probability cannot be greater than 1. Hence, the probability of an event X lies between 0 and 1. This means that the integral of probability of distribution over X equals to 1. Conditional probability. Conditional probability of any event A is defined as the probability of occurrence of A, given that event B has previously occurred. Condition probability of event A given B can be estimated as probability of A intersection B, that is, probability of both A and B happening together, divided by the probability of B. It is also written as that probability of A intersection B equals to probability of A given B multiplied to probability of B. Let's consider an example. In a coin, we are doing a 2-coin flip. Coin 1 gets heads, and tails in subsequent flips, while coin 2 gets tails, heads, and tails in the subsequent flips. Now the probability that coin 1 will get a head is 2 out of 4, while the probability that coin 2 will get heads is again 2 out of 4. The probability that both coin 1 and coin 2 will have a heads is just 1 out of the 4 flips. Hence, the probability that coin 1 will get heads given that coin 2 is already heads can be computed as probability of coin 1 edge intersection coin 2 edge. That is 1 by 4 divided by probability of coin 2 edge. That's a given that is 2 by 4, which is going to be 0.5 or 50% based. Bayes theorem. Bayes' theorem calculates the conditional probability of an event based on its prior probabilities. Basically, Bayes' theorem incorporates the prior probability distribution to predict the posterior probabilities. Bayes' theorem for conditional probability can be expressed as probability of A given B equals probability of B given A divided by probability of B multiplied to probability of A. Bayes' theorem allows updating the probability values by using new information or evidence. Here, probability of A is known as prior probability. That is the probability of event that before any new data is collected. Probability of A given B is known as the posterior probability. It is the revised probability of an event occurring after taking into consideration the new information. Probability of B given A is known as the likelihood, and probability of B is probability of observing an evidence. Bayes model. An example. Consider an example for calculating the likelihood of having diabetes based on frequency of fast food consumption. Here is the observed data. Let's say the fast food audience is 20%. Diabetes prevalence is 10%, and 5% is fast food and diabetes. The chances of diabetes given fast food, that is the conditional probability of D given B, can be calculated as probability of diabetes and fast food together divided by probability of fast food. That means 5% divided by 20%. That equals 25%. Define an analysis can state eating fast food increases the chance of having diabetes by 25%. The multiplication rule of probability. If events A and B are statistically independent and probability of A intersection B can be given as probability of A given B multiplied to probability of B. However, probability of A intersection B is also given as probability of A multiplied to probability of B. Here, probability of A given B equals to probability of A when we assume that probability of B is non-zero. Similarly, probability of B equals probability of B given A, assuming probability of A is non-zero. Chain rule of probability. Joint probability distributions over many random variables can be reduced into conditional distributions over a single variable. It can be expressed as probability of x1, x2, so on until xn equals probability of x1 intersection probability of xi, given probability of x1 till xi minus 1. For example, the joint probability of A, B, and C can be given as probability of A given B. C multiplied to probability of B given C multiplied to probability of C. Logistic sigmoid. The logistics function is a type of sigmoid function that aims to predict the class to which a particular sample belongs. Its outcome is discrete binary value, a probability between 0 and 1. The logistics sigmoid is a useful function that follows the yes curve. It saturates when the input is very large or very small. Logistics sigmoid is expressed as sigma of x equals 1 upon 1 plus e to the power minus x. The logistic sigmoid can be expressed as sigmoid function of x is given as 1 upon 1 plus e to the power minus x, where e is the Euler's number. Gaussian distribution. The Gaussian distribution is a type of distribution in which data tends to cluster around a central value with little or no bias to the left or right. It is often referred to as normal distribution. In absence of prior information, the normal distribution is frequently a fair assumption in machine learning. Equation. The formula for calculating Gaussian distribution is described as the normal distribution of x. That is the function of x given mean as mu and variance is sigma square can be calculated as 1 upon sigma square root of 2 pi e to the power minus half x minus mu divided by sigma whole square, where mu is the mean or peak value, which also is the expected value of x. Sigma is the standard deviation, sigma square is the variance. A standard normal distribution has a mean of 0 and a standard deviation of 1. Gaussian distribution can be univariate, which describes the distribution of a single variable x. It can also be multivariate, where it can just use to describe the distribution of several variables. It is represented in 3D of ND formats. Law of large numbers. Now let's talk about law of large numbers. The law of large numbers states that an observed sample average from a large sample will be close to the true population average, and that it will get closer in the larger sample. So the law of large number does not guarantee that a given sample, spatially a small sample, will reflect the true population characteristics, or that a sample does not reflect the true population will be balanced by a subsequent sample. This is for the law of large numbers to express the relationship between scale and growth rate. So there are multiple examples through which we can understand, and it is widely used in statistical analysis in working with the central limit theorem in terms of the business growth. So there are multiple real-time setup in which these are going to be used. So if you talk about tossing a coin, so tossing a coin in a number of times will give us two different type of outcomes. The result will spread evenly between head and tails, and the expected average value is going to be half. That means 50 times tails and 30 times heads. But again, if you toss a coin 1,000 times, then the result can be in different manners, because out of 1,000, let's say 850 times it has been head, and only 150 times it has been tails, and so on. So that's why the possibility of one event occurring is going to be changed in large sample sets as compared to a small sample sets, as in let's say 10 times. So the number of heads and tails unbalanced for lower number of trials, so we can see it is unbalanced. But again, as soon as we toss more number of coins, more leans towards the balance value, or we can see the observed averages. Next, we have p-value. So p-value is basically a number calculated from the statistical test that describes how likely we are to have found a particular set of observations if the null hypothesis were true. So p-values are used in hypothesis testing to help decide whether to reject the null hypothesis. And the smaller the p-value, the more likely we are to reject the null hypothesis. So we have a term called as null hypothesis. So all statistical tests, they have null hypothesis. So for most tests, the null hypothesis is that there is no relationship between our variables of n first, or that there is no difference among groups. For example, in a two-tail t-test, the non-hypothesis is that the difference between two groups is going to be 0. So p-value is going to tell us how likely it is that our data could have occurred under the null hypothesis. It is done by calculating the likelihood of a test statistic, which is the number calculated by a statistical test using our data. So p-value tell us how often we would expect to see a test statistic as extreme or more extreme than one calculated by a statistical test if the null hypothesis of the test was true. So there are multiple limitations as well. So first one is the results can be significant, but again, they may not be practical as we have compared. It can be based on multiple hypotheses for a game for the healthcare test. If the test is going to be positive or not, it may show even values of the effect of a variable, but not the magnitude in real life. What exactly is going to be the application of a drug test being failed in pharma company? Therefore, it is recommended to use confidence and levels in addition to the p-values to quantify, or we can say to give a solid figure to the reserve, which we are going to get. The p-values, they are interpreted as supporting, or we can say refuting, the alternative hypothesis. So p-value can only tell you whether or not the null hypothesis is supported. It cannot tell us whether our alternative hypothesis is true or why. So the risk of rejecting the null hypothesis is often higher than the p-value. So especially when we are looking at a single study or when using small sample sizes. So this is because the smaller frame of reference, the greater are the chance that as we stumble across a statistically significant pattern completely by accident. Key takeaways. Key takeaways. Probability and statistics structure the premise of the data. The data helps in anticipating the future or gauging in view of the past patterns of information. The central tendency is a single value that helps to describe the data by identifying these central positions. The mean, median, and mode are the measures of central tendencies. The distribution where the data tends to be around a central value with a lack of bias or minimal bias towards the left or right is called as Gaussian distribution.
Have you ever wondered how your favorite online store seems to know exactly what you are looking for? Every time you browse, add to cart, or wishlist an item, you are leaving clues about your style, favorite colors, brands, and even shopping times. Data scientists jump in, analyze these patterns, and create a super personalized shopping experience. Suddenly, the store is showing you just the right pieces at just the right time, almost like it's reading your mind. That's data science, turning your clicks into a shopping spree crafted just for you. Hello everyone, welcome back to Simplilearn's YouTube channel. If you're already a data science enthusiast or just got curious about this exciting field, you're in the right place. Today in this video, I am diving into 10 essential steps to help you become the next in-demand data scientist and land that dream job. No more waiting, let's dive right in and get you on the path to your future in data science. So let's see the 10 essential steps to become the next data scientist in demand. Step number 1 is programming languages. Starting with Python as a beginner is a great move because it's simple, versatile, and widely used in data science. Python's straightforward syntax makes it beginner-friendly, helping you grasp programming basics quickly and dive into data science libraries like Pandas, NumPy, and Matplotlib with ease. Adding R to your skill set is valuable because it excels at statistical analysis and data visualization, two essential parts of data science. You can be comfortable with Python and R within a month or two. So, moving on to the next step, that is version control system. Learning a version control system like Git is essential because it allows you to track, manage, and collaborate and code effectively. With Git, you can save different versions of your work, making it easy to backtrack if something goes wrong or to experiment without losing progress. This is especially useful when working with complex data science projects where you might try out different models of analysis techniques. 1 or 2 weeks of practice along with Python and R is good to get started. Now moving on to the third step, that is data structures and algorithms. Learning data structures and algorithms is crucial for becoming a data scientist because they provide the foundation for efficient data handling and problem solving. Data structures like arrays, stacks, queues, and trees help you store and organize data in ways that make it easier and faster to access, process, and analyze. Algorithms, on the other hand, give you strategies to perform tasks like searching, sorting, and optimizing data operations, which are essential for handling large data sets. While many candidates struggle with DAC, mastering it gives you an edge, helping you stand out in the interviews and shine as a skilled data scientist capable of tackling the toughest data problems. Spend about 2 months in this, you will get in the shape for sure. Now moving on to the step number 4, that is SQL. Learning SQL is essential for data scientists because it enables you to access, manage, and manipulate data directly within databases where most real-world data resides. With SQL, you can create new tables, alter existing ones, delete unnecessary records, and run queries to filter, sort, and aggregate data. These abilities allow you to retrieve, clean, and organize data effectively, core skills needed for any data science role. It's easy and you don't have to spend more than a month to have a deep understanding of it. Now, moving on to the fifth step, that is mathematics and statistics. Mathematics and statistics are essential for data science because they form the backbone of data analysis, model building, and interpretation. Topics like linear algebra, calculus, probability, and statistics gives data scientists the tools to understand data patterns, perform accurate analysis, and make data-driven decisions. Mastering these areas enables you to build robust models, validate results, and tackle complex problems confidently, making you a well-rounded and skilled data scientist. Make sure you spend 2 months to grasp these topics. Now moving on to the step number 6, that is data pre-processing and visualization. Learning data pre-processing and visualization is essential for a data scientist because these skills make you data accurate, insightful, and easy to understand. Python libraries like NumPy and Pandas are crucial for manipulating and creating data, enabling you to handle missing values, filter out noise, and prepare data for analysis. Once the data is ready, visualization lets you uncover patterns and communicate results effectively. Libraries like Matplotlib and Seaborn help create clear, impactful visuals, allowing you to interpret trends and convey insights in a way that's easily understood by others. Together with these tools, make data pre-processing and visualization fundamentals for effective data science. If you have a solid foundation on Python and mathematics, you will get a good understanding of data pre-processing and visualization in a month or two. Now moving on to the seventh step, that is machine learning fundamentals. Machine learning fundamentals involve understanding how algorithms enable computers to learn from data and make predictions on decisions without explicit programming. The two main categories are supervised learning and unsupervised learning. In supervised learning, models are trained on labeled data to make predictions, while in unsupervised learning, models find patterns in unlabeled data. Popular tools like TensorFlow, PyTorch help build and train complex models, especially for deep learning, while scikit-learn is essential used for simpler machine learning algorithms and data pre-processing. These tools make it easier to implement machine learning fundamentals effectively and build intelligent data-driven decisions. Dedicate about 3 months to understand the core of machine learning. Now coming to the next step, that is deep learning. Deep learning is a subset of machine learning that focuses on algorithms inspired by the structures of the human brain called neural networks. Deep learning uses neural networks with multiple layers, often dozens or hundreds, to learn complex patterns from large data sets. Specialized types like convolutional neural networks, that is CNNs, are great for image processing, while recurrent neural networks RNNs are used for sequence data like text or time series. Essential tools like TensorFlow, PyTorch make building, training, and deploying deep learning models more accessible, allowing you to create powerful AI solutions across various domains. I think it will take about 2 months to have a good hold on deep learning concepts and how to implement them. Now moving on to the ninth step, that is specializations. Once you have grasped the deep learning, it's like reaching a new level as a data scientist. Just as doctors specialize in areas in nephrology and cardiology, data scientists often choose to specialize in fields like natural language processing or computer vision. Natural language processing focuses on teaching machines to understand and generate human language, enabling applications like chatbots, sentiment analysis, and language translation. It's about making computers read, write, and even interpret human emotions through text or speech. Computer vision, on the other hand, is all about enabling machines to see and interpret images or videos. This field powers innovations like facial recognition, object detection, and autonomous driving. Now, you don't need to learn both. You can choose what interests you the most. Now, spend 1 to 2 months diving deep into one of these areas. Now moving on to the last but not the least step, that is big data. Big data refers to extremely large volumes of data generated rapidly from sources like social media and sensors. For data scientists, learning to handle big data is crucial, as it requires specialized tools like Hadoop and Spark to analyze and extract insights effectively. With companies relying on data-driven decisions, big data skills make you a highly in-demand professional in the field. Focus for about 2 months and you will be able to spot trends and patterns from datasets very easily. Once you are ready, it's time to build a killer resume packed with projects that showcase your new skills. Start applying to jobs on platforms like Naukri and Indeed and supercharge your LinkedIn. Connect with data scientists, see what skills they are mastering, and learn from their journeys as well. Keep sharpening your own skills, and when the time comes, you will be ready to crush those interviews and land your dream data scientist role in 2025.
Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. You can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage. as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used, no supervision, follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of a different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options. And we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching, and then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, and we're doing it in Python. So let's go ahead and go through not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row. Same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment, and suddenly a reward system like this is going to be just is going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing. You add weights to it, and so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward, because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess, I think was a big one, where they had the 2 players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where they get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state, this is class player, and when we say class player, we're not talking about a human player, we're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it. As you try different moves, it gets to the end, the first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important, this is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2, probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here. Let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, would have been easier. So the first move goes in here and it puts 2 in here. Then we have ourselves set up on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here, and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here, and feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go. And it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. You can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, And you can see right here, it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3x3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. You pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there. So what is Q-learning? Q-learning is reinforcement learning policy which will fill the next best action given a current state. It chooses this action at random and aims to maximize the reward. And so you can see here's our standard reinforcement learning graph. By now, if you're doing any reinforcement learning, you should be familiar with this, where you have your agent takes an action, the action affects the environment, and then the environment sends back the reward or the feedback, and the state, it's the new state the agent's in. Where is it at on the chessboard? Where is it at in the video game? If your robot's out there picking trash up off the side of the road, where is it at on the road? Consider an ad recommendation system. Usually when you look up a product online, you get ads which will suggest the same product over and over again. Using Q-learning, we can make an ad recommendation system which will suggest related products to our previous purchase. The reward will be if user clicks on the suggested product. And again, you can see you might have a lot of products on your web advertisement or your pages, but it's still not a float number. It's still a set number. And that's something to be aware of when you're using Q-learning. And you can see here that if you have 100 people clicking on ads and you click on one of the ads, it might go in there and say, okay, this person clicked on this ad. What is the best set of ads based on clicking on this ad or these two ads afterwards based on where they are browsing? So let's go ahead and take a look at some important terms when we talk about Q-learning. We have state. The state S represents the current position of an agent in an environment. The action A is the step taken by the agent when it is a particular state. Rewards. For every action, the agent will get a positive or negative reward. And again, when we talk about states, we're usually not, when you're using a Q table, you're not usually talking about float variables. You're talking about true, false. And we'll take a closer look at that in a second. And episodes, when an agent ends up in a terminating state and can't take a new action. This might be if you're playing a video game, your character stepped in and is now dead or whatever. Q values used to determine how good an action A taken at a particular state S is Q A of S. And temporal difference, a formula used to find the Q value by using the value of the current state and action and previous state and action. And there's Bellman's equation, which basically is the equation that kind of covers what we just looked at in all those different terms. The Bellman equation is used to determine the values of a particular state and deduce how good it is to be in take that state. The optimal state will give us the highest optimal value. Factor influencing Q values, the current state and action, that's your SA, so your current state and your action. Then you have your previous state and action, which is your S, I guess prime, I'm not sure how they reference that, S prime, A prime. So this is what happened before. Then you have a reward for action, so you have your R reward, and you have your maximum expected future reward. And you can see there's also a learning rate put in there and a discount rate. So when we're looking at these, just like any other model, we don't want to have an absolute final value on here. We don't want it to, if you do absolute values instead of taking smaller steps, you don't really have that approach to the solution. You just have a jump, and then pretty soon if you jump one solution out, that's what's going to be the new solution, whichever one jumps up really high first. Kind of ruining the whole idea of doing a random selection. I'll go into the random selection in just a second. Steps in Q learning. Step 1. Create an initial Q table with all values initialized to 0. Again, we're looking at 0, 1. So here's our action. We start, we're in idle, we took a wrong action, we took a correct action, and end. And then we have our actions, fetching, and running, in the dog example. And choose an action and perform it. Update values in the table. And of course, when we're choosing an action, we're going to kind of do something random and just randomly pick one. So you start out and you sit, and you have then depending on that action you took, you can now update the value for sitting after you start, from start to sitting. Get the value of the reward and calculate the value Q value using the Bellman equation. And so now we attach a reward to sitting. And when we attach all those rewards, we continue the same until the table is filled with or an episode ends. And I mentioned I was going to come back to the random side of this. And there's a few different formulas I use for the random setup to pick it. I usually let whatever Q model I'm using do their standard one, because someone's usually gone in and done the math for the optimal spread. But you can look at this. If I have running has a reward of 10, sitting has a reward of 7, fetching has a reward of 5, just kind of without doing like a means, using the bell curve for the means value, and like I said, there's some math you can put in there to pick so that you're more likely, so that running has even a higher chance. But even if you were just going to do an average on this, you could do an average, a random number, by adding them all together. So you get 10 plus 7 plus 5 is 22. You could do 0 to 22, or 0 to 21, but 1 to 22. 1 to 5 would be fetching, and so forth, the last 10. So you can just look at this as what percentage are you going to go for that particular option. And then that gets your random setup in there, and then as you slowly increment these up, you see that if you're idle, where's one? Here we go. Sitting at the end. If you're at the end of wherever you're at, sitting gets a reward of 1. Where's a good one on here? Oh, wrong action. Running for a wrong action gets almost no reward. So that becomes very, very less likely to happen, but it still might happen. It still might have a percentage of coming up. And that's where the random programming and Q-learning comes in. The below table gives us an idea of how many times an action has been taken and how positively correct action or negatively wrong action it is going to affect the next state. So let's go ahead and dive in and pull up a little piece of code and see what this looks like in Python. In this demo, we'll use Q-learning to find the shortest path between two given points.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
If you've seen my videos before, I like to do it in the Anaconda Jupyter Notebook setup, just because it's really easy to see and it's a nice demo. And so here's my Anaconda. This one I'm actually using Python 3.6 environment that I set up in here. And we'll go ahead and launch the Jupyter Notebook on this. And once we're in our Jupyter Notebook, which has the kernel loaded with Python 3, we'll go ahead and create a new Python 3 folder in here. And we'll call this Q Learning. And to start this demo, let's go ahead and import our NumPy array. We'll just run that so it's imported. And like a lot of these model programs, when you're building them, you spend a lot of time putting it all together, and then you end up with this really short answer at the end. And we'll take a look at that as we come into it. So we go ahead and start with our location to state. So we have L1, L2. These are our 9 locations, 1 to 9. And then, of course, the state is going to be 0, 1, 2, 3, 4. It's just a mapping of our location to an integer on there. And then we have our actions. Our actions are simply moving from one location to another. So I can go to location 0, I can go to location 1, 2, 3, 4, 5, 6, 7, 8. So these are my actions I can choose. These are the locations of our state. And if you remember earlier, I mentioned that the limitation is that you don't want to put in a continually growing table, because you can actually create a dynamic queue table where you continually add in new values as they arise. Because if you have float values, it just becomes infinite, and then your memory in your computer is gone, or it's not going to work. At the same time, you might think, well, that kind of really limits the Q learning setup. But there are ways to use it in conjunction with other systems. And so you might look at, well, I've been doing some work in stock. And one of the questions that comes out is to buy or sell the stock. And the state coming in might be, you might take it and create what we call buckets, where anything that you predict is going to return more than a certain amount of money. The error for that stock that you've had in the past, you put those in buckets, and suddenly as you start creating these buckets, you realize you do have a limited amount of information coming in. You no longer have a float number. You now have bucket 1, 2, 3, and 4, and then you can take those buckets, put them through a Q learning table and come up with the best action. Which stock should I buy? It's like gambling. Stock is pretty much gambling if you're doing day trading. You're not doing long-term investments. And so you can start looking at it like that. A lot of the current feeds say that the best algorithms used for day traders, where you're doing it on your own, is really to ask the question, do I want to trade the stock? Yes or no? And now you have it in a Q learning table, and now you can take it to that next level, and you can see where that can be a really powerful tool at the end of doing a basic linear regression model or something. What is the best investment? And you start getting the best reward on there. So if we're going to have rewards, these rewards we just create. It says if you're this should match our Q table, because it's going to be you have your state and you have your action across the top, if you remember from the dog. And so we have whatever state we're in going down, and then the next action and what the reward is for it. And of course, if you were actually doing something more connected, your reward would be based on the actual environment it's in. And then we want to go ahead and create a state to location so we can map the indexes. So just like we defined our rewards, we're going to go ahead and do state to location. And you can see here it's a dictionary setup for location state and location to state with items. And we also need to define what we want for learning rates. You remember we had our two different rates as far as like learning from the past and learning from the current. So we'll go ahead and set those to 0.75 and the alpha set to 0.9. And we'll see that when we do the formula. And of course, any of this code, send a note to our Simplilearn team. They'll get you a copy of this code on here. And let's go ahead and pull. There we go. Well, the next two sections. Since we're going to keep it short and sweet. Here we go. So let's go ahead and create our agent. So our agent is going to have our initialization where we send it all the information. We'll define our self gamma equals gamma. We could have just set the gamma rate down here instead of submitting it. It's kind of nice to keep them separate because you can play with these numbers. And our self alpha. Then we have our location state. We'll set that in here. We have our choice of actions. We're going to go ahead and just embed the rewards right into the agent. So obviously this would be coming from somewhere else instead of from self-generated. And then a self state to location equals our state to location dictionary. And we go ahead and create a Q learning table. And I went ahead and just set the Q learning table up to 0 to 0. What the setup is, location to state. How many of them are there? And this just creates an array of 0 to 0 setup on there. And then the big part is the training. We have our rewards new equals a copy of self.rewards. Ending state equals the self location state in location. So this is whatever we end up at. Rewards new equals ending state plus ending state equals 999. Just kind of goes to a dead end. And we start going through iterations. And we'll go ahead, let's do this. So this, we're going to come back and we're going to call it on here. Let me just erase that. Switch it to an arrow. There we go. So what we're doing is we're going to send in here to train it. We're going to say, hey, I want to iterate through this 1,000 times and see what happens. Now this part would actually be, instead of iterating, you might have your external environment and they're going back and forth and you iterate through outside of here. But just for ease of use, our agent's going to come in here and iterate through this. Sometimes I'll put this iteration in here and I'll have it call the environment and say, hey, this is what I did, what's the next state? And the environment does its thing right in here as I iterate through it. And then we want to go ahead and pick a random state to start with. That's what's going on here. You have to start somewhere. And then you have your playable actions. We're going to start with just an empty thing for playable actions, and we'll fill that up. So that's what choices I have. And so we're going to iterate through the rewards matrix to get the states. Directly reachable from the randomly chosen current state. assign those states to a list named playable actions. And so you can see here we have range 9. I usually use length of whatever I'm looking at, which is our locations or states as they are. We have a reward, so we want to look at the rewards. The new reward is in our chart here of rewards underscore new current state plus J. J being what is the next state we want to try. And so we go ahead and do our playable actions and we append J. And so what we're doing is we're randomly trying different things in here to see what's going to generate a better reward. And then of course we go ahead and choose our next state. So we have our random choice playable actions. And if you remember, I mentioned on this, let me just go ahead and, let's do a free form. When we were talking about the next state, this right here just does a random selection. Instead of a random selection, you might do something where whatever the best selection is, which might be option 3 here, and then so you can see that it might use a bell curve, and then option 2 over here might have a bell curve like this. Oops. And we start looking at these averages and these spreads, or we can just add them all together and pick the one that kind of goes in all of those. So those are some of the options we have in here. We just go with a random choice. That's usually where you start, play with it. And then we have our reward section down here. And so we want to go ahead and find, well, in this case, the temporal difference. So you have your rewards new plus the self gamma, and this is the formula we were looking at. This is Bellman's equation here. So we have our current value, our learning rate, our discount rate involved in there, the reward system coming in for that, and we can add it all together. This is, of course, our maximum expected future setup in here. So this is all of our Bellman's equation that we're looking at here. And then we come up in here and we update our Q table. That's all this is on this one. And that's right here. We have self Q, current state, next state, and we add in our alpha because we don't want to train all of it at once in case there's slight differentials coming in there. We want to slowly approach the answer. And then we have our route equals the start location, and next location equals start location. So we're just incrementing. We took a step forward. And then finally, remember I was telling you how we're going to do all this and just have some simple thing at the end where it just generates a simple path. We're going to go ahead and get the optimal route. We want to find the best route in here. And so we've created a definition for the optimal route down here. Just scroll down for that. And we get the optimal route. We go ahead and put the information in, including the Q table, self, start location, end location, next location, route, Q. And it says while next location is not equal to end location, so while we can still go, our start location equals self location to state start location. So we already have our best value for the start location. The next state looks at the Q table and says, hey, what's the next one with the best value? And then the next location, we go ahead and pull that in and we just append it. That's what's going on down here. And then our start location equals the next location. And we just go through all the steps. And we'll go ahead and run this. And now that we have our Q table, our Q agent loaded, we're going to go ahead and take our Q agent, load them up with our alpha, gamma that we set up above, along with the location step, action, reward, state to location. And our goal is to plot a course between L9 and L1. And we're going to go through 1,000 iterations on here. And so when I run that, it runs pretty quick. Why is this so fast? If you've been running neural networks and you've been doing all these other models, you sit here and wait a long time. Well, we're a very small amount of data. These are all integers. These aren't float values. The math is not heavy on the processing end. And this is where Q tables are so powerful. If you have a small amount of information coming in, you very quickly get an answer off of this, even though we went through it 1,000 times to train it. And you'll see here we have L9, 8, 5, 2, and 1, and that's based on our reward table we had set up on there. And this is the shortest path going between these different setups in here. And if you remember on our reward table, you can see that if you start here, you can go to here. There's places you can't go. That's how this reward table was set up. So I can only go to certain places. So kind of a little maze set up in there. And you can play with it. This is really fun setup to play with. And you can see how you can take this whole code and you can, like I was saying earlier, you can embed it into another setup and model and predictions where you put things into buckets and you're trying to guess the best investment, the best course of action. Long as you can take that course of action and reduce it down to a yes, no. Or if you're using text, you can use a one-hot encoder, which word is next. There's all kinds of things you can do with a Q table, depending on just how much information you're putting in there. So that wraps up our demo. In this demo, we've found the shortest distance between two paths based on whatever rules or state rewards we have to get from point A to point B and what available actions there are.
Hello and welcome to this tutorial on deep learning. My name is Mohan, and in the next about 1.5 hours I will take you through what is deep learning and into TensorFlow environment to show you an example of deep learning. Now, there are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of, based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons, the different types of neural networks, and then applications of deep learning. And we will also see how neural networks works. So how do we do the training of neural networks? And at the end, we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning, the handwriting number recognition, which is a MNIST, commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term artificial intelligence. So artificial intelligence is like the high level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning, where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. And it is a large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons, and this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed, and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron, and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least of one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2, and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output, and the summation is of course passed through the activation function. As you see here, this wixi summation plus b is passed through activation function, and then the neuron gets either fired or not, and based on that there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back, and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be zero. The error may not ever reach zero, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and the iteration continues till either the error is zero, which is an unlikely situation, or it is the minimum possible within these given conditions. Now, in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons. And that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0 again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather, in all the cases it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are 2 layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. And if you now look at the output, final output, where the threshold is taken as 1, if we use a sigmoid with the threshold 1, you will see that in these 2 cases it is 0, and in the last 2 cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of perceptron. Now that we got a good idea about perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they are good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music. And autonomous cars, you must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles when these images are fed? So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel, and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information, what is inside this image, can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now this is an animation of how this whole thing works. So these pixels, one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes these 784 pixels as input, the values of each of these pixels, and then you get an output which can be of three types or three classes. One can be a square, a circle, or a triangle. Now during the training process, there will be initially, obviously you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern. And during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangles. So this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these three types of objects. Now if you feed another image, and it will be able to identify whether it's a square or a triangle or a circle. Now what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle but maybe at the corner or in the side, it would still identify that it is a triangle. And that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs. It receives inputs, and then there is a weighted sum, which is nothing but this xi, wi, summation of that plus the bias. And this is then fed to the activation function, and that in turn gives us a output. Now during the training process, initially obviously when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights, W1, W2 up to Wn, keep changing in such a way that towards the end of the training process, it should be able to identify these images correctly. So till then, the weights are adjusted, and that is known as the training process. So, and these weights are numeric values. It could be 0.5, 0.25, 0.35, and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way. 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product Wi(xi) is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. So, but the bias also keeps changing. Initially it will again have a random value, but as a part of the training process, the weights, the values of the weights W1, W2, Wn and the value of B will change, and ultimately once the training process is complete, these values are fixed for this particular neuron. W1, W2 up to Wn, and plus the value of the B is also fixed for this particular neuron. And in this way there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are 2 hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process. And at the end of the training process, all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. And the activation function in turn takes the input, which is the weighted sum. Remember, we talked about WIXI plus B. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as Y hat. And then there is a labeled data, because for supervised learning, we already know what should be the output. So that is the actual output. And in the initial process, before the training is complete, obviously there will be error. So that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error. And the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of squares. Sum of square errors, or SSE, and that is then fed as a feedback in what is known as backward propagation or back propagation, and that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization, and this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima and the global minima using the differentiation and so on and so forth. But the idea is this. So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to converge. So you need to come up with the optimum value of the learning rate, and once that is done, using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value, and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So the algorithm is already there and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow, and so that's the reason we have this tutorial. We have created this tutorial for TensorFlow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a library, a Python library, so you can use Python or any other languages. It's also supported in other languages like Java and R and so on, but Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks, and it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number, and then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0, and then it can be a one-dimensional vector, in which case the rank is supposed to be 1, and then you can have a two-dimensional vector, typically like a matrix. Then in that case we say the rank is 2, and then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow we will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. You already have the data in the right format, which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation, and all of them are labeled. So you have the images and their label, and these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28, so there are 784 pixels. So pixel number 1 starts here, it goes all the way up to 28, then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use the pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library. And this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between is, it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code. And the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones. And placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then, of course, you will have variables, which are remember, these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784, because each neuron takes all the inputs. So if we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 780. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix, because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned bias is only one per neuron, so it is not one per input, unlike the weights. So therefore, there are only 10 biases, because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of 3 different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables, or at the most variables and constants. But in TensorFlow, you have 3 different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication, or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow, so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights, and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use. And reduce mean is what is like the mechanism which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because in that case it will take very long. So you define the optimizer, and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. We have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data, and we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, so this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, this 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here as we have seen in the slides. So we create one placeholder and we create two variables, which is for the weights and biases. These two variables are actually matrices, so each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the Y value is basically the label value. So this is another placeholder. We had X as one placeholder and Y underscore true as a second placeholder. And this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session, right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and b is a variable. So any variables that we created, you have to run this code, you have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this, but in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose, and then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnist function here. So we are saying mnist train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for the as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data, and you're trying to find out what is the actual value and what is the predicted value, and seeing whether they are equal or not, tf.equal, right? And how many of them are correct, and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Hello and welcome to the TensorFlow Object Detection API tutorial. In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries, for example, NumPy, we need image.io, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. All right. And then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. All right. And then here onwards, we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build a model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is, here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code, what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. We'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic_annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video underscore reader has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you are in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is a cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here. It is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it. Thank you very much for watching this video, and you have a great day. And in case you have any questions, please put them below the video here, and we will be more than happy to get back to you. And make sure you put your email ID so that we can contact you in case you have any questions. Thank you once again. Bye-bye.
Today we're going to be covering the convolutional neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in. So it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulations. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist, so we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer, ReLU is how that is pronounced, and that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN, what is convolution neural network, how CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for, and you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first 3 elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now obviously when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges, it might be looking for different parts. We'll cover that in a little bit more detail in a minute. Right now we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, is going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we have when we say linearity, we're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or the backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here is turn it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value. A little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together because then you might have like 5 1s and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data. And so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image. And if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there just looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7. And we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value. Which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer. Our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there, because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it, and then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So a great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape. We're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You could look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let's just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. You'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what X0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images, and it's very easy to look at them. And they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our value is equal to 10. What this means is that we have the 10 values. And look at the number, because one more than just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that. in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self all train batches. So we're going to make an array of all those different images. And then of course we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up these self-training images at this point, and that's going to go to a NumPy array VStack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32. We're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where we say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialize, we've already initialized it for 0. So we're going to look at x from 0 to batch size, which we set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self I plus batch size because the self I is going to keep changing. And then finally, we increment the self I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in, and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the cfar helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into 2 parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, since we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float 64 to float type, or is treated as an NP float 64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float 64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals tf placeholder tf float 32. We just talked about the float 64 versus the NumPy float. We're actually just going to keep this at float 32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder tf float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. we're going to go ahead and work on our convolutional 2D, our max pool. So we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions, and let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. Let me just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. Usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it, and of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes, and then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2 or whatever it is, that's what goes into the pooling, and what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2 by 2, and we put in the convolutional 1 that we just created. The convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so it knows to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4 by 4 going in, let's do 8 by 8 by 64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling, and then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer, and then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there. They change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. And exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy, or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out. It has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow, and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and Graph as just general graphing, but they talk about a graph session. So we're going to go ahead and run the model, and let's go ahead and walk through this, what's going on here. And let's paste this data in here, and here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run, so we're going to do with TF session as session right here. We've created our variable session, and then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. In the first process is we're going to do a session run. We're going to take our train. We created our train variable or optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created, and we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run, accuracy, feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this, oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0 it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because it doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.0, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. You can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is.
Deep learning. Deep learning was first introduced in the 1940s. Deep learning did not develop suddenly. It developed slowly and steadily over 7 decades. Many theses and discoveries were made on deep learning from the 1940s to 2000. Thanks to companies like Facebook and Google, the term deep learning has gained popularity and may give the perception that it is a relatively new concept. Deep learning can be considered as a type of machine learning and artificial intelligence, or AI, that imitates how humans gain certain types of knowledge. Deep learning includes statistics and predictive modeling. Deep learning makes processes quicker and simpler, which is advantageous to data scientists to gather, analyze, and interpret massive amounts of data. Having the fundamentals discussed, let's move into the different types of deep learning. Neural networks are the main component of deep learning, but neural networks comprise 3 main types, which contain artificial neural networks, or ANN, convolution neural networks, or CNN, and recurrent neural networks, or RNN. Artificial neural networks are inspired biologically by the animal brain. Convolutional neural networks surpass other neural networks when given inputs such as images, voice, or audio. It analyzes images by processing data. Recurrent neural networks uses sequential data or series of data. Convolutional neural networks and recurrent neural networks are used in natural language processes, speech recognition, image recognition, and many more. Machine learning. The evolution of ML started with the mathematical modeling of neural networks that served as the basis for the invention of machine learning. In 1943, neuroscientist Warren McCulloch and logician Walter Pitts attempted to quantitatively map out how humans make decisions and carry out thinking processes. Therefore, the term machine learning is not new. Machine learning is a branch of artificial intelligence and computer science that uses data and algorithms to imitate how humans learn, gradually increasing the system's accuracy. There are 3 types of machine learning, which include supervised learning. What is supervised learning? Well, here, machines are trained using labeled data. Machines predict output based on this data. Now, coming to unsupervised learning, models are not supervised using a training data set. It is comparable to the learning process that occurs in the human brain while learning something new. And the third type of machine learning is reinforcement learning. Here, the agent learns from feedback. It learns to behave in a given environment based on actions and the result of the action. And this feature can be observed in robotics. Now, coming to the evolution of AI. The potential of artificial intelligence wasn't explored until the 1950s, although the idea has been known for centuries. The term artificial intelligence has been around for a decade. Still, it wasn't until British polymath Alan Turing posed the question of why machines couldn't use knowledge like humans do to solve problems and make decisions. We can define artificial intelligence as a technique of turning a computer-based robot to work and act like humans. Now let's have a glance at the types of artificial intelligence. Weak AI performs only specific tasks, like Apple's Siri, Google Assistant, and Amazon's Alexa. You might have used all of these technologies, but the types I am mentioning after this are under experiment. General AI can also be addressed as artificial general intelligence. It is equivalent to human intelligence, hence, an AGI system is capable of carrying out any task that a human can. Strong AI aspires to build machines that are indistinguishable from the human mind. Both general and strong AI are hypothetical right now. Rigorous research is going on this matter. There are many branches of artificial intelligence, which include machine learning, deep learning, natural language processing, robotics, expert systems, fuzzy logic. Therefore, the correct answer for which is not a branch of artificial intelligence is option A, data analysis. Now that we have covered deep learning, machine learning, and artificial intelligence, the final topic is data science. Concepts like deep learning, machine learning, and artificial intelligence can be considered a subset of data science. Let us cover the evolution of data science. The phrase data science was coined in the early 1960s to characterize a new profession that would enable the comprehension and analysis of the massive volumes of data being gathered at the time. Since its beginnings, data science has expanded to incorporate ideas and methods from other fields, including artificial intelligence, machine learning, deep learning, and so forth. Data science can be defined as the domain of study that handles vast volumes of data using modern tools and techniques to find unseen patterns, derive meaningful information, and make business decisions. Therefore, data science comprises machine learning, artificial intelligence, and deep learning.
There are a lot of areas where data science can be used. One of the very common one is fraud detection or fraud prevention. There are a lot of fraudulent activities or transactions, primarily on the internet. It's very easy to commit fraud, and therefore we can use data science to either prevent or detect fraud. There are certain algorithms, machine learning algorithms, that can be used, like for example some outlier techniques, clustering techniques that can be used to detect fraud and prevent fraud as well. So who is a data scientist rather? It is actually a very generic role that defines somebody who is working with data is known as a data scientist, but there can be very specific activities and the roles can be actually much more specific. What exactly a person does within the area of data science can be much more specific. But broadly, anybody working in the area of data science is known as a data scientist. So what does a data scientist do? These are some of the activities: data acquisition, data preparation, data mining, data modeling, and then model maintenance. We will talk about each of these in a great detail, but at a very high level, the first step obviously is to get the raw data, which is known as data acquisition. It can be in all kinds of format and it could be multiple sources, but obviously that raw data cannot be used as it is for performing data mining activities or data modeling activities. So the data has to be cleansed and prepared for using in the data models or in the data mining activity. So that is the data preparation. Then we actually do the data mining, which can also include some exploratory activities. And then if we have to do stuff like machine learning, then you need to build a machine learning model and test the model, get insights out of it. And then if the model is fine, you deploy it, and then you need to maintain the model, because over a period of time it is possible that you need to tweak the model because of change in the process or change in the data and so on. So that all comes under the model maintenance. So let's take a deeper look at each each of these activities. Let's start with data acquisition. So in the stage of data acquisition, basically the data scientist will collect raw data from all possible sources. So this could be typically an RDBMS, which is a relational database, or it can also be a non-RDBMS, or it could be flat files or unstructured data and so on. So we need to bring all that data from different sources. If required, we need to do some kind of homogeneous formatting so that it all fits into looks, at least format, from a format perspective, it looks homogeneous. So that may be requiring some kind of transformation. Very often this is loaded into what is known as data warehouse. So this can also be sometimes referred to as ETL, or extract, transform and load. So a data warehouse is like a common place where data from different sources is brought together so that people can perform data science activities like reporting or data mining or statistical analysis and so on. So data from various sources is put in a centralized place, which is known as a data warehouse. So that is also known as ETL. And in order to do this, there can be, the data scientist can take help of some ETL tools. There are some existing tools that a data scientist can take help of, like for example, DataStage or Talent or Informatica. These are pretty good tools for performing these ETL activities and getting the data. The next stage, now that you have the raw data into a data warehouse, you still probably are not in a position to straight away use this data for performing the data mining activities. So that is where data preparation comes into play, and there are multiple reasons for that. One of them could be the data is dirty, there are some missing values and so on and so forth. So a lot of time is actually spent in this particular stage. So a data scientist spends a lot of time, almost 60 to 70% of the time, in this part of the project or the process, which is data preparation. So there are, again, within this there can be multiple sub activities, starting from, let's say, data cleaning. You will probably have missing values. The data, there is some columns, the values are missing, or the values are incorrect, there are null values, and so on and so forth. So that is basically the data cleaning part of it. Then you need to perform certain transformations, like for example normalizing the data and so on, right? So, or you could probably have to modify categorical values into numerical values and so on and so forth. So these are transformational activities. Then we may have to handle outliers. So the data could be such that there are a few values which are way beyond the normal behavior of the data. For whatever reason, either people have keyed in wrong values, or for some reason some of the values are completely out of range. So those are known as outliers. So there are certain ways of handling these outliers and detecting and handling these outliers. So this is a part of what is known as exploratory analysis. So you quickly explore the data to find out and you can use visual tools like plots and identify what are the outliers and see how we can get rid of the outliers and so on. Then the next part could be data integrity. Data integrity is to validate, for example, if there are some primary keys, that all the primary keys are populated. There are some foreign keys, then at least most of the foreign keys should be populated, and otherwise when we are trying to query the data, you may get wrong values and so on. So that is the data integrity part of it. And then we have what is known as data reduction. Sometimes we may have duplicate values, we may have columns that may be duplicated because they are coming from different sources, the same values are there, and so on. So a lot of this can be done using what is known as data reduction, and thereby you can reduce the size of the data drastically, because very often this could be redundant data which can be removed and so on. So let's take a look at what are the various techniques that are used for data cleaning. So we need to ensure that the data is valid and it is consistent and uniform and accurate. So these are the various parameters that we need to ensure as a part of the data cleaning process. Now, what are the techniques that are used for data cleaning? So we will see what each of these are in this particular case. And so what is the data set that we have? We have data about a bank and its customer details. So let's take an example and see how we go about cleaning the data. And in this particular example, we are assuming we are using Python. So let's assume we loaded this data, which is the raw file.csv. This is how the customer data looks like. And we will see, for example, if we take a closer look at the geography column, we will see that there are quite a few blank spaces. So how do we go about when we have some blank spaces, or if it is a string value, then we put an empty string here, or we just use a space or empty string. If they are numerical values, then we need to come up with a strategy. For example, we put the mean value. So wherever it is missing, we find the mean for that particular column. So in this case, let's assume we have credit score and we see that quite a few of these values are missing. So what do we do here? We find the mean for this column for all the existing values, and we found that the mean is equal to 638.6. So we kind of write a piece of code to replace wherever there are blank values. NaN is basically like null, and we just go ahead and say fill it with the mean value. So this is the piece of code we are writing to fill it. So all the blanks or all the null values get replaced with the mean value. Now, one of the reasons for doing this is that very often if you have some such situation, many of your statistical functions may not even work. So that's the reason you need to fill up these values, or either get rid of these records or fill up these values with something meaningful. So this is one mechanism, which is basically using a mean. There are a few others. As we move forward, we can see what are the other ways. For example, we can also say that any missing value in a particular row, if even one column the value is missing, you just drop that particular row, or delete all rows where even a single column has missing values. So that is one way of dealing. Now the problem here can be that if a lot of data has, let's say, 1 or 2 columns missing, and we drop many such rows, then overall you may lose out on, let's say, 60% of the data has some value or the other missing, 60% of the rows. Then it may not be a good idea to delete all the rows like in that manner, because then you're losing pretty much 60% of your data. Therefore your analysis won't be accurate. But if it is only 5 or 10%, then this will work. Another way is only to drop values where, or rather drop rows where all the columns are empty, which makes sense, because that means that record is of really no use because it has no information in it. So there can be some situations like that. So we can provide a condition saying that drop the records where all the columns are blank or not applicable. We can also specify some kind of a threshold. Let's say you have 10 or 20 columns in a row. You can specify that maybe 5 columns are blank or null, then you drop that record. So again, we need to take care that such a condition, such a situation, the amount of data that has been removed or excluded is not large. If it is like maybe 5%, maximum 10%, then it's okay. But by doing this, if you're losing out on a large chunk of data, then it may not be a good idea. You need to come up with something better. What else we need to do next is, so the data preparation part is done. So now we get into the data mining part. So what exactly we do in data mining? Primarily, we come up with ways to take meaningful decisions. So data mining will give us insights into the data, what is existing there, and then we can do additional stuff like maybe machine learning and so on to perform advanced analytics and so on. So one of the first steps we do is what is known as data discovery, and which is basically like exploratory analysis. So we can use tools like Tableau for doing some of this. So let's just take a quick look at how we go about that. So Tableau is excellent data mining, or actually more of a reporting or a BI tool. And you can download a trial version of Tableau at tableau.com, or there is also Tableau Public, which is free and you can actually use and play around. However, if you want to use it for enterprise purpose, then it is a commercial software, so you need to purchase license. And you can then run some of the data mining activities. Say your data source, your data is in some Excel sheet, so you can select the source as Microsoft Excel or any other format, that, and the data will be brought into the Tableau environment, and then it will show you what is known as dimensions and measures. So dimensions are all the descriptive columns, and Tableau is intelligent enough to actually identify these dimensions and measures. So measures are the numerical values. So as you can see here, customer ID, gender, geography, these are all dimensions, non-numerical values, whereas age, balance, credit score, and so on are numeric values, so they come under measures. So you got your data into Tableau, and then you want to, let's say, build a small model, and you want to, let's say, solve a particular problem. So what is the problem statement? All right, let's say we want to analyze why customers are leaving the bank, which is known as exit, and we want to analyze and see what are some of the factors for exiting the bank, and we want to, let's assume, consider these three of them, like let's say gender, credit card, and geography, these as a criteria, and analyze if these are in any way impacting or have some bearing on the customer exiting or the customer exit behavior. Okay, so let's use Tableau, and very quickly we will be able to find out how these parameters are affecting. All right, so let's see. So this is our customer data. So from our Excel sheet, we have data set about let's say 10,000 rows, and we want to find out what is the criteria. Let's start with gender. Let's say we want to first use gender as a criteria. So Tableau really offers an easy drag and drop kind of a mechanism, so that makes it really easy to perform this kind of analysis. So what we need to do is exited says whether the customer has exited or not, so it has a value of 0 and 1, and then of course you have gender and so on. So we will take these two and simply drag and drop. Okay, so exited, and then we will put gender. And if we drag and drop into the analysis side of Tableau, all right, so here what we are doing is we are showing male female as two different columns here, and 0 for people who did not exit and 1 for people who exited, and that is color coded. So the blue color means people who did not exit, and this yellow color means people who did exit. All right, so now if we pull the data here, create like bar graphs, this is how it would look. So what is yellow? Let's go back. So yellow is who exited, and for the male, only 16.45% have exited. And we can also draw a reference line that will help us, or even provide aliases. So these are a lot of fancy stuff that is provided by Tableau. You can create aliases, and so that it looks good rather than basic labels. And you can also add a reference line. So if you add a reference line, something like this, from here we can make out that on an average, female customers exit more than the male customers, right? So that is what we are seeing here on an average. So we have analyzed based on gender. We do see that there is some difference in the male and female behavior. Now let's take the next criteria, which is the credit card. So let's see if having a credit card has any impact on the customer exit behavior. So just like before, we drag and drop the credit card has credit card column. If we drag and drop here, and then we will see that there is pretty much no difference between people having credit card and not having credit card. 20.81% of people who have no credit card have exited, and similarly 20.18% of people who have credit card have also exited. So the credit card is not having much of an impact. That's what this piece of analysis shows. Last, we will basically go and check how the geography is impacting. So once again, we can drag and drop geography column onto this side, and if we see here, there are geographies like, I think there are about 3 geographies like France, Germany, and Spain, and we see that there is some kind of impact with the geography as well. Okay, so what we derive from this is that the credit card is really, we can ignore the credit card variable or feature from our analysis because that doesn't have any impact, but gender and geography we can keep and do further analysis. Okay, all right. So what are some of the advantages of data mining? Bit more detailed analysis can help us in predicting the future trends, and it also helps in identifying customer behavior patterns. Okay, so you can take informed decisions because the data is telling you or providing you with some insights, and then you take a decision based on that. If there is any fraudulent activity, data mining will help in quickly identifying such a fraud as well. And of course, it will also help us in identifying the right algorithm for performing more advanced data mining activities like machine learning and so on. All right, so the next activity, now that we have the data, we have prepared the data and perform some data mining activity, the next step is model building. Let's take a look at model building. So what is a model building? If we want to perform a more detailed data mining activity, like maybe perform some machine learning, then you need to build a model. And how do you build a model? First thing is you need to select which algorithm you want to use to solve the problem on hand, and also what kind of data that is available, and so on and so forth. So you need to make a choice of the algorithm, and based on that you go ahead and create a model, train the model, and so on. Now machine learning is kind of at a very high level classified into supervised and unsupervised. So if we want to predict a continuous value, could be a price or a temperature or a height or a length or things like that. So those are continuous values, and if you want to find some of those, then you use techniques like regression, linear regression, simple linear regression, multiple linear regression, and so on. So these are the algorithms. On the other hand, there will be situations, or there may be situations where you need to perform unsupervised learning. In case of unsupervised learning, you don't have any historical labeled data so to learn from. So that is when you use unsupervised learning, and some of the algorithms in unsupervised learning are clustering. K means clustering is the most common algorithm used in unsupervised learning. And similarly, in supervised learning, if you want to perform some activity on categorical values, like for example, it is not measured but it is counted, like you want to classify whether this image is a cat or a dog, whether you want to classify whether this customer will buy the product or not, or you want to classify whether this email is spam or not spam. So these are examples of categorical values, and these are examples of classification. Then you have algorithms like logistic regression, k nearest neighbor or KNN, and support vector machine. So these are some of the algorithms that are used in this case. And similarly, in case of unsupervised learning, if you need to perform on categorical values, you have some algorithms like association analysis and hidden Markov model. Okay, so in order to understand this better, let's take an example and take you through the whole process, and then we will also see how the code can be written to perform this. Now let's take our example here where we want to perform a supervised learning, which is basically we want to do a multilinear regression, which means there are multiple independent variables, and then we want to perform a linear regression to predict certain value. So in this particular example, we have world happiness data. So this is the data about the happiness quotient of people from various countries, and we are trying to predict and see whether how our model will perform. So what is the question that we need to ask? First of all, how to describe the data, and then can we make a predictive model to calculate the happiness score, right? So based on this, we can then decide on what algorithm to use and what model to use, and so on. So variables that are available or used in this model, this is a list of variables that are available. There is a happiness rank. I'll load the data or I'll show you the data in a little bit so it becomes clear what are these. So there is what is known as a happiness rank, happiness score, which is happiness score is more like an absolute value, whereas rank is what is the ranking, and then which country we are talking about, and within that country which region, and what kind of economy, and whether the family, which family, and health details, and freedom, trust, generosity, and so on and so forth. So there are multiple variables that are available to us, and the specific details probably are not required, and there can be in another example the variables can be completely different, so we don't have to go into the details of what exactly these variables are, but it's just enough to understand that we have a bunch of these variables, and now we need to use either all or some of these variables, and then which we also sometimes refer to as features, and then we need to build our model and train our model. Alright, so let's assume we will use Python in order to perform this analysis or perform this machine learning activity. And I will actually show you in our lab in a little bit. This whole thing, we will run the live code. But quickly, I will run you through the slides and then we will go into the lab. So what are we doing here? First thing we need to do is import a bunch of libraries in Python which are required to perform our analysis. Most of these are for manipulating the data, preparing the data, and then scikit-learn or sklearn is the library which we will use actually for this particular machine learning activity, which is linear regression. So we have NumPy, we have pandas, and so on and so forth. So all these libraries are imported, and then we load our data. And the data is in the form of a CSV file, and there are different files for each year. So we have data for 2015, 16, and 17. And so we will load this data and then combine them, concatenate them to prepare a single data frame. And here we are making an assumption that you are familiar with Python, so it becomes easier if you are familiar with Python programming language, or at least some programming language, so that you can at least understand by looking at the code. So we are reading the file, each of these files for each year, and this is basically we are creating a list of all the names of the columns we will be using later on. You will see in the code. So we have loaded 2015, then 2016, and then also 2017. So we have created 3 data frames, and then we concatenate all these 3 data frames. This is what we are doing here. Then we identify which of these columns are required, which, for example, some of the categorical values do we really need? We probably don't. Then we drop those columns so that we don't unnecessarily use all the columns and make the computation complicated. We can then create some plots using Plotly library, and it has some powerful features including creation of maps and so on, just to understand the pattern, the happiness quotient, or how the happiness is across all the countries. So it's a nice visualization. We can see each of these countries, how they are in terms of their happiness score. This is the legend here. So the lighter colored countries have lower ranking, and so these are the lower ranking ones, and these are higher ranking, which means that the ones with these dark colors are the happiest ones. So as you can see here, Australia and maybe this side, US and so on are the happiest ones. Okay, the other thing that we need to do is the correlation between the happiness score and happiness rank. We can find a correlation using a scatter plot, and we find that yes, they are kind of inversely proportional, which is obvious. So if the score is high, happiness score is high, then they are ranked number 1, for example. Highest is scored as number 1. So that's the idea behind this. So the happiness score given here and the happiness rank is actually given here. So they are inversely proportional, because the higher the score, the absolute value of the rank will be lower, right? So number 1 has the highest value of the score and so on. So they are inversely correlated, but there is a strong, what this graph shows is that there is a strong correlation between happiness rank and happiness score. And then we do some more plots to visualize this. We determine that probably rank and score are pretty much conveying the same message, so we don't need both of them. So we will kind of drop one of them, and that is what we are doing here. So we drop the happiness rank. And similarly, so this is one example of how we can remove some columns which are not adding value. So we will see in the code as well how that works. Moving on, this is the correlation between pretty much each of the columns with the other columns. So this is a correlation you can plot using plot function, and we will see here that, for example, happiness score and happiness score are correlated, strongest correlation, right? Because every variable will be highly correlated to itself. So that's the reason. So the darker the color is, the higher the correlation. And and correlation in numerical terms goes from 0 to 1. So 1 is the highest value, and it can only be between 0 and 1. Correlation between two variables can be only have a value between 0 and 1. So the numerical value can go from 0 to 1, and 1 here is dark color, and 0 is kind of dark, but it is blue color. From red it goes down, the dark blue color indicates pretty much no correlation. So from this heat map we see that happiness and economy and family are probably also health, probably are the most correlated, and then it keeps decreasing after freedom, kind of keeps decreasing and coming to pretty much 0. Alright, So that is a correlation graph, and then we can probably use this to find out which are the columns that need to be dropped, which do not have very high correlation, and we take only those columns that we will need. So this is the code for dropping some of the columns. Once we have prepared the data, when we have the required columns, then we use scikit-learn to actually split the data. First of all, this is a normal machine learning process. You need to split the data into training and test data set. In this case, we are splitting into 80-20. So 80 is the training data set and 20 is the test data set. So that's what we are doing here. So we use train test split method or function. So you have all your training data in x_train, the labels in y_train. Similarly, x_test has the test data, the inputs, whereas the labels are in y_test. So that's how, and this value, whether it is 80-20 or 50-50, that is all individual preference. So in our case, we are using 80-20. All right. And then the next is to create a linear regression instance. So this is what we are doing. We are creating an instance of linear regression, and then we train the model using the fit function, and we are passing x and y, which is the x value and the label data, regular input and the label data, label information. Then we do the test. We run we perform the evaluation on the test data set. So this is what we are doing with the test data set, and then we will evaluate how accurate the model is and using the scikit-learn functionality itself. We can also see what are the various parameters and what are the various coefficients, because in linear regression you will get like a equation of like a straight line, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. Those beta 1, beta 2, beta 3 are known as the coefficients, and beta 0 is the intercept. After the training, you can actually get these information of the model. What is the intercept value, what are the coefficients, and so on, by using these functions. So let's quickly go into the lab and take a look at our code. Okay, so this is my lab. This is my Jupyter notebook where the code, I have the actual code, and I will take you through this code to run this linear regression on the world happiness data. So we will import a bunch of libraries, NumPy, Pandas, Plotly, and so on. Also, yeah, scikit-learn, that's also very important. So that's the first step. Then I will import my data, and the data is in 3 parts. There are 3 files, one for each year, 2015, 2016, and 2017, and it is a CSV file. So I've imported my data. Let's take a look at the data, quickly glance at data. So this is how it looks. We have the country, region, happiness rank, and then happiness score. There are some standard errors, and then what is the per capita, family, and so on. So, and then we will keep going. We will create a list of all these column names we will be using later. So for now, I will run this code, and no need of major explanation at this point. We know that some of these columns probably are not required. So you can use this drop functionality to remove some of the columns which we don't need. Like for example, region and standard error will not be contributing to our model. So we will basically drop those values out here. So we use the drop, and then we created a vector with these names, column names. That's what we are passing here. Instead of giving the names of the columns here, we can pass a vector. So that's what we are doing. So this will drop from our data frame. It will remove region and standard error, these 2 columns. Then the next step, we will read the data for 2016 and also 2017, and then we will concatenate this data. So let's do that. So we have now data frame called happiness, which is a concatenation of all the 3 files. Let's take a quick look at the data now. So most of the unwanted columns have been removed, and you have all the data in one place for all the 3 years, and this is how the data looks. And if you want to take a look at the summary of the columns, you can say describe, and you will get this information. For example, for each of the columns, what is the count, what is the mean value, standard deviation, especially the numeric values, okay, not the categorical values. So this is a quick way to see how the data is, and initial little bit of exploratory analysis can be done here. So what is the maximum value, what's the minimum value, and so on for each of the columns. Alright, so then we go ahead and create some visualizations using Plotly. So let us go and build a plot. So if we see here, now this is the correlation between happiness rank and happiness score. This is what we have seen in the slides as well. We can see that there is a tight correlation between them. Only thing is it is inverse correlation, but otherwise they are very tightly correlated, which also says that they both probably provide the same information, so there is not much of value add. So we'll go ahead and drop the happiness rank as well from our columns. So that's what we are doing here. And now we can do the creation of the correlation heat map. Let us plot the correlation heat map to see how each of these columns is correlated to the others. And as we have seen in the slides, this is how it looks. So happiness score is very highly correlated. So this is the legend we have seen in the slide as well. So blue color indicates pretty much zero or very low correlation. Deep red color indicates very high correlation, and the value correlation is a numeric value, and the value goes from 0 to 1. If two items or two features or columns are highly correlated, then there will be as close to 1 as possible, and two columns that are not at all correlated will be as close to 0 as possible. So that's how it is. For example, here happiness score and happiness score, every column or every feature will be highly correlated to itself. So it is like between them there will be correlation value will be 1. So that's why we see deep red color. But then others are, for example, with higher values are economy, and then health, and then maybe family and freedom. So these are generosity and trust are not very highly correlated to happiness score. So that is one quick exploratory analysis we can do, and therefore we can drop the country and the happiness rank, because they also again don't have any major impact on the analysis, on our analysis. So now we have prepared our data. There was no need to clean the data because the data was clean, but if there were some missing values and so on, as we have discussed in the slides, we would have had to perform some of the data cleaning activities as well. But in this case, the data was clean. All we needed to do was just the preparation part. So we removed some unwanted columns and we did some exploratory data analysis. Now we are ready to perform the machine learning activity. So we use scikit-learn for doing the machine learning. Scikit-learn is a Python library that is available for performing our machine learning. Once again, we will import some of these libraries like pandas and numpy, and also scikit-learn. First step we will do is split the data in 2080 format. So you have all the test data, which is 20% of the data is test data and 80% is your training data. So this test size indicates how much of it is in the what is the size of the test data. So the remaining, which is here we are saying 0.2, therefore that means training is 0.8. So training data is 80%. All right, so we have executed that, split the data, and now we create an instance of the linear regression model. So LM is our linear regression model, and we pass X and Y, the training data set, and call the function fit so that the model gets trained. So now once that is done, training is completed, and now what we have to do is we need to predict the values for the test data. So the next step is using, so you see here fit will basically run the training method, predict will actually predict the values. So we are passing the input values, which is the independent variables, and we are asking for the values of the dependent variable, which we are capturing in y_pred, and we use the predict method here, lm.predict. So this will give us all the predicted y values, and remember we already have y_test has the actual values, which are the labels, so that we can use these two to compare and find out how much of it is error. So that's what we are doing here. We are trying to find the difference between the predicted value and the actual value. Y_test is the actual value for the test data, and y_predict is the predicted value. We just found out the predicted value. So we will run that and we can do a quick check as to how the data looks, how is the difference. So in some cases it is positive, Some cases it is negative, but in most of the cases I think the difference is very small. This is exponential to the power of 0, minus 0.4 and so on. So looks like our model has performed reasonably well. We can now check some of the parameters of our model, like the intercept and the coefficients. So that's what we are doing here. So these are the coefficients of the various parameters that we are, the coefficients of the various independent variables. Okay, so these are the values. Then we can quickly go ahead and list them down as well against the corresponding independent variable. So the coefficients against the corresponding independent variable. So 1.00051 is the coefficient for economy, 0.99983 is for family, coefficient for family and health, and so on and so forth, right? So that's what this is showing. Now we can use the functionality, readily available functionality of scikit-learn, and then plot that to find some of the parameters which determine the accuracy of this model, like for example, what is the mean square error and so on. So that's what we are doing here. So let's just go ahead and run this. So you can see here that the root mean square error is pretty low, which is a good sign, and which is one of the measures of how well our model is performing. We can do one more quick plot to just see how the actual values and the predicted values are looking. And once again, you can see that as we have seen from the root mean square error is very, very low. That means that the actual values and the predicted values are pretty much matching up, almost matching up, and this plot also shows the same. So this line is going through the predicted values and the actual values, and the difference is very, very low. So again, this is actual data. This is one example where the accuracy is high and the predicted values are pretty much matching with the actual values, but in real life you may find that these values are slightly more scattered, and you may get the error value can be relatively on the higher side, the root mean square error. Okay, so this was a good and quick example of the code to perform data science activity or a machine learning or data mining activity. In this case, we did what is known as linear regression. So let's go back to our slides and see what else is there. So we saw this. These are the coefficients of each of the features in our code, and we have seen the root mean square error as well, and we can take a few hundred countries, certain values, and actually predict to see if how the model is performing, and I think we have done this as well. And in this case, as we have seen, pretty much the predicted values and the actual values are pretty much matching, which means our model is almost 100% accurate. As I mentioned, in real life it may not be the case, but in this particular case we have got a pretty good model, which is very good. Also, subsequently we can assume that this is how the equation in linear regression, the model is nothing but an equation like y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. So this is what we are showing here. So this is our intercept, which is beta 0, and then we have beta 1 into economy value, beta 2 into the family value, beta 3 into health value, and so on. So that is what is shown here. Okay, so I think the next step, once we have the results from the data mining or machine learning activity, the next step is to communicate these results to the appropriate stakeholders. So that is what we will see here now. So how do we communicate? Usually you take these results and then either prepare a presentation or put it in a document and then show them these actionable results or actionable insights. And you need to find out who are your target audience and put all the results in context. And maybe if there was a problem statement, you need to put the results in the context of the problem statement. What was our initial goal that we wanted to achieve? So that we need to communicate here based on, you remember we started off with what is the question and what is the data and so on, and then what is the answer. So we need to put the results and then what is the methodology that we have used. All that has to be put and clearly communicated in business terms so that the people understand very well from a business perspective. So once the model building is done, once the results are published and communicated, the last part is maintenance of this model. Now very often what can happen is the model may have to be subsequently updated or modified because of multiple reasons. Either the data has changed, the way the data comes has changed, or the process has changed, or for whatever reason the accuracy may keep changing. Once you have trained the model, for example, we got a very high accuracy, but then over a period of time there can be various factors which can cause that. So from time to time we need to check whether the model is performing well or not. The accuracy needs to be tested once in a while, and if required you may have to rebuild or retrain the model. So you do the assessment, you see if it needs any tweaks or changes, and then if it is required you need to probably retrain the model with the latest data that you have, and then you deploy it. You build the model, train it, and then you deploy it. So that is like the maintenance cycle that you may have to take the model.
Data analyst versus data engineer versus data scientist. Which one to choose? This is one of the most popular questions asked by learners looking for a career in data and analytics. I'm sure you too would have come across these job roles in the ever-growing data science landscape. Though they all deal with data, these jobs are not the same. There are significant differences between what a data analyst, data engineer, and a data scientist does. We will look at these job roles and the differences in detail. First, let's look at some data analytics and data science trends. The analytics and data science market is thriving. Data analytics, data engineering, and data science are the key trends in today's accelerating market. As per Statista.com, the global big data analytics market revenue will grow at a CAGR of 30%, with revenue reaching over $68 billion by 2025. According to TechNavio, the enterprise data management market is expected to increase by $64.08 billion by 2025. As per marketsandmarkets.com, the big data market size is projected to grow from $162.6 billion in 2021 to $273.4 billion in 2026. Now, another report from Research Drive says that the data science platform market is estimated to reach $224.3 billion by 2026. So with so much data available and companies making huge investments to drive business insights, the job opportunities for data analysts, data engineers, and data scientists are going to increase in 2022 and over the coming years. Now, let's learn the major differences between data analyst versus data engineer versus data scientist. So, who are they? A data analyst analyzes and interprets vast volumes of data in order to extract meaningful information out of it. They find solutions to a business problem and make critical business decisions. The insights provided by data analysts are important to companies that want to understand the needs of their end customers. Now, talking about who a data engineer is, a data engineer, on the other hand, builds infrastructure and scalable pipelines to manage the flow of data and prepare it for analysis. So basically, they optimize the systems that enable data analysts and data scientists to perform their job efficiently. Data scientists are professionals who analyze and visualize existing data and use algorithms to build predictive models for making future decisions. They also engage with business leaders to understand their needs and present complex findings. With that, let's look at the primary roles and responsibilities of these three job roles. Data analysts are responsible to collect, clean, store, and process data. They discover hidden patterns from data by performing exploratory data analysis and visualize data by creating charts and graphs. Acquiring data from primary and secondary sources is one of their key tasks. They build reports and dashboards and also maintain databases. Now, talking about the roles and responsibilities of a data engineer. A data engineer performs data acquisition. They design, build, and test data as well to develop and maintain data architecture. Data engineers are tasked with testing, integrating, managing, and optimizing data from a variety of sources. So they integrate data into existing data pipelines, prepare data for modeling, and perform various ETL operations. Now, talking about the roles and responsibilities of a data scientist. So data scientists develop machine learning models to identify trends in data for making decisions. They develop hypotheses and use their knowledge of statistics, data visualization, and machine learning to forecast the future for the business. Data scientists visualize data and use storytelling techniques, and also write programs to automate data collection and processing. Now move on to the skills possessed by data analysts, data engineers, and data scientists. To become a data analyst, you need to have good hands-on experience with writing SQL queries. You should have excellent Microsoft Excel skills for analyzing data. Data analysts are also good at programming, and they need to know how to visualize data, solve business problems, and possess domain knowledge. Data engineers should have a solid understanding of SQL, MongoDB, and programming. They need to have a good command of data architecture, scripting, data warehousing, and ETL. Data engineers are also good at Hadoop-based analytics. Now talking about the skills for a data scientist. So a data scientist should have experience with programming in Python and R. They should have a very good understanding of mathematics and statistics as well. Data scientists need to possess analytical thinking and data visualization skills as well. Machine learning, deep learning, and decision making are other critical skills every data scientist should have. Now we look at the salaries of a data scientist, a data analyst, as well as a data engineer. So a data analyst in the United States earns over $70,000 per annum, while in India a data analyst can earn nearly 7,25,000 rupees per annum. A data engineer in the United States can earn over $112,500 per year, and in India you can earn over 9 lakh rupees per annum. Now, talking about the salary of a data scientist in the United States earns over $117,000 per annum, and in India a data scientist can earn over 11 lakh rupees per annum. Now, coming to the final section of this video, we'll look at the top companies hiring for data analysts, data engineers, and data scientists. So we have the first company as Google, then we have Tesla, next we have the e-commerce giant Amazon, the internet giant Facebook, or the social media giant Facebook, we have the tech giant Oracle, we also have Verizon and Airbnb. So these are some of the top companies that hire for the three roles.
Now let's talk about the life cycle of a data science project. Okay, the first step is the concept study. In this step, it involves understanding the business problem, asking questions, get a good understanding of the business model, meet up with all the stakeholders, understand what kind of data is available, and all that is a part of the first step. So here are a few examples. We want to see what are the various specifications, and then what is the end goal, what is the budget, is there an example of this kind of a problem that has been maybe solved earlier. So all this is a part of the concept study. And another example could be a very specific one to predict the price of a 1.35 carat diamond, and there may be relevant information, inputs that are available, and we want to predict the price. The next step in this process is data preparation, data gathering and data preparation, also known as data munging, or sometimes it is also known as data manipulation. So what happens here is the raw data that is available may not be usable in its current format for various reasons. So that is why in this step, a data scientist would explore the data. He will take a look at some sample data, maybe pick, if there are millions of records, pick a few thousand records and see how the data is looking. Are there any gaps? Is the structure appropriate to be fed into the system? Are there some columns which are probably not adding value, may not be required for the analysis? Very often these are like names of the customers. They will probably not add any value or much value from an analysis perspective. the structure of the data. Maybe the data is coming from multiple data sources and the structures may not be matching. What are the other problems? There may be gaps in the data. So the data, all the columns, all the cells are not filled. If you're talking about structured data, there are several blank records or blank columns. So if you use that data directly, you'll get errors or you'll get inaccurate results. So how do you either get rid of that data or how do you fill these gaps with something meaningful? So all that is a part of data munging or data manipulation. So these are some additional subtopics within that. So data integration is one of them. If there are any conflicts in the data, data may be redundant. Yeah, data redundancy is another issue. There may be, you have, let's say, data coming from two different systems and both of them have customer table, for example, customer information. So when you merge them, there is a duplication issue. So how do we resolve that? So that is one. Data transformation. As I said, there will be situations where data is coming from multiple sources and then when we merge them together, they may not be matching. So we need to do some transformations to make sure everything is similar. We may have to do some data reduction. If the data size is too big, you may have to come up with ways to reduce it meaningfully without losing information. Then data cleaning. So there will be either wrong values or null values or there are missing values. So how do you handle all of that? A few examples of very specific stuff. So if there are missing values, how do you handle missing values or null values? Here in this particular slide, we are seeing three types of issues. One is missing value. Then you have null value. You see the difference between the two, right? So in the missing value, there is nothing, blank. Null value, it says null. Now, the system cannot handle if there are null values. Similarly, there is improper data. So it's supposed to be numeric value, but there is a string or a non-numeric value. So how do we clean and prepare the data so that our system can work flawlessly? So there are multiple ways and there is no one common way of doing this. It can vary from project to project. It can vary from what exactly is the problem we are trying to solve. It can vary from data scientist to data scientist, organization to organization. So these are like some standard practices people come up with. And of course, there will be a lot of trial and error. Somebody would have tried out something and it worked and will continue to use that mechanism. So that's how we need to take care of data cleaning. Now, what are the various ways of doing, if values are missing? How do you take care of that? Now, if the data is too large and only a few records have some missing values, then it is okay to just get rid of those entire rows, for example. So if you have 1,000,000 records and out of which 100 records don't have full data, so there are some missing values in about 100 records. So it's absolutely fine because it's a small percentage of the data. So you can get rid of the entire records which have missing values. But that's not a very common situation. Very often you will have multiple or at least a large number of a data set. For example, out of 1,000,000 records, you may have 50,000 records which are like having missing values. Now, that's a significant amount. You cannot get rid of all those records. Your analysis will be inaccurate. So how do you handle such situations? So there are again multiple ways of doing it. One is you can probably, if a particular values are missing in a particular column, you can probably take the mean value for that particular column and fill all the missing values with the mean value, so that first of all you don't get errors because of missing values, and second, you don't get results that are way off because these values are completely different from what is there. So that is one way. Then a few other could be either taking the median value or depending on what kind of data we are talking about. So something meaningful we will have put in there. If we are doing some machine learning activity, then obviously as a part of data preparation, you need to split the data into training and test data set. The reason being, if you try to test with a data set which the system has already seen as a part of training, then it will tend to give reasonably accurate results because it has already seen that data, and that is not a good measure of the accuracy of the system. So typically you take the entire data set, the input data set, and split it into two parts, and again the ratio can vary from person to person, individual preferences. Some people like to split it into 50-50, some people like it as 63.33 and 33.3 is basically 2/3 and 1/3, and some people do it as 80-20, 80 for training and 20 for testing. So you split the data, perform the training with the 80%, and then use the remaining 20% for testing. All right, so that is one more data preparation activity that needs to be done before you start analyzing or applying the data or putting the data through the model. Then the next step is model planning. Now these models can be statistical models, this could be machine learning models, so you need to decide what kind of models you're going to use. Again, it depends on what is the problem you're trying to solve. If it is a regression problem, you need to think of a regression algorithm and come up with a regression model. So it could be linear regression. Or if you're talking about classification, then you need to pick up an appropriate classification algorithm like logistic regression or decision tree or SVM, and then you need to train that particular model. So that is the model building or model planning process, and the cleaned up data has to be fed into the model. And apart from cleaning, you may also have to, in order to determine what kind of model you will use, you have to perform some exploratory data analysis to understand the relationship between the various variables and see if the data is appropriate and so on, right? So that is the additional preparatory step that needs to be done. So a little bit of details about exploratory data analysis. So what exactly is exploratory data analysis? It's basically to, as the name suggests, you're just exploring. You just receive the data and you're trying to explore and find out what are the data types and what is the data clean in each of the columns. What is the maximum minimum value? So for example, there are out of the box functionality available in tools like R. So if you just ask for a summary of the table, it will tell you for each column, it will give some details as to what is the mean value, what is the maximum value, and so on and so forth. So this exercise or this exploratory analysis is to get an understanding of your data. And then you can take steps to, during this process, you find there are a lot of missing values. You need to take steps to fix those. You will also get an idea about what kind of model to be used and so on and so forth. What are the various techniques used for exploratory data analysis? Typically, these would be visualization techniques, like you use histograms, you can use box plots, you can use scatter plots. So these are very quick ways of identifying the patterns or a few of the trends of the data and so on. And then once your data is ready, you've decided on the model, what kind of algorithm you're going to use. If you're trying to do machine learning, you need to pass your 80% the training data, or rather you use that training data to train your model. And the training process itself is iterative. So the training process you may have to perform multiple times. And once the training is done and you feel it is giving good accuracy, then you move on to test. So you take the remaining 20% of the data. Remember, we split the data into training and test. So the test data is now used to check the accuracy or how well our model is performing. And if there are further issues, let's say, and model is still, during testing, if the accuracy is not good, then you may want to retrain your model or use a different model. So this whole thing again can be iterative. But if the test process is passed, or if the model passes the test, then it can go into production and it will be deployed. All right. So what are the various tools that we use for model planning? R is an excellent tool in a lot of ways. Whether you're doing regular statistical analysis or machine learning or any of these activities, R, along with RStudio, provides a very powerful environment to do data analysis, including visualization. It has a very good integrated visualization or plot mechanism which can be used for doing exploratory data analysis, and then later on to do analysis, detailed analysis and machine learning and so on and so forth. Then of course you can write Python programs. Python offers a rich library for performing data analysis and machine learning and so on. MATLAB is a very popular tool as well, especially during education. So this is a very easy to learn tool. So MATLAB is another tool that can be used. And then last but not least, SAS. SAS is again very powerful. It is a proprietary tool and it has all the components that are required to perform very good statistical analysis or perform data science. So those are the various tools that would be required for, or that can be used for model building. And so the next step is model building. So we have done the planning part. We said, okay, what is the algorithm we are going to use? What kind of model we are going to use? Now we need to actually train this model, or build the model rather, so that it can then be deployed. So what are the various ways, or what are the various types of model building activities? So it could be, let's say in this particular example that we have taken, you want to find out the price of 1.35 carat diamond. So this is, let's say, a linear regression problem. You have data for various carats of diamond and you use that information, you pass it through a linear regression model, or you create a linear regression model which can then predict your price for 1.35 carat. So this is one example of model building. And then a little bit details of how linear regression works. So linear regression is basically coming up with a relation between an independent variable and a dependent variable. So it is pretty much like coming up with equation of a straight line which is the best fit for the given data. So like for example here, y is equal to mx plus c. So y is the dependent variable and x is the independent variable. We need to determine the values of m and c for our given data. So that is what the training process of this model does. At the end of the training process, you have a certain value of m and c, and that is used for predicting the values of any new data that comes. Alright, so the way it works is we use the training and the test data set to train the model and then validate whether the model is working fine or not using test data. And if it is working fine, then it is taken to the next level, which is put in production. If not, the model has to be retrained. If the accuracy is not good enough, then the model is retrained, maybe with more data, or you come up with a newer model or algorithm and then repeat that process. So it is an iterative process. Once the training is completed, training and test, then this model is deployed and we can use this particular model to determine what is the price of 1.35 carat diamond. Remember, that was our problem statement. So now that we have the best fit for this given data, we have the price of 1.35 carat diamond, which is 10,000. So this is one example of how this whole process works. Now, how do we build the model? There are multiple ways. You can use Python, for example, and use libraries like Pandas or NumPy to build the model and implement it. This will be available as a separate tutorial, a separate video in this playlist. So stay tuned for that. Moving on, once we have the results, the next step is to communicate these results to the appropriate stakeholders. So which is basically taking this results and preparing like a presentation or a dashboard and communicating these results to the concerned people. So finishing or getting the results of the analysis is not the last step, but you need to, as a data scientist, take these results and present it to the team that has given you this problem in the first place and explain your findings, explain the findings of this exercise and recommend maybe what steps they need to take in order to overcome this problem or solve this problem. So that is the pretty much once that is accepted, and the last step is to operationalize. So if everything is fine, your data scientist presentations are accepted, then they put it into practice and thereby they will be able to improve or solve the problem that they stated in step 1. Okay, so quick summary of the life cycle. You have a concept study, which is basically understanding the problem, asking the right questions, and trying to see if there is enough data to solve this problem. And then even maybe gather the data. Then data preparation, the raw data needs to be manipulated. You need to do data munging so that you have the data in a certain proper format to be used by the model or our analytics system. And then you need to do the model planning, what kind of a model, what algorithm you will use for a given problem. and then the model building. So the exact execution of that model happens in step 4, and you implement and execute that model and put the data through the analysis in this step, and then you get the results. These results are then communicated, packaged and presented and communicated to the stakeholders, and once that is accepted, that is operationalized. So that is the final step.
Let's begin this lesson by defining the term statistics. Statistics is a mathematical science pertaining to the collection, presentation, analysis, and interpretation of data. It's widely used to understand the complex problems of the real world and simplify them to make well-informed decisions. Several statistical principles, functions, and algorithms can be used to analyze primary data, build a statistical model, and predict the outcomes. An analysis of any situation can be done in 2 ways: statistical analysis or a non-statistical analysis. Statistical analysis is the science of collecting, exploring, and presenting large amounts of data to identify the patterns and trends. Statistical analysis is also called quantitative analysis. Non-statistical analysis provides generic information and includes text, sound, still images, and moving images. Non-statistical analysis is also called qualitative analysis. Although both forms of analysis provide results, statistical analysis gives more insight and a clearer picture, a feature that makes it vital for businesses. There are 2 major categories of statistics: descriptive statistics and inferential statistics. Descriptive statistics helps organize data and focuses on the main characteristics of the data. It provides a summary of the data numerically or graphically. Numerical measures such as average, mode, standard deviation or SD, and correlation are used to describe the features of a dataset. Suppose you want to study the height of students in a classroom. In the descriptive statistics, you would record the height of every person in the classroom and then find out the maximum height, minimum height, and average height of the population. Inferential statistics generalizes the larger dataset and applies probability theory to draw a conclusion. It allows you to infer population parameters based on the sample statistics and to model relationships within the data. Modeling allows you to develop mathematical equations which describe the interrelationships between 2 or more variables. Consider the same example of calculating the height of students in the classroom. In inferential statistics, you would categorize height as tall, medium, and small, and then take only a small sample from the population to study the height of students in the classroom. The field of statistics touches our lives in many ways, from the daily routines in our homes to the business of making the greatest cities run. The effect of statistics are everywhere. There are various statistical terms that one should be aware of while dealing with statistics: population, sample, variable, quantitative variable, qualitative variable, discrete variable, continuous variable. A population is the group from which data is to be collected. A sample is a subset of a population. A variable is a feature that is characteristic of any member of the population differing in quality or quantity from another member. A variable differing in quantity is called a quantitative variable. For example, the weight of a person, number of people in a car. A variable differing in quality is called a qualitative variable or attribute. For example, color, the degree of damage of a car in an accident. A discrete variable is one which no value can be assumed between the 2 given values. For example, the number of children in a family. A continuous variable is one in which any value can be assumed between the 2 given values. For example, the time taken for a 100-meter run. Typically, there are 4 types of statistical measures used to describe the data. They are measures of frequency, measures of central tendency, measures of spread, measures of position. Let's learn each in detail. Frequency of the data indicates the number of times a particular data value occurs in the given dataset. The measures of frequency are number and percentage. Central tendency indicates whether the data values tend to accumulate in the middle of the distribution or toward the end. The measures of central tendency are mean, median, and mode. Spread describes how similar or varied the set of observed values are for a particular variable. The measures of spread are standard deviation, variance, and quartiles. The measure of spread are also called measures of dispersion. Position identifies the exact location of a particular data value in the given data set. The measures of position are percentiles, quartiles, and standard scores. Statistical Analysis System, or SAS, provides a list of procedures to perform descriptive statistics. They are as follows: proc print, proc contents, proc means, proc frequency, proc univariate, proc gchart, proc boxplot, proc gplot. Proc print. It prints all the variables in a SAS dataset. Proc contents. It describes the structure of a dataset. Proc means. It provides data summarization tools to compute descriptive statistics for variables across all observations and within the groups of observations. Proc frequency. It produces one-way to n-way frequency and cross-tabulation tables. Frequencies can also be an output of a SAS dataset. Proc univariate. It goes beyond what proc means does and is useful in conducting some basic statistical analyses and includes high-resolution graphical features. Proc gchart. The gchart procedure produces 6 types of charts: block charts, horizontal, vertical bar charts, pie, donut charts, and star charts. These charts graphically represent the value of a statistic calculated for one or more variables in an input SAS dataset. The charted variables can be either numeric or character. Proc boxplot. The boxplot procedure creates side-by-side box and whisker plots of measurements organized in groups. A box and whisker plot displays the mean, quartiles, and minimum and maximum observations for a group. Proc gplot. Gplot procedure creates two-dimensional graphs, including simple scatter plots, overlay plots in which multiple sets of data points are displayed on one set of axes, plots against a second vertical axis, bubble plots, and logarithmic plots. In this demo, you'll learn how to use descriptive statistics to analyze the mean from the electronic dataset. Let's import the electronic dataset into the SAS console. In the left plane, right-click the electronic.xlsx dataset and click Import Data. The code to import the data generates automatically. Copy the code and paste it in the new window. The proc means procedure is used to analyze the mean of the imported dataset. The keyword data identifies the input dataset. In this demo, the input dataset is electronic. The output obtained is shown on the screen. Note that the number of observations, mean, standard deviation, and maximum and minimum values of the electronic dataset are obtained. This concludes the demo on how to use descriptive statistics to analyze the mean from the electronic dataset. So far, you have learned about descriptive statistics. Let's now learn about inferential statistics. Hypothesis testing is an inferential statistical technique to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for the entire population. To understand the characteristics of the general population, we take a random sample and analyze the properties of the sample. We then test whether or not the identified conclusions correctly represent the population as a whole. The population of hypothesis testing is to choose between two competing hypotheses about the value of a population parameter. For example, one hypothesis might claim that the wages of men and women are equal, while the other might claim that women make more than men. Hypothesis testing is formulated in terms of two hypotheses: null hypothesis, which is referred to as H-null; alternative hypothesis, which is referred to as H1. The null hypothesis is assumed to be true unless there is strong evidence to the contrary. The alternative hypothesis is assumed to be true when the null hypothesis is proven false. Let's understand the null hypothesis and alternative hypothesis using a general example. Null hypothesis attempts to show that no variation exists between variables, and alternative hypothesis is any hypothesis other than the null. For example, say a pharmaceutical company has introduced a medicine in the market for a particular disease, and people have been using it for a considerable period of time, and it's generally considered safe. If the medicine is proved to be safe, then it is referred to as null hypothesis. To reject null hypothesis, we should prove that the medicine is unsafe. If the null hypothesis is rejected, then the alternative hypothesis is used. Before you perform any statistical tests with variables, it's significant to recognize the nature of the variables involved. Based on the nature of the variables, it's classified into 4 types. They are categorical or nominal variables, ordinal variables, interval variables, and ratio variables. Nominal variables are ones which have 2 or more categories, and it's impossible to order the values. Examples of nominal variables include gender and blood group. Ordinal variables have values ordered logically. However, the relative distance between 2 data values is not clear. Examples of ordinal variables include considering the size of a coffee cup, large, medium, and small, and considering the ratings of a product, bad, good, and best. Interval variables are similar to ordinal variables, except that the values are measured in a way where their differences are meaningful. With an interval scale, equal differences between scale values do have equal quantitative meaning. For this reason, an interval scale provides more quantitative information than the ordinal scale. The interval scale does not have a true 0 point. A true 0 point means that a value of 0 on the scale represents 0 quantity of the construct being assessed. Examples of interval variables include the Fahrenheit scale used to measure temperature and distance between 2 compartments in a train. Ratio scales are similar to interval scales in that equal differences between scale values have equal quantitative meaning. However, ratio scales also have a true 0 point, which give them an additional property. For example, the system of inches used with a common ruler is an example of a ratio scale. There is a true 0 point because 0 inches does in fact indicate a complete absence of length. In this demo, you'll learn how to perform the hypothesis testing using SAS. In this example, let's check against the length of certain observations from a random sample. The keyword data identifies the input dataset. The input statement is used to declare the aging variable and cards to read data into SAS. Let's perform a t-test to check the null hypothesis. Let's assume that the null hypothesis to be that the mean days to deliver a product is 6 days. So null hypothesis equals 6. Alpha value is the probability of making an error, which is 5% standard, and hence alpha equals 0.05. The variable statement names the variable to be used in the analysis. The output is shown on the screen. Note that the p-value is greater than the alpha value, which is 0.05. Therefore, we fail to reject the null hypothesis. This concludes the demo on how to perform the hypothesis testing using SAS. Let's now learn about hypothesis testing procedures. There are 2 types of hypothesis testing procedures. They are parametric tests and non-parametric tests. In statistical inference or hypothesis testing, the traditional tests, such as t-test and ANOVA, are called parametric tests. They depend on the specification of a probability distribution except for a set of free parameters. In simple words, you can say that if the population information is known completely by its parameter, then it is called a parametric test. If the population or parameter information is not known, and you are still required to test the hypothesis of the population, then it's called a non-parametric test. Non-parametric tests do not require any strict distributional assumptions. There are various parametric tests. They are as follows: t-test, ANOVA, chi-squared, linear regression. Let's understand them in detail. T-test. A t-test determines if two sets of data are significantly different from each other. The t-test is used in the following situations: to test if the mean is significantly different than a hypothesized value, to test if the mean for two independent groups is significantly different, to test if the mean for two dependent or paired groups is significantly different. For example, let's say you have to find out which region spends the highest amount of money on shopping. It's impractical to ask everyone in the different regions about their shopping expenditure. In this case, you can calculate the highest shopping expenditure by collecting sample observations from each region. With the help of the t-test, you can check if the difference between the regions are significant or a statistical fluke. ANOVA. ANOVA is a generalized version of the t-test and used when the mean of the interval-dependent variable is different to the categorical independent variable. When we want to check variance between two or more groups, we apply the ANOVA test. For example, let's look at the same example of the t-test example. Now you want to check how much people in various regions spend every month on shopping. In this case, there are four groups, namely East, West, North, and South. With the help of the ANOVA test, you can check if the difference between the regions is significant or a statistical fluke. Chi-square. Chi-square is a statistical test used to compare observed data with data you would expect to obtain according to a specific hypothesis. Let's understand the chi-square test through an example. You have a data set of male shoppers and female shoppers. Let's say you need to assess whether the probability of females purchasing items of $500 or more is significantly different from the probability of males purchasing items of $500 or more. Linear regression. There are two types of linear regression: simple linear regression and multiple linear regression. Simple linear regression is used when one wants to test how well a variable predicts another variable. Multiple linear regression allows one to test how well multiple variables, or independent variables, predict a variable of interest. When using multiple linear regression, we additionally assume the predictor variables are independent. For example, finding a relationship between any two variables, say sales and profit, is called simple linear regression. Finding a relationship between any three variables, say sales, cost, and telemarketing, is called multiple linear regression. Some of the non-parametric tests are Wilcoxon rank sum test and Kruskal-Wallis H-test. Wilcoxon rank sum test. The Wilcoxon signed rank test is a non-parametric statistical hypothesis test used to compare two related samples or matched samples to assess whether or not their population mean ranks differ. In Wilcoxon rank sum test, you can test the null hypothesis on the basis of the ranks of the observations. Kruskal-Wallis H-test. Kruskal-Wallis H-test is a rank-based non-parametric test used to compare independent samples of equal or different sample sizes. In this test, you can test the null hypothesis on the basis of the ranks of the independent samples. The advantages of parametric tests are as follows. Provide information about the population in terms of parameters and confidence intervals. Easier to use in modeling, analyzing, and for describing data with central tendencies and data transformations. Express the relationship between two or more variables. Don't need to convert data into rank order to test. The disadvantages of parametric tests are as follows. Only support normally distributed data. Only applicable on variables, not attributes. Let's now list the advantages and disadvantages of non-parametric tests. The advantages of non-parametric tests are as follows. Simple and easy to understand. Do not involve population parameters and sampling theory. Make fewer assumptions. provide results similar to parametric procedures. The disadvantages of non-parametric tests are as follows. Not as efficient as parametric tests, difficult to perform operations on large samples manually.
We'll discuss the types of distribution in statistics. But before we move ahead, let's have a brief introduction on what is probability distribution. A probability distribution is a list of all of the possible outcomes of a random variable along with their corresponding probability values. And it is used in many fields, but we rarely do explain what they are. So, in this video, we'll discuss the three main types of probability distribution, that is normal, binomial, and Poisson distribution. So, let's move ahead.
So what is normal distribution? Normal distribution is a continuous probability density that has a probability density function which gives us a symmetrical bell curve. Now data can be distributed or spread out in different ways, but there are many cases where the data tends to be around a central value with no bias to the left or right, which means that it doesn't show any particular spikes towards the left or the right, and it gets close to a normal distribution. Half of the data will fall on the left of the mean and the other half will fall on the right. Now let's take a look at a graph which shows the height distribution in a class. As you can see, the average height is in the middle and the data to the left of the average height represents the short people and the data to the right of it represents the taller people. The y-axis shows us the likelihood of any of these heights occurring. The average height has the most distribution, or it has the most number of cases in the class, and as the height decreases or increases, the number of people who have that height also decreases. This kind of a distribution is called a normal distribution, where the average or the mean is always the highest point and any other point after that or before that is significantly lower. The resulting data gives us a bell curve, and as you can see, there is no abrupt bias or spike in the data anywhere except for the average height. So this kind of a curve is called a bell curve, and it's usually seen in a normal distribution. The reason we call this a normal distribution is because the data is normally distributed, with the average being the highest and all the other data points having a lower likelihood. Now we came across two terms which are associated with normal distribution: continuous probability density and probability density function. What is continuous probability density? Continuous probability density is a probability distribution where the random variable x can take any given value. Because there are infinite values that x could assume, the probability of x taking on any specific value is 0. For example, let's say you have a continuous probability density for men's height. What is the probability that a man will have the exact height of 70 inches? It is impossible to find this out, because the probability of one man measuring exactly 70 inches is very low. It is more probable that he will measure around 70.1 inches or maybe 69.97 inches. And it doesn't stop there. The fact is that it's impossible to exactly measure any variable that's on a continuous scale, and because of this it's impossible to figure out the probability of one exact measurement which is occurring in a continuous probability density. Next, we have the probability density function. It's nothing but a function or an expression which is used to define the range of values that a continuous random variable can take. An example of this would be to gauge the risk and reward of a stock. A probability density function is a statistical measure which is used to gauge the likelihood of a discrete value. A discrete variable can be measured exactly, while a continuous variable can have infinite values. However, for both continuous as well as discrete variables, we can define a function which gives us the range of values within which these variables will fall, and that function is known as the probability density function. Now let's take a look at standard deviation. What is standard deviation?
Standard deviation is used to measure how the values in your data differ from one another or how spread out your data is. A standard deviation is a statistic that measures the dispersion of a data set relative to its mean. The standard deviation is calculated as the square root of variance by determining each data point's deviation relative to the mean. If the data points are further from the mean, that means that there's a higher deviation within the data set, and then the data is said to be more spread out. This leads to a higher standard deviation too. Let's take an example of income in rural and urban areas. In rural areas, let's say such as farming areas, the income doesn't differ that much. More or less everyone earns the same. Because of this, our bell curve has a very low standard deviation and it has a very narrow peak. However, in urban areas, the wealth distribution is very uneven. Some people can have very high incomes and can be earning a lot, while other people can have very low incomes. Furthermore, the data distribution between these two income points is going to be more spread out because there are a lot more people living there who work in various fields and who have various incomes. Because of this, our standard deviation is more spread out and our bell curve will also have a wider peak. Now, how can we find the standard deviation? Standard deviation is obtained by subtracting each data value from the mean and finding the squared average of these values. Let's look at how we can do this with the help of an example. These values correspond to the height of various dogs. We can find the mean by finding the average of all these values, which is nothing but adding all the values and dividing it by the total number of values. The mean that we get is 394. This means that the average height of a dog is 394 millimeters. To find the standard deviation, first we need to subtract the height from the mean. This will tell us how far from the mean our data points actually are. Next, we will square up all of these differences and add them up and again divide it by the total number of values that we have. This is called the variance. The variance that we get in this case is 21704. Finally, when we find the square root of this value, we will get the standard deviation. The standard deviation here is 147. The standard deviation will tell us how our data points differ from the average. And it gives us a basic value suggesting how spread out our data is from the very middle or from the mean. So when we plot these values, this value 147 will mean that a curve will have a width of 147 points around the mean. Now, what is the standard normal distribution? The standard normal distribution is a type of normal distribution that has a mean of 0 and a standard deviation of 1. This means that the normal distribution has its center at 0 and it has intervals which increase by 1. All normal distributions, like the standard normal distribution, are unimodal and symmetrically distributed with a bell-shaped curve. However, a normal distribution can take on any value as its mean and standard deviation. In the standard normal distribution, however, the mean and standard deviation are always fixed. When you standardize a normal distribution, the mean becomes 0 and the standard deviation becomes 1. This allows you to easily calculate the probability of certain values occurring in your distribution or to compare data sets with different mean and standard deviations. The curve shows a standard normal distribution. As you can see, again, the data is centered at 0. This does not mean that the data necessarily starts at 0. This means that after standardizing, this point is where our mean will lie. In a standard normal distribution, the standard deviation is 1. So all the data points will increase or decrease in steps of 1. Let's better understand a standard normal distribution with the help of an example. Again, as you can see, the data is centered around 0, which is nothing but the mean. Let's again consider the weights of students in class 8th. The average weight here is around 50 kgs and the data increases and decreases in steps of 5. The data over here in this curve is evenly distributed along these steps. This is what a standard normal distribution will look like. We already know that the mean of our data is 50, and because the data is increasing and decreasing in equal steps, we can just standardize it and take it to mean that the data is increasing and decreasing in steps of 1. This is what a standard normal distribution looks like, and when you have a data which looks like this, you can always standardize it and convert it into a standard normal distribution. Now, standard normal distribution has a couple of properties which makes calculation comparatively easy. The first one is that 68% of the values fall within the first standard deviation, which means that 68% of all data values on this curve will fall between the range of -1 to 1, or the first interval ranging from -1 to 1. The second property is that 95% of the rest of the values are within the second standard deviation, or from the second negative point to the second positive point. And finally, 99.7% of the values fall within the third standard deviation, or from the third negative point to the third positive point. This makes calculations on standard normal distribution fairly easy. You can compare scores on different distributions with different means and standard deviations. You can normalize scores for statistical decision making using standard normal distribution. You can find the probability of observations in a distribution which fall above or below a given value. And finally, you can find the probability that a mean significantly differs from a population mean. Now let's take a look at z-score. So what is a z-score? A z-score is used to tell us how far from the mean our data point actually is. It is calculated using the mean and standard deviation, so it can be said that the z-score is how many standard deviations below the mean our data is. Basically, by using the z-score, we can get an approximate location of where our data point lies on the graph with regards to the mean. Now the z-score is given by subtracting the data point from the mean and dividing it by standard deviation. This can also be written as x minus mu divided by sigma. Now any normal distribution can be standardized by converting its values into z-scores. The z-score will tell you how many standard deviation from the mean each values lie. While data points are referred to as x in a normal distribution, they are called z or z-scores in the z distribution. A z-score is a standard score that will tell you how many standard deviations away from the mean an individual point will lie. A positive z-score will mean that your x value is greater than the mean, and a negative z-score will mean that your x value is less than the mean. A z-score of 0 will mean that your x value is equal to the mean. And again, to standardize a value from a normal distribution, all we have to do is convert it to a z-score by subtracting the mean from our individual value and dividing it by the standard deviation. Now let's see how we can find the z-score from data points with the help of a solved example. Let's do a case study. In this case study, we'll be taking the summary of daily travel time of a person who's commuting to and from work. All these values are in minutes. And using these values, we have to calculate the mean, the standard deviation, and the z-score. These values are as shown. As we can see, there are 13 values in total. Let's start by finding the mean. The mean is the average, and it can be gotten by adding all of these values and dividing it by the total number of values. This gives us a value of 38.6. The mean tells us the average of all our data points, which means on an average, he travels for 38.6 minutes to reach work. Next, let's subtract the individual values from our mean and calculate the variance and standard deviation. The values on the left give us the values that we get after subtracting it from the mean, and the variance can be calculated by squaring all of these values, adding up all of the squared values, and dividing it by the total number of values. At the end of the day, we get a variance of 140. To calculate the standard deviation, all we have to do is take a square root of the variance, which gives us a value of 11.8. Now, the mean signifies the average of our values, and we already know this. It gives us the average time which is taken to travel. But the standard deviation will tell us the average value of how much our data points differ from the mean. It tells us the deviation within our own data, and it tells us how far away on an average a point is from the mean. Now the value that we get is 11.8, which means that on an average A single data point is around 11.8 data points away from the mean. Now let's calculate the z-score. The z-score is given by subtracting individual data points from the mean and dividing it by the standard deviation. We know that we have a standard deviation of 11.8 and a mean of 38.6. Using these values, we can calculate the z-scores for individual x values. Now we know that a negative z-score means that our x value is lower than our mean. But what does the number 1.06 mean? This means that the z-score for 26 is 1.06 standard deviations away from the mean. The negative symbol here means that our x value is less than the mean. And by how less? 1.06 times the standard deviation. Now we know that the negative value of a z-score means that our x value is less than our mean. But what does the number 1.06 mean? This means that the z-score is 1.06 times the standard deviation less than the mean. The same thing can be said for the z-score of 33. It is 0.47 times the standard deviation less than the mean. The z-score of 65 is 2.23 times the standard deviation more than the mean. That means it has to be added to the mean. The reason that we know it's more than the mean is because this has a positive value. So this means that using z-scores, we can know where our data points fall relative to other points on the graph. The z-score will tell us how far away from the mean a point is in steps of our standard deviation.
Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails. And if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It either gives a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing x successes in n number of trials, with the probability of success on a single trial denoted by p. The binomial distribution assumes that p is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are four important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only 2, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not changes from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p to the power n minus r, where r is the number of success in n number of trials and p is the probability of success. 1 minus p denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here r is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace r with 1 and n will be 3. So px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute r equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent event at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per season.
You are an aspiring data scientist who is looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Hello everyone, welcome to another session by Simplilearn. Today, we are going to discuss the Bayes theorem, an important subtopic that comes under probability theory. We'll start this video by talking about probability and conditional probability. After that, we'll move on to the Bayes theorem and understand its formula and a real-life example where the Bayes theorem can be used. So, let's get started. What is probability? Probability is a branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking, 0 indicates the impossibility of the event and 1 indicates certainty. The higher the probability of an event, the more likely is that the event will occur. Let's look at an example. A simple example is the tossing of a fair unbiased coin. Since the coin is fair, the outcome, that is heads and the tails, are both equally probable. The probability of heads equals the probability of the tails, and since no other outcomes are possible, the probability of either heads or tails can be said to be 1 by 2, which is also 50%. The probability of an event can be calculated by number of ways it can happen divided by the total number of outcomes. Now that we know about the probability, let's see if you can answer this question. What is the probability of drawing a jack and a queen consecutively from a deck of 52 cards without replacement? Here are your options. Post your answers in the comment section and let us know. Now let's move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred and probability of B is not equal to 0 is called the conditional probability. It is denoted by PA/B. Thus, we can say that PA/B is equal to PA intersection B divided by P of B, where PA/B is the probability of occurrence of A given that B has already occurred, and PB is the probability of occurrence of B. To know more about conditional probability, you can check our previous video which is specifically on conditional probability. Now let's move on to Bayes' theorem. The Bayes' theorem is a mathematical formula for calculating conditional probability in probability and statistics. In other words, it is used to figure out how likely an event is associated on its proximity to another. Bayes' law or Bayes' rule are the other names of this theorem. The formula for the Bayes' theorem can be written in a variety of ways. The most common version is PA/B is equal to P of B/A into P of A divided by P of B, where PA/B is the conditional probability of event A occurring given that B is true, and P, A and P of B are the probabilities of A and B occurring independently of one another. Let's solve a problem using the Bayes' theorem to understand it better. There is a cricket match tomorrow, and in recent years it has rained only 5 days each year. Unfortunately, the meteorologist has predicted the rain for tomorrow. Now, when it rains, the meteorologist correctly forecasts rain 90% of the time, and when it doesn't rain, he incorrectly forecasts rain 10% of the time. Let's calculate what is the probability that it will rain on the match day. So, the two sample spaces here are the events that it rains and it does not rain. Additionally, a third event is also there that meteorologist predicts the rain. So the notation for these events appear below. Event A1 is equal to it rains on the match day, event A2 that it does not rain on the match day, and event B is the meteorologist predicting the rain. Now in terms of probability, we know the following. Probability of A1 is 5 by 365 that it rains 5 days in a year, which will come out to be 0.0136. PA2 is 360 by 365, that is no days for 360 days in a year, which will come out to be 0.986. PB/A1 is 0.9. This signifies when it rains, the meteorologist predicts the rain 90% of the time. In a similar manner, PB/A2 is 0.1, that it does not rain, the meteorologist predicts the rain 10% of the time. Combining all this, we can calculate PA1/B, that is the probability it will rain on the given match day, given a forecast of rain by meteorologist. The answer can be determined using the Bayes' theorem as shown below. So here's the formula of the Bayes' theorem, and putting all the values that we have calculated in the previous slide, the probability that it will rain on the match day given a forecast of the rain by meteorologist will come out to be 0.111, which will be equal to 11.11%. So there's an 11% chance that it will rain on the match day given that the meteorologist has predicted the rain. I hope this example is clear to you.
It's a weekend, and John decided to watch the latest movie recommended by Netflix at his friend's place. Before heading out, he asked Siri about the weather and realized it would rain. So he decided to take his Tesla for the long journey and switch to autopilot on the highway. After coming home from the eventful day, he started wondering how technology has made his life easy. He did some research on the internet and found out that Netflix, Siri, and Tesla are all using AI. So, what is AI? AI, or artificial intelligence, is nothing but making computers-based machines think and act like humans. Artificial intelligence is not a new term. John McCarthy, a computer scientist, coined the term artificial intelligence back in 1956, but it took time to evolve as it demanded heavy computing power. Artificial intelligence is not confined to just movie recommendations and virtual assistants. Broadly classifying, there are three types of AI. Artificial narrow intelligence, also called weak AI, is the stage where machines can perform a specific task. Netflix, Siri, chatbots, facial recommendation systems are all examples of artificial narrow intelligence. Next up, we have artificial general intelligence, referred to as an intelligent agent's capacity to comprehend or pick up any intellectual skill that a human can. We are halfway into successfully implementing this phase. IBM's Watson supercomputer and GPT-3 fall under this category. And lastly, artificial superintelligence. It is the stage where machines surpass human intelligence. You might have seen this in movies and imagined how the world would be if machines occupied it. Fascinated by this, John did more research and found out that machine learning, deep learning, and natural language processing are all connected with artificial intelligence. Machine learning, a subset of AI, is the process of automating and enhancing how computers learn from their experiences without human help. Machine learning can be used in email spam detection, medical diagnosis, etc. Deep learning can be considered a subset of machine learning. It is a field that is based on learning and improving on its own by examining computer algorithms. While machine learning uses simpler concepts, deep learning works with artificial neural networks, which are designed to imitate the human brain. This technology can be applied in face recognition, speech recognition, and many more applications. Natural language processing, popularly known as NLP, can be defined as the ability of machines to learn human language and translate it. Chatbots fall under this category. Artificial intelligence is advancing in every crucial field like healthcare, education, robotics, banking, e-commerce, and the list goes on. Like in healthcare, AI is used to identify diseases, helping healthcare service providers and their patients make better treatment and lifestyle decisions. Coming to the education sector, AI is helping teachers automate grading, organizing, and facilitating parent-guardian conversations. In robotics, AI-powered robots employ real-time updates to detect obstructions in their path and instantaneously design their routes. Artificial intelligence provides advanced data analytics that is transforming banking by reducing fraud and enhancing compliance. With this growing demand for AI, more and more industries are looking for AI engineers who can help them develop intelligent systems and offer them lucrative salaries going north of $120,000. The future of AI looks promising, with the AI market expected to reach $190 billion by 2025.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify song A. But when the choice became complicated, as in the case of song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for song B, if we draw a circle around the song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Let's dive in a little deeper and see how machine learning works. Let's say you provide a system with the input data that carries the photos of various kinds of fruits. Now you want the system to figure out what are the different fruits and group them accordingly. So what the system does, it analyzes the input data. Then it tries to find patterns like shapes, size, and color. Based on these patterns, the system will try to predict the different types of fruit and segregate them. Finally, it keeps track of all such decisions it took in the process to make sure it's learning. The next time you ask the same system to predict and segregate the different types of fruits, it won't have to go through the entire process again. That's how machine learning works. Now let's look into the types of machine learning. Machine learning is primarily of three types. First one is supervised machine learning. As the name suggests, you have to supervise your machine learning while you train it to work on its own. It requires labeled training data. Next up is unsupervised learning, wherein there will be training data but it won't be labeled. Finally, there is reinforcement learning, wherein the system learns on its own. Let's talk about all these types in detail. Let's try to understand how supervised learning works. Look at the pictures very carefully. The monitor depicts the model or the system that we are going to train. This is how the training is done. We provide a data set that contains pictures of a kind of a fruit, say an apple. Then we provide another data set which lets the model know that these pictures were that of a fruit called apple. This ends the training phase. Now, what we will do is we provide a new set of data which only contains pictures of apple. Now here comes the fun part. The system can actually tell you what fruit it is. And it will remember this and apply this knowledge in future as well. That's how supervised learning works. You are training the model to do a certain kind of an operation on its own. This kind of a model is generally used into filtering spam mails from your email accounts as well. Yes, surprised, aren't you? So let's move on to unsupervised learning now. Let's say we have a data set which is cluttered. In this case, we have a collection of pictures of different fruits. We feed this data to the model and the model analyzes the data to figure out patterns in it. In the end, it categorizes the photos into three types, as you can see in the image, based on their similarities. So, you provide the data to the system and let the system do the rest of the work. Simple, isn't it? This kind of a model is used by Flipkart to figure out the products that are well suited for you. Honestly speaking, this is my favorite type of machine learning out of all the three. And this type has been widely shown in most of the sci-fi movies lately. Let's find out how it works. Imagine a newborn baby. You put a burning candle in front of the baby. The baby does not know that if it touches the flame, its fingers might get burned. So it does that anyway and gets hurt. The next time you put that candle in front of the baby, it will remember what happened the last time and would not repeat what it did. That's exactly how reinforcement learning works. We provide the machine with a data set wherein we ask it to identify a particular kind of a fruit, in this case an apple. So what it does as a response, it tells us that it's a mango. But As we all know, it's a completely wrong answer. So as a feedback, we tell the system that it's wrong, it's not a mango, it's an apple. What it does, it learns from the feedback and keeps that in mind. When the next time when we ask a same question, it gives us the right answer. It is able to tell us that it's actually an apple. That is a reinforced response. So that's how reinforcement learning works. It learns from its mistakes and experiences. This model is used in games like Prince of Persia or Assassin's Creed or FIFA, wherein the level of difficulty increases as you get better with the games. Just to make it more clear for you, let's look at a comparison between supervised and unsupervised learning. Firstly, the data involved in case of supervised learning is labeled. As we mentioned in the examples previously, we provide the system with a photo of an apple and let the system know that this is actually an apple. That is called labeled data. So the system learns from the labeled data and makes future predictions. Now, unsupervised learning does not require any kind of labeled data because its work is to look for patterns in the input data and organize it. The next point is that you get a feedback in case of supervised learning. That is, once you get the output, the system tends to remember that and uses it for the next operation. That does not happen for unsupervised learning. And the last point is that supervised learning is mostly used to predict data, whereas unsupervised learning is used to find out hidden patterns or structures in data. I think this would have made a lot of things clear for you regarding supervised and unsupervised learning. Now, let's talk about a question that everyone needs to answer before building a machine learning model. What kind of a machine learning solution should we use? Yes, you should be very careful with selecting the right kind of solution for your model. Because if you don't, you might end up losing a lot of time, energy, and processing cost. I won't be naming the actual solutions because you guys aren't familiar with them yet. So we will be looking at it based on supervised, unsupervised, and reinforcement learning. So let's look into the factors that might help us select the right kind of machine learning solution. First factor is the problem statement describes the kind of model you will be building, or as the name suggests, it tells you what the problem is. For example, let's say the problem is to predict the future stock market prices. So for anyone who is new to machine learning would have trouble figuring out the right solution. But with time and practice, you will understand that for a problem statement like this, solution based on supervised learning would work the best for obvious reasons. Then comes the size, quality, and nature of the data. If the data is cluttered, you go for unsupervised. If the data is very large and categorical, we normally go for supervised learning solutions. Finally, we choose a solution based on their complexity. As for the problem statement wherein we predict the stock market prices, it can also be solved by using reinforcement learning. But that would be very, very difficult and time consuming, unlike supervised learning. Algorithms are not types of machine learning. In the most simplest language, they are methods of solving a particular problem. So the first kind of method is classification, which falls under supervised learning. Classification is used when the output you are looking for is a yes or a no, or in the form A or B, or true or false. Like if a shopkeeper wants to predict if a particular customer will come back to his shop or not, he will use a classification algorithm. The algorithms that fall under classification are decision tree, naive Bayes, random forest, logistic regression, and KNN. The next kind is regression. This kind of a method is used when the predicted data is numerical in nature. Like if the shopkeeper wants to predict the price of a product based on its demand, it would go for regression. The last method is clustering. Clustering is a kind of unsupervised learning again. It is used when the data needs to be organized. Most of the recommendation systems used by Flipkart, Amazon, etc. make use of clustering. Another major application of it is in search engines. The search engines study your old search history to figure out your preferences and provide you the best search results. One of the algorithms that fall under clustering is K-means. Now that we know the various algorithms, let's look into 4 key algorithms that are used widely. We will understand them with very simple examples. The 4 algorithms that we will try to understand are K-nearest neighbor, linear regression, decision tree, and naive Bayes. Let's start with our first machine learning solution, K nearest neighbor. K nearest neighbor is again a kind of a classification algorithm. As you can see on the screen, the similar data points form clusters. The blue one, the red one, and the green one. There are 3 different clusters. Now if we get a new and unknown data point, it is classified based on the cluster closest to it or the most similar to it. K in KNN is the number of nearest neighboring data points we wish to compare the unknown data with. Let's make it clear with an example. Let's say we have 3 clusters in a cost to durability graph. First cluster is of footballs, the second one is of tennis balls, and the third one is of basketballs. From the graph, we can say that the cost of footballs is high and the durability is less. The cost of tennis balls is very less, but the durability is high. And the cost of basketballs is as high as the durability. Now let's say we have an unknown data point. We have a black spot which can be one kind of the balls, but we don't know what kind it is. So what we'll do, we'll try to classify this using KNN. So if we take K is equal to 5, we draw a circle keeping the unknown data point as the center, and we make sure that we have 5 balls inside that circle. In this case, we have a football, a basketball, and 3 tennis balls. Now since we have the highest number of tennis balls inside the circle, the classified ball would be a tennis ball. So that's how K nearest neighbor classification is done. Linear regression is again a type of supervised learning algorithm. This algorithm is used to establish linear relationship between variables, one of which would be dependent and the other one would be independent. Like if we want to predict the weight of a person based on his height, weight would be the dependent variable and height would be independent. Let's have a look at it through an example. Let's say we have a graph here showing a relationship between height and weight of a person. Let's put the y-axis as age and the x-axis as weight. So the green dots are the various data points. These green dots are the data points. And D is the mean squared error, that is the perpendicular distances from the line to the data points are the error values. This error tells us how much the predicted values vary from the original value. Let's ignore this blue line for a while. So let's say if this is our regression line, you can see the distance from all the data points from this line is very high. So if we take this line as a regression line, the error in the prediction will be too high. So in this case, the model will not be able to give us a good prediction. Let's say we draw another regression line here like this. Even in this case, you can see that the perpendicular distance of the data points from the line is very high. So the error value will still come as high as the last one. So this model will also not be able to give us a good prediction. So what to do? So finally, we draw a line which is this blue line. So here we can see that the distance of the data points from the line is very less relative to the other 2 lines we drew. So the value of D for this line will be very less. So in this case, if we take any value on the x-axis, the corresponding value on the y-axis will be our prediction. And given the fact that the D is very low, our prediction should be good also. This is how regression works. We draw a line, a regression line that is, in such a way that the value of D is the least, eventually giving us good predictions. This algorithm, that is decision tree, is a kind of an algorithm you can very strongly relate to. It uses a kind of a branching method to realize the problem and make decisions based on the conditions. Let's take this graph as an example. Imagine yourself sitting at home getting bored. You feel like going for a swim. What you do is you check if it's sunny outside. So that's your first condition. If the answer to that condition is yes, you go for a swim. If it's not sunny, then the next question you would ask yourself is if it's raining outside. So that's condition number 2. If it's actually raining, you cancel the plan and stay indoors. If it's not raining, then you would probably go outside and have a walk. So that's the final node. That's how decision tree algorithm works. You probably use this every day. It realizes a problem and then takes the decisions based on the answers to every conditions. Naive-Bayes algorithm is mostly used in cases where a prediction needs to be done on a very large dataset. It makes use of conditional probability. Conditional probability is the probability of an event, say A, happening given that another event B has already happened. This algorithm is most commonly used in filtering spam mails in your email account. Let's say you receive a mail. The model goes through your old spam mail records. Then it uses Bayes' theorem to predict if the present mail is a spam mail or not. So PC of A is the probability of event C occurring when A has already occurred. PA of C is the probability of event A occurring when C has already occurred. And PC is the probability of event C occurring, and PA is the probability of event A occurring. Let's try to understand Naive-Bayes with a better example. Naive-Bayes can be used to determine on which days to play cricket. Based on the probabilities of a day being rainy, windy, or sunny, the model tells us if a match is possible. If we consider all the weather conditions to be event A for us, and the probability of a match being possible event C, so the model applies the probabilities of event A and C into the Bayes theorem and predicts if a game of cricket is possible on a particular day or not. In this case, if the probability of C of A is more than 0.5, we can be able to play a game of cricket. If it's less than 0.5, we won't be able to do that. That's how Naive-Bayes algorithm works.
We're going to cover reinforcement learning today. And what's in it for you? We'll start with why reinforcement learning. We'll look at what is reinforcement learning. We'll see what the different kinds of learning strategies are that are being used today in computer models under supervised versus unsupervised versus reinforcement. We'll cover important terms specific to reinforcement learning. We'll talk about Markov's decision process, and we'll take a look at a reinforcement learning example. Well, we'll teach a tic-tac-toe how to play. Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And you can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used. No supervision. Follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works, and this is my reward. Doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options, and we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs, so if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3, it just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game Certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment, and suddenly a reward system like this is going to be just is going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that, as far as weighing. You add weights to it, and so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like, if you take a certain path, the first reward is going to be weighed a little bit less than the last reward, because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning, because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess. I think was a big one, where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is, when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state. This is class player. And when we say class player, we're not talking about a human player. We're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it? as you try different moves, it gets to the end. The first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position. And then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through. So it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2. Probably should have done ABC. This has a step 3. Step 4, and so on until you get to step N, and this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self set up on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here. And feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces. And the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go. And it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here, and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. And you can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3 by 3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. So you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action. There we go. Boom. So you can see here we've got didn't catch the win on this. It said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
Supervised learning uses labeled data to train machine learning models. Labeled data means that the output is already known to you. The model just needs to map the inputs to the outputs. An example of supervised learning can be to train a machine that identifies the image of an animal. Below you can see we have our trained model that identifies the picture of a cat. Unsupervised learning uses unlabeled data to train machines. Unlabeled data means there is no fixed output variable. The model learns from the data, discovers patterns and features in the data, and returns the output. Here is an example of an unsupervised learning technique that uses the images of vehicles to classify if it's a bus or a truck. So the model learns by identifying the parts of a vehicle, such as the length and width of the vehicle, the front and rear end covers, roof hoods, the types of wheels used, etc. Based on these features, the model classifies if the vehicle is a bus or a truck. Reinforcement learning trains a machine to take suitable actions and maximize reward in a particular situation. It uses an agent and an environment to produce actions and rewards. The agent has a start and an end state, but there might be different paths for reaching the end state, like a maze. In this learning technique, there is no predefined target variable. An example of reinforcement learning is to train a machine that can identify the shape of an object given a list of different objects such as square, triangle, rectangle, or a circle. In the example shown, the model tries to predict the shape of the object, which is a square here. Now, let's look at the different machine learning algorithms that come under these learning techniques. Some of the commonly used supervised learning algorithms are linear regression, logistic regression, support vector machines, k-nearest neighbors, decision tree, random forest, and naive Bayes. Examples of unsupervised learning algorithms are k-means clustering, hierarchical clustering, db-scan, principal component analysis, and others. Choosing the right algorithm depends on the type of problem you are trying to solve. Some of the important reinforcement learning algorithms are Q-learning, Monte Carlo, SARSA, and Deep Q network. Now let's look at the approach in which these machine learning techniques work. So supervised learning takes labeled inputs and maps it to known outputs, which means you already know the target variable. Unsupervised learning finds patterns and understands the trends in the data to discover the output. So the model tries to label the data based on the features of the input data. While reinforcement learning follows trial and error method to get the desired solution. After accomplishing a task, the agent receives an award. An example could be to train a dog to catch the ball. If the dog learns to catch a ball, you give it a reward such as a biscuit. Now, let's discuss the training process for each of these learning methods. So supervised learning methods need external supervision to train machine learning models, and hence the name supervised. They need guidance and additional information to return the result. Unsupervised learning techniques do not need any supervision to train models. They learn on their own and predict the output. Similarly, reinforcement learning methods do not need any supervision to train machine learning models. And with that, let's focus on the types of problems that can be solved using these three types of machine learning techniques. So supervised learning is generally used for classification and regression problems. We'll see the examples in the next slide. And unsupervised learning is used for clustering and association problems, while reinforcement learning is reward-based. So for every task or for every step completed, there will be a reward received by the agent. And if the task is not achieved correctly, there will be some penalty used. Now, let's look at a few applications of supervised, unsupervised, and reinforcement learning. As we saw earlier, supervised learning are used to solve classification and regression problems. For example, you can predict the weather for a particular day based on humidity, precipitation, wind speed, and pressure values. You can use supervised learning algorithms to forecast sales for the next month or the next quarter for different products. Similarly, you can use it for stock price analysis or identifying if a cancer cell is malignant or benign. Now, talking about the applications of unsupervised learning, we have customer segmentation. So based on customer behavior, likes, dislikes, and interests, you can segment and cluster similar customers into a group. Another example where unsupervised learning algorithms are used is customer churn analysis. Now, let's see what applications we have in reinforcement learning. So reinforcement learning algorithms are widely used in the gaming industries to build games. It is also used to train robots to perform human tasks.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Often, professionals want to know if there is a relationship between two or more variables. For instance, is there a relationship between the grade on the third French exam a student takes and the grade on the final exam? If yes, then how is it related and how strongly? Regression can be used here to arrive at a conclusion. This is an example of bivariate data, that is, two variables. However, statisticians are mostly interested in multivariate data. Regression analysis is used to predict the value of one variable, the dependent variable, on the basis of other variables, the independent variables. In the simplest form of regression, linear regression, you work with one independent variable. The formula for simple linear regression is shown on the screen. In the next screen, we'll look at a few examples of regression analysis. Regression analysis is used in several situations, such as those described on the screen. In example 1, using the data given on the screen, you have to analyze the relation between the size of a house and its selling price for a realtor. In example 2, you need to predict the exam scores of students who study for 7.2 hours with the help of the data shown on the slide. A couple more examples are given on the screen. In example 3, based on the expected number of customers and the previous day's data given, you need to predict the number of burgers that will be sold by a KFC outlet. In example 4, you have to calculate the life expectancy for a group of people with the average length of schooling based on the data given. Let's look at the two main types of regression analysis, simple linear regression and multiple linear regression. Both of these statistical methods use a linear equation to model the relationship between two or more variables. Simple linear regression considers one quantitative and independent variable x to predict the other quantitative but dependent variable y. Multiple linear regression considers more than one quantitative and qualitative variable to predict a quantitative and dependent variable y. We'll look at the two types of analyses in more detail in the slides that follow. In simple linear regression, the predictions of the explained variable y, when plotted as a function of the explanatory variable x from a straight line. The best fitting line is called the regression line. The output of this model is a function to predict the dependent variable on the basis of the values of the independent variable. The dependent variable is continuous, and the independent variable can be continuous or discrete. Let's look at the different kinds of linear and nonlinear analyses. List of linear techniques are simple, method of least squares, coefficient of multiple determination, standard error of the estimate, dummy variable, and interaction. Similarly, there are many nonlinear techniques available, such as polynomial, logarithmic, square root, reciprocal, and exponential. To understand this model, we'll first look at a few assumptions. The simple linear regression model depicts the relationship between one dependent and two or more independent variables. The assumptions which justify the use of this model are as follows. Linear and additive relationship between the dependent and independent variables. Multivariate normality. Little or no collinearity in the data. Little or no autocorrelation in the data. Homoscedasticity, that is, variance of errors same across all values of x. The equation for this model is shown on the screen. A more descriptive graphical representation of simple linear regression is given on the screen. Beta naught represents the slope. A slope with two variables implies that 1 unit changes in x result in a 2-unit change in y. Beta 1 represents the estimated change in the average value of y as a result of 1 unit change in x. Epsilon represents the estimated average value of y when the value of x is 0. This demo will show the steps to do simple linear regression in R. In this demo, you'll learn how to do simple linear regression. Let's use x and y vectors that we have created in the previous demo. We also ensured there exists a relationship between x and y visually by plotting a graph. To build a simple linear regression model, let's use the LM function. To see how the linear model fits into x and y, let's plot the linear line by the AB line function. Let's use the predict function to test or predict the linear model. We can pass a known variable to predict the unknown variables.
Let's look at an example of a common use for linear regression, profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. What's in it for you? First, we'll have an introduction to machine learning, followed by machine learning algorithms. These will be specific to linear regression and where it fits into the larger model. Then we'll take a look at applications of linear regression, understanding linear regression, and multiple linear regression. Finally, we'll roll up our sleeves and do a little programming in use case profit estimation of companies. Let's go ahead and jump in. Let's start with our introduction to machine learning, along with some machine learning algorithms and where that fits in with linear regression. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum is equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from is called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66, and take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your C coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So, the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that and we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there, and let's walk through what libraries we're importing. First, we're going to import NumPy as NP, and then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlib and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlib inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any two of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in two steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder. which equals one hot encoder categorical features equals 3. And then we take the x and we go ahead and do that equal to one hot encoder fit transform x to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print x and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have x equals x colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take y. We've already created those. X has the columns with the data in it, and y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines. And then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do x train and y train because we're using the training data. X being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y predict variable. and we're going to put in the X test. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have y predict equals regressor dot predict X test going in, and this gives us y predict. Now because I'm in Jupyter Inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. We can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our Y test versus our Y predict. Y test is the actual values we're testing. That was the one that was given to us so we know are true. The Y predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. So now that we have a successful linear regression model, let's take a look at what we went over today and take a look at our key takeaways. First,
if you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
What is logistic regression? Let's say we have to build a predictive model or a machine learning model to predict whether the passengers of the Titanic ship have survived or not, the shipwreck. So how do we do that? So we use logistic regression to build a model for this. How do we use logistic regression? So we have the information about the passengers, their ID, whether they have survived or not, their class and name and so on and so forth. And we use this information where we already know whether the person has survived or not. That is the labeled information. And we help the system to train based on this information, based on this labeled data. This is known as labeled data. And during the process of building the model, we probably will remove some of the non-essential parameters or attributes here. We only take those attributes which are really required to make these predictions. And once we train the model, we run new data through it, whereby the model will predict whether the passenger has survived or not. So let's see what we will learn in this video. We will talk about what is supervised learning, and we will go into details about classification, which is one of the techniques for supervised learning. And then we will further focus on logistic regression, which is one of the algorithms for performing classification, especially binary classification. Then we will compare linear and logistic regression and what are some of the logistic regression applications. And finally, we will end with a use case or a demo of actual Python code for doing logistic regression in Jupyter Notebook. Alright, so let's start with what is supervised learning. Supervised learning is one of the two main types of machine learning methods. Here we use what is known as labeled data to help the system learn. This is very similar to how we human beings learn. So let's say you want to teach a child to recognize an apple. How do we do that? We never tell the child, okay, this is an apple has a certain diameter on the top, a certain diameter at the bottom, and this has a certain RGB color. No, we just show an apple to the child and tell the child this is apple. And then next time when we show an apple, child immediately recognizes, yes, this is an apple. Supervised learning works very similar on the similar lines. So where does logistic regression fit into the overall machine learning process? Machine learning is divided into two types, mainly two types. There is a third one called reinforcement learning, but we will not talk about that right now. So one is supervised learning and the other is unsupervised learning. Unsupervised learning uses techniques like clustering and association, and supervised learning uses techniques like classification and regression. Now, supervised learning is used when you have labeled data. You have historical data, then you use supervised learning. When you don't have labeled data, then you used unsupervised learning. In supervised learning, there are two types of techniques that are used, classification and regression, based on what is the kind of problem we are solving. Let's say we want to take the data and classify it. It could be binary classification, like a 0 or a 1. An example of classification we have just seen, whether the passenger has survived or not survived. It's like a 0 or 1. That is known as binary classification. Regression, on the other hand, is you need to predict a value, what is known as a continuous value. Classification is for discrete values. Regression is for continuous values. Let's say you want to predict a share price, or you want to predict the temperature that will be there. What will be the temperature tomorrow? That is where you use regression. Whereas classification are discrete values. Will the customer buy the product or will not buy the product? Will you get a promotion or you will not get a promotion? I hope you're getting the idea. Or it could be multi-class classification as well. Let's say you want to build an image classification model. So the image classification model would take an image as an input and classify into multiple classes, whether this image is of a cat or a dog or an elephant or a tiger. So there are multiple classes, so not necessarily binary classification. So that is known as multi-class classification. So we are going to focus on classification because logistic regression is one of the algorithms used for classification. Now, the name may be a little confusing. In fact, whenever people come across logistic regression, it always causes confusion because the name has regression in it, but we are actually using this for performing classification. Okay, so yes, it is logistic regression, but it is used for classification. And in case you are wondering, is there something similar for regression? Yes, for regression we have linear regression. Keep that in mind. So linear regression is used for regression. Logistic regression is used for classification. So in this video, we are going to focus on supervised learning, and within supervised learning, we are going to focus on classification, and then within classification, we are going to focus on logistic regression algorithm. So first of all, classification. So what are the various algorithms available for performing classification? The first one is decision tree. There are of course multiple algorithms, but here we will talk about a few. Decision trees are quite popular and very easy to understand, and therefore they are used for classification. Then we have k-nearest neighbors. This is another algorithm for performing classification. And then there is logistic regression. And this is what we are going to focus on in this video. And we are going to go into a little bit of details about logistic regression. Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the X and Y axis. X is the number of years since the last service was performed, and Y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along X and Y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the Y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the height. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you are trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion, that is a no, and this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between. And what is the employee's rating? Okay, and ratings can be continuous, that is not an issue. But the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix. the heat map and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. All right. So what is a confusion matrix? This is an example of a confusion matrix. And this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's a gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, all right, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x underscore train and y underscore train for the training data set. And what is x underscore train? These are the features, right, which is like the independent variable, and y underscore train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x underscore train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x underscore train, y underscore train is for the training data set, x underscore test, y underscore test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of this. So x underscore train, the shape is 1383 by 64, and y underscore train has 1383 because there is nothing like the second part is not required here. And then x underscore test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this. In this case, the data is not large, but by and large, the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose, we use the fit method. There is a method called fit, which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is, or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So we have, so this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less, and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, The diagonals again are all the values are here, most of the values, so which means reasonably, this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0, actual value is of course 0. Then this is the image of 9, so this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
So we put them side by side. We have our linear regression, which is a predictive number used to predict a dependent output variable based on independent input variable. Accuracy is measured using least squares estimation. So that's where you take, you could also use absolute value. The least squares is more popular. There's reasons for that mathematically and also for computer runtime. But it does give you an accuracy based on the least square estimation. The best fit line is a straight line, and clearly that's not always used in all the regression models. There's a lot of variations on that. The output is a predicted integer value. Again, this is what we're talking about when we talk about linear regression. And we're talking about regression, it means the number's coming out. Linear usually means we're looking for that line versus a different model. And it's used in business domain, forecasting stocks. It's used as a basis of most predictions with numbers. So if you're looking at a lot of numbers, you're probably looking at a linear regression model. For instance, if you do just the high lows of the stock exchange, and you're going to take a lot more of that if you want to make money off the stock, you'll find that the linear regression model fits probably better than almost any of the other models, even high-end neural networks and all these other different machine learning and AI models, because they're numbers. They're just a straight set of numbers. You have a high value, a low value, volume, that kind of thing. So when you're looking at something that's straight numbers and are connected in that way, usually you're talking about a linear regression model, and that's where you want to start. A logistic regression model used to classify dependent output variable based on independent input variable. So just like the linear regression model and like all of our machine learning tools, you have your features coming in. And so in this case you might have label, an image or something like that is probably the very popular thing right now, labeling broccoli and vegetables or whatever. Accuracy is measured using maximum likelihood estimation. The best fit is given by a curve. And we saw that when we're talking about linear regression, you definitely are talking about a straight line, although there is other regression models that don't use straight lines. And usually when you're looking at a logistic regression, the math, as you saw, was still kind of a Euclidean line, but it's now got that sigmoid activation, which turns it into a heavily weighted curve. And the output is a binary value between 0 and 1. And it's used for classification. Image processing, as I mentioned, is what people usually think of, although they use it for classification of like a window of things. So you could take a window of stock history and you could generate classifications based on that and separate the data that way. If it's going to be that this particular pattern occurs, it's going to be upward trending or downward trending. In fact, a number of stock traders use that not to tell them how much to bid or what to bid, but they use it as to whether it's worth looking at the stock or not, whether the stock's going to go down or go up. And it's just a 0 or 1. Do I care? Do I even want to look at it? So let's do a demo so you can get a picture of what this looks like in Python code. Let's predict the price at which insurance should be sold to a particular customer based on their medical history. We will also classify on a mushroom dataset to find the poisonous and non-poisonous mushrooms. And when you look at these two datas, the first one, we're looking at the price. So the price is a number. So let's predict the price which the insurance should be sold to. And the second one is we're looking at either it's poisonous or it's not poisonous. So first off, before we begin the demo, I'm in the Anaconda Navigator. In this one, I've loaded the Python 3.6 and using the Jupyter Notebook. And you can use Jupyter Notebook by itself. You can use the Jupyter Lab, which allows multiple tabs. It's basically the notebook with tabs on it. But the Jupyter Notebook is just fine, and it'll go into Google Chrome, which is what I'm using for my Internet Explorer. And from here we open up New, and you'll see Python 3. And again, this is loaded with Python 3.6. And we're doing the linear versus logic regression, or logit. You'll see L-O-G-I-T is one of the names that kind of pops up when you do a search on here. But it is a logic. We're looking at the logistic regression models. And we'll start with the linear regression because it's easy to understand. You draw a line through stuff. And so in programming, we got a lot of stuff to unfold here in our startup as we preload all of our different parts. And let's go ahead and break this up. We have at the beginning import pandas. So this is our data frame. It's just a way of storing the data. Think of when you talk about a data frame, think of a spreadsheet. You have rows and columns. It's a nice way of viewing the data. And then we have, we're going to be bringing in our pre-processing label encoder. I'll show you what that is. When we get down to it, it's easier to see in the data, but there's some data in here like sex. It's male or female, so it's not like an actual number. It's either you're one or the other. That kind of stuff ends up being encoded. That's what this label encoder is right here. We have our test split model. If you're going to build a model, you do not want to use all the data. You want to use some of the data and then test it to see how good it is. And if it can't have seen the data you're testing on until you're ready to test it on there and see how good it is. And then we have our logistic regression model, our categorical one, and then we have our linear regression model. These are the two, these right here. Let me just clear all that. There we go. These two right here are what this is all about. Logistic versus linear. Is it categorical? Are we looking for a true false, or are we looking for a specific number? And then finally, usually at the very end, we have to take and just ask how accurate is our model. Did it work? If you're trying to predict something, in this case we're going to be doing insurance costs. How close to the insurance cost does it measure that we expect it to be? You know, if you're an insurance company, you don't want to promise to pay everybody's medical bill and not be able to. And in the case of the mushrooms, you probably want to know just how much at risk you are for following this model as far as whether you're going to eat a poisonous mushroom and die or not. So we'll look at both of those, and we'll talk a little bit more about the shortcomings and the value of these different processes. So let's go ahead and run this. This is loaded the data set on here, and then because we're in Jupyter Notebook, I don't have to put the print on there. We just do data set, and it prints out all the different data on here, and you can see here for our insurance, because that's what we're starting with, we're loading that with our pandas, and it prints it in a nice format where you can see the age, sex, body mass index, number of children, smoker. So this might be something that the insurance company gets from the doctor. It says, hey, this is what we need to know to give you a quote for what we're going to charge you for your insurance. And you can see that it has 1,338 rows and 7 columns. You can count the columns, 1, 2, 3, 4, 5, 6, 7. So there's 7 columns on here. And the column we're really interested in is charges. I want to know what the charges are going to be. What can I expect? Not a very good arrow drawn. What to expect them to charge on there. So is this going to be, is this person going to cost me $16,884, or is this person only going to cost me $3,866? How do we guess that so that we can guess what the minimal charge is for their insurance? And then there's one other thing you really need to notice on this data. And I mentioned it before, but I'm going to mention it again because pre-processing data is so much of the work in data science. Sex. Well, how do you deal with female versus male? Are you a smoker? Yes or no? What does that mean? Region. How do you look at region? It's not a number. How do you draw a line between southwest and northwest? They're objects. It's either your southwest or your northwest. It's not like I'm southwest. I guess you could do longitude and latitude, but the data doesn't come in like that. It comes in as true, false, or whatever. It's either your southwest or your northwest. So we need to do a little bit of pre-processing of the data on here to make this work. Oops, there we go. Okay, so let's take a look and see what we're doing with pre-processing. And again, this is really where you spend a lot of time with data science, is trying to understand how and why you need to do that. And so we're going to do, you'll see right up here, label. And then we're going to do a label encoder, one of the modules we brought in. So this is sklearn's label encoder. I like the fact that it's all pretty much automated, but if you're doing a lot of work with the label encoder, you should start to understand how that fits. And then we have label.fit right here, where we're going to go ahead and do the dataset .sex.drop duplicates. And then for dataset sex, we're going to do the label transform the dataset sex. And so we're looking right here at male or female. And so it usually just converts it to a 0 or 1 because there's only 2 choices on here. Same thing with the smoker. It's 0 or 1, so we're going to change the smoker 0 or 1 on this. And then finally we did region down here. Region does it a little bit different. We'll take a look at that. And I think in this case it's probably going to do it because we did it on this label transform. With this particular setup, it gives each region a number, like 0, 1, 2, 3. So let's go ahead and take a look and see what that looks like. Go and run this. And you can see that our new data set has age, that's still a number. Sex is 0 or 1. So 0 is female, 1 is male. Number of children, we left that alone. Smoker, 1 or 0. It says no or yes on there. We actually just do 1 for no, 0 or no. Yeah, 1 for no. I'm not sure how it organized them, but it turns the smoker into 0 or 1, yes or no. And then region, it did this as 0, 1, 2, 3. So it's 3 regions. Now, a lot of times when you're working with data science and you're dealing with regions or even word analysis, instead of doing one column and labeling it 0, 1, 2, 3, a lot of times you increase your features. And so you would have region northwest would be 1 column, yes or no. Region southwest would be 1 column, yes or no. True, 0, 1. But for this particular setup, this will work just fine on here. Now that we spent all that time getting it set up, here's the fun part. Here's the part where we're actually using our setup on this, and you'll see right here we have our Y linear regression dataset drop the charges, because that's what we want to predict. And so our X linear data set drop the charges, because that's what we're going to predict. We're predicting charges right here. So we don't want that as our input for our features. And our Y output is charges. That's what we want to guess. We want to guess what the charges are. And then what we talked about earlier is we don't want to do all the data at once. So we're going to take 0.3, means 30%. We're going to take 30% of our data, and it's going to be as the testing site. So here's our Y test and our X test down there. And so that part, our model will never see it until we're ready to test to see how good it is. And then of course right here you'll see our training set, and this is what we're going to train it. We're going to train it on 70% of the data. And then finally the big ones, this is where all the magic happens. This is where we're going to create our magic setup, and that is right here. Our linear model, we're going to set it equal to the linear regression model, and then we're going to fit the data on here. And then at this point, I always like to pull up, if you're working with a new model, it's good to see where it comes from. And this comes from the Scikit-learn, and this is the sklearn linear model, linear regression that we imported earlier. And you can see they have different parameters. The basic parameter works great if you're dealing with just numbers. I mentioned that earlier with stock, high-lows. This model will do as good as any other model out there if you're doing just the very basic high-lows and looking for a linear fit, a regression model fit. And one of the things when I'm looking at this is I look for methods. And you'll see here's our fit that we're using right now, and here's our predict. And we'll actually do a little bit in the middle here as far as looking at some of the parameters hidden behind it, the math that we talked about earlier. And so when we go in this, we go ahead and run this, you'll see it loads the linear regression model and just has a nice output that says, hey, I loaded the linear regression model. And then the second part is we did the fit. And so this model is now trained. Our linear model is now trained on the training data. And so one of the things we can look at is the, for IDX and column name and enumerate X linear trained columns, kind of an interesting thing. This prints out the coefficients. So when you're looking at the back end of the data, you remember we had that formula, bxx1 plus bxx2 plus the intercept, and so forth. These are the actual coefficients that are in here. This is what it's actually multiplying these numbers by. And you can see like region gets a minus value, so when it adds it up, I guess region. You can read a lot into these numbers. It gets very complicated. There's ways to mess with them. If you're doing a basic linear regression model, you usually don't look at them too closely. But you might start looking in these and saying, hey, you know what, smoker, look how smoker impacts the cost. It's just massive. So this is a flag that, hey, the value of the smoker really affects this model. And then you can see here where the body mass index, so somebody who is overweight is probably less healthy and more likely to have cost money. And then of course age is a factor, and then you can see down here we have sex is then a factor also, and it changes as you go in there. Negative number, it probably has its own meaning on there. Again, it gets really complicated when you dig into the workings and how the linear model works on that. And so we can also look at the intercept. This is just kind of fun. So it starts at this negative number and then adds all these numbers to it. That's all that means. That's our intercept on there. And that fits the data we have on that. And so you can see right here, we can go back and, oops, give me just a second. There we go. We can go ahead and predict the unknown data, and we can print that out. And if you're going to create a model to predict something, we'll go ahead and predict it. Here's our Y prediction value, linear model predict. And then we'll go ahead and create a new data frame. In this case, from our X linear test group, we'll go ahead and put the cost back into this data frame. And then the predicted cost, we're going to make that equal to our Y prediction. And so when we pull this up, you can see here that we have the actual cost and what we predicted the cost is going to be. There's a lot of ways to measure the accuracy on there, but we're going to go ahead and jump into our mushroom data. And so in this, you can see here we've run our basic model. We built our coefficients. You can see the intercept, the back end. You can see how we're generating a number here. Now with mushrooms, we want a yes or no. We want to know whether we can eat them or not. And so here's our mushroom file. We're going to go ahead and run this and take a look at the data. And again, you can ask for a copy of this file. Send a note over to simplilearn.com. And you can see here that we have a class, the cap shape, cap surface, and so forth. So there's a lot of feature. In fact, there's 23 different columns in here going across. And when you look at this, I'm not even sure what these particular, like PEE, PE. I don't even know what the class is on this. I'm going to guess by the notes that the class is poisonous or edible. So if you remember before, we had to do a little pre-coding on our data. Same thing with here. We have our cap shape, which is B or X or K. We have cap color. These really aren't numbers, so it's really hard to do anything with just a single number. So we need to go ahead and turn those into a label encoder, which again, there's a lot of different encoders. With this particular label encoder, it's just switching it to 0, 1, 2, 3 and giving it an integer value. In fact, if you look at all the columns, all of our columns are labels. And so we're just going to go ahead and loop through all the columns in the data, and we're going to transform it into a label encoder. And so when we run this, you can see how this gets shifted from XBXXK to 0, 1, 2, 3, 4, 5, or whatever it is. Class is 0, 1, 1 being poisonous, 0 looks like it's editable, and so forth on here. So we're just encoding it. If you were doing this project, depending on the results, you might encode it differently. Like I mentioned earlier, you might actually increase the number of features as opposed to labeling it 0, 1, 2, 3, 4, 5. In this particular example, it's not going to make that big of a difference how we encode it. And then, of course, we're looking for the class, whether it's poisonous or edible. So we're going to drop the class in our X logistics model, and we're going to create our Y logistics model is based on that class. So here's our XY. And just like we did before, we're going to go ahead and split it using 30% for test, 70% to program the model on here. And that's right here. Whoops, there we go. There's our train and test. And then you'll see here on this next setup, this is where we create our model. All the magic happens right here. We go ahead and create a logistics model. I've upped the max iterations. If you don't change this for this particular problem, you'll get a warning that says this has not converged. Because that's what it does, is it goes through the math and it goes, hey, can we minimize the error? And it keeps finding a lower and lower error, and it still is changing that number. So that means it hasn't converged yet. It hasn't found the lowest amount of error it can. And the default is 100. There's a lot of settings in here. So when we go in here to, let me pull that up from the sklearn. So we pull that up from the sklearn model. You can see here we have our logistic. It has our different settings on here that you can mess with. Most of these work pretty solid on this particular setup, so you don't usually mess a lot. Usually I find myself adjusting the iteration, and I'll get that warning and then increase the iteration on there. And just like the other model, you can go, just like you did with the other model, we can scroll down here and look for our methods. And you can see there's a lot of methods available on here. And certainly there's a lot of different things you can do with it. But the most basic thing we do is we fit our model, make sure it's set right, and then we actually predict something with it. So those are the two main things we're going to be looking at on this model, is fitting and predicting. There's a lot of cool things you can do that are more advanced, but for the most part, these are the two which I use when I'm going into one of these models and setting them up. So let's go ahead and close out of our sklearn setup on there. And we'll go ahead and run this. And you can see here it's now loaded this up there. We now have a logistic model. And we've gone ahead and done a predict here also, just like I was showing you earlier. So here's where we're actually predicting the data. So we've done our first two lines of code as we create the model. We fit the model to our training data. And then we go ahead and predict for our test data. Now, in the previous model, we didn't dive into the test score. I think I just showed you a graph, and we can go in there, and there's a lot of tools to do this. We're going to look at the model score on this one. And let me just go ahead and run the model score. And it says that it's pretty accurate. We're getting a roughly 95% accuracy. Wow, that's good. 95% accuracy. 95% accuracy might be good for a lot of things. But when you look at something as far as whether you're going to pick a mushroom on the side of the trail and eat it, we might want to look at the confusion matrix. And for that, we're going to put in our Y logistic test, the actual values of edible and unedible, and we're going to put in our prediction value. And if you remember on here, let's see, I believe it's poisonous was 1, 0 is edible. So let's go ahead and run that, 0, 1. 0 is good. So here is a confusion matrix, and this is, if you're not familiar with these, we have true, 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 false, true, false, false, false. So it says out of the edible mushrooms, we correctly labeled 1,201 mushrooms edible that were edible. And we correctly measured 1,113 poisonous mushrooms as poisonous. But here's the kicker. I labeled 56 edible mushrooms as being poisonous. Well, that's not too big of a deal. We just don't eat them. But I measured 68 mushrooms as being edible that were poisonous. So probably not the best choice to use this model to predict whether you're going to eat a mushroom or not. And you'd want to dig a little deeper before you start picking mushrooms off the side of the trail. So a little warning there when you're looking at any of these data models, looking at the error and how that error fits in with what domain you're in, domain in this case being edible mushrooms. Be a little careful. Make sure that you're looking at them correctly. So we've looked at edible or not edible. We've looked at regression model as far as the end values, what's going to be the cost and what our predicted cost is, so we can start figuring out how much to charge these people for their insurance. And so these really are the fundamentals of data science. When you pull them together, when I say data science, I'm talking about your machine learning code. Classification is probably one of the most widely used tools in machine learning in today's world. It is also one of the simpler versions to start understanding how a lot of machine learning works. We're going to start by taking a look at what exactly is classification, the important terminologies around classification. We'll look at some real-world applications, my favorite, popular classification algorithms, and there are a lot out there, so we're only going to touch briefly on a variety of them so you can see how the different flavors work. And we'll have some hands-on demos in Python embedded throughout the tutorial. Classification. Classification is a task that requires the use of machine learning algorithms to learn how to assign a class label to a given data. You can see in this diagram we have our unclassified data. It goes through a classification algorithms, and then you have classified data. It's hard to just see it as data, and that really is where you kind of start and where you end when you start running these machine learning algorithms and classification. And the classification algorithms is a little black box in a lot of respects. And we'll look into that. You can see what I'm talking about when we start swapping in and out different models. Let's say we are given the task of classifying a given bunch of fruits and vegetables on the basis of their category, i.e. fruits are to be grouped together and vegetables are to be grouped together. And so we have a data set, we'll call it the bunch, is divided into clusters, one of which consists of the fruits, while the other has the vegetables. You can actually look at this as any kind of data. When we talk about breast cancer, can we sort out in images to see what is malignant, what is benign? Very popular one. Can you classify flowers, the iris data set? Certainly in wildlife, can you classify different animals and track where they're going? Classification is really the bottom starting point or the baseline for a lot of machine learning and setting it up and trying to figure out how we're going to break the data up so we can use it in a way that is beneficial. So here the fruits and the vegetables are grouped into clusters, and each cluster has a specific characteristic, i.e. whether they are a fruit or a vegetable. And you can see we have a pile of fruits and vegetables. We feed it into the algorithm, and the algorithm separates them out, and you have fruits and vegetables. So some important terminologies before we dig into how it sorts them out and what that all means. When we look at the terminologies, you have a classifier. That's the algorithm that is used to map the input data to a specific category. The classification model, the model that predicts or draws a class to the input data given for training. Feature. It is an individual measurable property of the phenomena being observed. and labels, the characteristics on which the data points of a data set are categorized. The classifier and the classification model go together. A lot of times the classifier is part of the classification model, and then you choose which classifier you use after you choose which model you're using. Where features are what goes in, labels are what comes out. So your classifier model is right in the middle of that. That's that little black box we were just talking about. Clusters. They are a group of data points which have some common characteristics. Binary classification. It is a classification condition with two outcomes which are either true or false. Multi-label classification. This is a classification condition where each sample is assigned to a set of labels or targets. Multi-class classification, the classification with more than two classes. Here each sample is assigned to one and only one label. When we look at this group of terminologies, a few important things to notice. Going from the top, clusters, when we cluster data together, we don't necessarily have to have an end goal. We just want to know what features cluster together. These features then are mapped to the outcome we want. In many cases, the first step might not even care about the outcome, only about what data connects with other data. And there's a lot of clustering algorithms out there that do just the clustering part. Binary classification. It is a classification condition with two outcomes which are either true or false. We're talking usually it's either a cat or it's not a cat. It's either a dog or it's not a dog. That's the kind of thing we talk about binary classification. And then that goes into multi-label classification. Think of label as you can have an object that is brown, you can have an object that is labeled as a dog, so it has a number of different labels. That's very different than a multi-class classification where each one's a binary. You can either be a cat or a dog. You can't be both a cat and a dog. Real-world applications. So to make sense of this, of course, the challenge is always in the details, is to understand how we apply this in the real world. So in real-world applications, we use this all the time. We have email spam classifier. So you have your email inbox coming in. It goes through the email filter that we usually don't see in the background, and it goes, this is either valid email or it's a spam, and it puts it in the spam filter if that's what it thinks it is. Alexa's voice classifier, Google Voice, any of the voice classifiers, they're looking for points, so they try to group words together, and then they try to find those groups of words trigger a classifier. So it might be that the classifier is to open your tasks program or open your text program so that you can start sending a text. Sentiment analysis is really big. When we're tracking products, we're tracking marketing, trying to understand whether something is liked or disliked is huge. That's like one of the biggest driving forces in sales nowadays, and you almost have to have these different filters going on if you're running a large business of any kind. Fraud detection. You can think of banks. They find different things on your bank statement and they detect that there's something going on there. They have algorithms for tracking the logs on computers. They start finding weird logs on computers. They might find a hacker. I mentioned cat and dog, so here's our image classification. We have a neighbor who runs an outdoor webcam, and we like to have it come up with a classification when the wild animals in our area are out, like foxes. We actually have a mountain lion that lives in the area, so it's nice to know when he's here. Handwriting prediction, classifying A, B, C, D, and then classifying words to go with that. So let's go ahead and roll our sleeves up and take a look at some popular classification algorithms. Before we look at the algorithms, let's go back and take a look at our definitions. We have a classifier and a classification model. So we're looking at the classifier, an algorithm that is used to map the input data to a specific category. One of those algorithms is a logistic regression. The logistic regression is a classification algorithm used to model the probability of a certain class or event existing, such as pass, fail, or win, lose, etc. It provides its output using the logistic function or sigmoid function to return the probability value that can then be mapped to two or more discrete classes. A sigmoid function is an activation function that fits the variable and limit the output to a range between 0 and 1. A standard sigmoid function or logistic function is represented by the formula fx equals 1 over 1 plus e to the minus x, where x is the equation of the line and e is the exponential. Just taking a quick look at this, you can think of this as being a point of uncertainty. And so as we get closer and closer to the middle of the line, it's either activated or not. And we want to make that just shoot way up. So you'll see a lot of the activation formulas kind of have this nice S-curve where it approaches 1 and approaches 0. And based on that, there's only a small region of error. And so you can see in the sigmoid logistic function, the 1 over 1 plus e minus x to the minus x, you can see it frames that nice S-curve. We also can use a tangent variation. There's a lot of other different models here as far as the actual algorithm. This is the most commonly used one. Let's go ahead and roll up our sleeves and take a look at a demo that is going to use a logistic regression. So we're going to have the activation formula and the model, because you have to have both. For this, we will go into our Jupyter notebook. Now, I personally use the Anaconda Navigator to open up the Jupyter notebook to set up my IDE as a web-based. It's got some advantages that it's very easy to display in, but it also has some disadvantages in that if you're trying to do multi-threads and multi-processing, you start running into single get issues with Python, and then I jump to PyCharm. Really depends on whatever IDE you want. Just make sure you've installed NumPy and the sklearn modules into your Python in whatever environment you're working in so that you'll have access to that for this demo. Now, the team in the back has prepared my code for me, which I'll start bringing in one section at a time so we can go through it. Before we do that, it's always nice to actually see where this information is coming from and what we're working with. So the first part is we're going to import our packages, which you need to install into your Python, and that's going to be your NumPy. We usually use NumPy as in P, and then from sklearn, the learn model, we're going to use a logistic regression. And from sklearn metrics, we're going to import the classification report confusion matrix. And if we go ahead and open up the scikit-learn.org and go under their API, you can see all the different features and models they have. And we're looking at the linear model logistic regression, one of the more common classifiers out there. And if we go ahead and go into that and dig a little deeper, you'll see here where they have the different settings. And it even says right here, note, the regularization is applied by default. So by default, that is the activation formula being used. Now, we're not going to spend, we might come back to this, look at some of the other models, because it's always good to see what you're working with. But let's go ahead and jump back in here. And we have our imports. We're going to go ahead and run those. So these are now available to us as we go through our Jupyter Notebook script. And they put together a little piece of data for us. This is simply going through 0 to 1. Actually, let's go ahead and print this out over here. We'll go ahead and print X just so you can see what we're actually looking for. And when we run this, you can see that we have our X is 0, 1, 2 through 9. We reshaped it. The reason for this is just looking for a row of data. Usually we have multiple features. We just have the one feature which happens to be 0 through 9. And then we have our 10 answers right down here. 0, 1, 0, 0, 1, 1, 1, 1, 1, 1. You can bring in a lot of different data depending on what you're working with. You can make your own. You can, instead of having this as just a single, you could actually have like multiple features in here, but we just have the one feature for this particular demo. And this is really where all the magic happens right here. And I told you it's like a black box. That's the part that is kind of hard to follow. And so if you look right here, we have our model. We talked about the model right there, and then we went ahead and set it for library linear. As I showed you earlier, that's actually default, so it's not that important. Random state equals 0. This stuff you don't worry too much about. And then with the scikit-learn, you'll see the model fit. This is very common to scikit. They use similar stuff in a lot of other different packages, but you'll see that that's very common. You have to fit your data. And that means we're just taking the data and we're fitting our X right here, which is our features. That's our X. And here's Y. These are the labels we're looking for. So before we were looking at, is it fraud? Is it not? Is it cat? Is it not? That kind of thing. And this is looking at 0, 1, so we want to have a binary setup on this. And we'll go ahead and run this. You can see right here it just tells us what we loaded it with as our defaults, and that this model has now been created and we've now fit our data to it. And then comes the fun part. You work really hard to clean your data, to bake it and cook it. There's all kinds of, I don't know why they go with the cooking terms as far as how we get this data formatted. Then you go through and you pick your model, you pick your solver, and you have to test it to see, hey, which one's going to be best. And so we want to go ahead and evaluate the model. And you do this is that once you've figured out which one is going to work the best for you, you want to evaluate it so you can compare it to your last model. And you can either update it to create a new one or maybe change the solver to something else. I mentioned tangent. That's one of the other common ones that's commonly used with language. For some reason the tangent, even though it looks almost to me identical to the one we're using with the sigmoid function, for some reason it activates better with language, even though it's a very small shift in the actual math behind it. We already looked at the data early, but we'll go and look at it again just so you can see what we look at. We have our rows of 0, 1, row, it only has one entity, and we have our output that matches these rows, and these do have to match. You'll get an error if you put in something with a different shape. So if you have 10 rows of data and 9 answers, it's going to give you an error because you need to have 10 answers for it. A lot of times you separate this too when you're doing larger models. But for this, we're just going to take a quick look at that. The first thing we want to start looking at is the intercept, one of the features inside our linear regression model. We'll go ahead and run that and print it. You'll see here we have an intercept of minus 1.516. And if we're going to look at the intercept, we should also look at our coefficients. And if you run that, you'll see that we get our coefficient is the 0.7035. You can just think of this as your Euclidean geometry for a very basic model like this, where it intercepts the y at some point and we have a coefficient multiplying by it. A little more complicated in the back end, but that is the gist of this simple model with just the one feature in there. And we'll go ahead and we'll reprint the y because I want to put them on top of each other with the y predict. And so these were the y values we put in, and this is the y predict we had coming out. And you can see, here we go. There's the y actual, and there's what the prediction comes in. Now keep in mind that we used the actual complete data as part of our training. That is, if you're doing a real model, a big stopper right there because you can't really see how good it did unless you split some data off to test it on. This is the first step, is you want to see how your model actually tests on the data you trained it with. And you can see here, there is this point right here where it has it wrong, and this point right here where it also has it wrong. And it makes sense because our input is 0 through 9, and it has to break it somewhere, and this is where the break is. So it says this half the data is going to be 0 because that's what it looked like to me if I was looking at it without an algorithm, and this data is probably going to be 1. And I forgot to point this out, so let's go back up here. I just kind of glanced over this window here where we did a lot of stuff. Let's go back and just take a look at that. What was done here is we ran a prediction. So this is where our predict comes in, is our model.predict. So we had a model fit. We created the model. We programmed it to give us the right answer. Now we go ahead and predict what we think it's going to be. There's our model.predict probability of x. And then we have our y predict, which is very similar, but this has to do more with the probability numbers. So if you remember down below, we had the setup where we're looking at that sigmoid function. That's what this is returning. And the y predict is returning a 0 or a 1. And then we have our confusion matrix. We'll look at that. And we have our report, which just basically compares our y to our y predict, which we just did. It's kind of nice. It's simple data, so it's really easy to see what we're doing. That's why we use the simple data. This can get really complicated when you have a lot of different features and things going on and splits. So here we go. I printed out our actual and our prediction. So this is the actual data. This is what the predict ran. And then we'll go ahead and we're going to print out the confusion matrix. We were just talking about that. This is great if you have a lot of data to look at. But you can see right here our confusion matrix says, if you remember from the confusion matrix, we have the 2. This is 2 correct. 1, 2. And it's been a while since I looked at a confusion matrix. There's the 2, and then we have this one, which is our 6. That's where the 6 comes from. And then we have this one, which is the 1 false. This is the 2 1s, so we have this one here and this one here, which is misclassified. This really depends on what data you're working with as to what is important. You might be looking at this model, and if this confusion matrix comes up and says that you've misclassified even one person as being non-malignant cancer, that's a bad model. I wouldn't want that classification. I'd want this number to be 0. I wouldn't care if this false positive was off by a little bit more, as long as I knew that I was correct on the important factor that I don't have cancer. So you can see that this confusion matrix really aims you in the right direction of what you need to change in your model, how you need to adjust it. And then there's, of course, a report. Reports are always nice. If you notice, we generated a report earlier. We'll go and just print the report up, and you can remember this is our report. It's a classification report, y, y predict. So we're just putting in our two values. Basically what we did here visually with our actual and our predicted value. And we'll go ahead and run the report, and you can see it has the precision, the recall, your F1 score, your support, translated into accuracy, macro average, and weighted average. So it has all the numbers. A lot of times when working with clients or with the shareholders in the company, this is really where you start, because it has a lot of data and they can just kind of stare at it and try to figure it out. And then you start bringing in like the confusion matrix. I almost do this in reverse as to what they show. I would never show your shareholders the intercept of the coefficient. That's for your internal team only working on machine language. But the confusion matrix and the report are very important. Those are the two things you really want to be able to show on these. And you can see here we did a decent job of classifying the data, managed to get a significant portion of it correct. We had our accuracy here is a 0.80 F1 score, that kind of thing. So, it's a pretty accurate model. Of course, this is pretty goofy because it's a very simple model, and it's just splitting the model between ones and zeros. So that was our demo of the on logistic regression on there. Let's go ahead and take a look at k nearest neighbors. This one is another very highly used and important algorithm to understand. K nearest neighbors is a simple algorithm which stores all available cases and classifies new cases based on the similarity measure. The k nearest neighbor finds out the class of the new data point by finding its nearest neighbors. If there are 3 data points of class A and 2 data points of class B near to the new data point, then the KNN classifies the new data point as class A. The k in k nearest neighbors is the number of nearest neighbors we are looking for. i.e., if we say k equals 3, this means that we are looking for nearest 3 neighbors of unclassified data point. Usually we take the k value between 3 to 10 as it leads to a better result. A smaller value of k means that noise will have a bigger influence on the result, and a larger value of k makes it computationally expensive. Hence, the data scientists prefer the range of k between 3 and 10. When we talk about noise, you remember the data we just looked at was 0, 1, 1, 0, 0. It had some values where cut it and said everything to the right is a 1, everything to the left is a 0, but it had some 1s and 0s mixed in there. That's called noise. That's what they're talking about, is there's some things that are right in the middle in the classification which makes it very hard to classify. So suppose we're trying to find the class for a new point indicated by the red color. And you can see it's kind of right between the cat, right between the dogs. Let k equal 3, so we are finding the 3NN for the red data point. By looking at the plot on the right, we can see that the red data point belongs to the class dogs, as it has 2 votes for class dog and 1 vote for class cat. And if you ask the question, well, what are you measuring the distance? What is that distance? It could be the measurements of the ears, whether they're pointed or floppy. That might be one of the features you're looking at, is how floppy the ears are. Another one might be the whiskers versus the nose. And then you take those measurements, and using one of the most common things in k-means measurement is the Euclidean geometry, you can figure out the distance between those points. There's a lot of different algorithms for that. But you can think about it that you do have to have some kind of solid data to measure. And so we can conclude that the new data point belongs to the class dog. So let's go ahead and see what this looks like in code and do a demo on the k nearest neighbors in here. And we'll go right back into our Jupyter Notebook and open up a new Python programming script page. Of course, once we're in here, we'll want to look at the scikit-learn. I did just a quick search for skneighbors, kn-neighbors classifier. This actually is the older version, 0.023 is the one we want. And you'll see here that we have all their defaults. In neighbors equals 5. At defaults, we were talking about that between 3 and 10. There's different ways to weigh it. There's an algorithm based on it. I mentioned Euclidean geometry, finding the distance. There's other algorithms for figuring out what that distance is and how to weight those. And there's a lot of other parameters you can adjust. For the most part, the k-means basic setup is a good place to start and just let the defaults go. We might play with some of those. We'll see what the guys in the back did. And from here we're going to import NumPy. We're going to use pandas. If you haven't been running pandas, pandas is our data frame which sits on top of NumPys. Data frames are, NumPys is our number array. Pandas is our data frame. Matplot library, because we're going to plot some graphs. Everybody likes some pretty pictures. It makes it a lot easier to see what's going on when you have a nice display. And that's also what the Seaborn is in here in the setup that sits on top of the Matplot library. The ones we really want to look at right here are what we're bringing in from sklearn. These ones right here. So from sklearn we're going to load, I mentioned the breast cancer. That's a very popular one because it has, I believe it's 36 measurements, so there's 36 features, and unless you're a expert, you're not going to know what any of those features really mean. You can sort of guess, but there's special measurements they take of when they take an image. And of course our confusion matrix, so that we can take a look and see what the data looks like and how good we did. And then we have our KN neighbors classifier on here. And then I mentioned that whenever you do training and testing, you want to split the data up. You don't want to train the data and then test it on the same data. That just tells you how good your training model is. It doesn't tell you whether it actually works on unknown data. And so this just splits it off so that we can train it, and then we can take a look at data we don't have in there and see how good it did. And we'll go ahead and load our data up. So here's our setup on that. Oops, there we go. So we're going to go ahead and load the data up. We have our X value, and that's going to come from our breastcancer.data and column breast cancer feature names. So there's our actual, all our different features. We'll print that out here in a second. And then we have our mean area, mean compactness. So I guess we're going to take the data and we're only going to use a couple of the columns. This just makes it easier to read. Of course, when you actually we're going to do this, you'd want to use all your columns. And then we have our Y, and this is simply whether it's either malignant or benign. And then we want to go ahead and drop the first line because that's how it came in on there. And we'll go ahead, let's just take a look at this a little closer here. Let's go and run this real quick. And just because I like to see my data before I run it, we can look at this and we can look at the original features. Remember, we're only going to use 2 features off of here just to make it a little easier to follow. And here's the actual data, and you can see that this is just this massive stream of data coming in here. It's going to just skip around because there's so much in there to set up. I think there's like 500 if I remember correctly, and you can see here's all the different measurements they take. But we don't really need to see that on here. We're just going to take a look at just the 2 columns. And then also our solution. We'll go ahead and just do a quick print Y on here so you can see what the Y looks like. And it is simply just 0, 0, 0, benign, 0, 0, 0, 1. So a 1 means it's benign, a 0 means it's malignant. Is what we're looking at on that. Go ahead and cut that out of there. The next stage is to go ahead and split our data. I mentioned that earlier. We'll just go ahead and let them do the splitting for us. We have xtrain, xtest, ytrain, ytest, and so we go ahead and train, test, split, xy, random state equals 1. It makes it nice and easy for us. We'll go ahead and run that. And so now we have our training and our testing. Train means we're going to use that to train the model, and then we're going to use the test to see how good our model does. And then we'll go ahead and create our model. Here's our KNN model, the K neighbors classifier. N neighbors equals 5. The metrics is Euclidean. Remember I talked about Euclidean? This is simply your C squared equals A squared plus B squared plus A squared equals B squared plus C squared plus C squared plus D squared, and then you take the square root of all that. That's what they're talking about here. It's just the length of the hypotenuse of a triangle, but you can actually do that in multiple dimensions, just like you do in 2 dimensions with a regular triangle. And here we have our fit. This should start to look familiar since we already did that in our last example. That's very standard for scikit and any other one, although sometimes the fit algorithms look a little bit more complicated because they're doing more things on there, especially when you get into neural networks. And then you have your k-neighbors. It just tells you we created a k-neighbors setup. They kind of wanted us to reformat the y, but it's not that big of a deal for this. And it comes out and shows you that we're using the Euclidean metric for our measurement. So now we've created a model. Here's our live model. We fitted the data to it. We say, hey, here's our training data. Let's go ahead and predict it. So we're going to take our y predict equals knn predict y test. So this is data we have not. This model has not seen this data, and so we're going to create a whole new set of data off of there. Now, before we look at our prediction, in fact, let's I'm going to bring this down and put it back in here later. Let's take a look at our x test data versus the y test. What does it look like? And so we have our mean area. We're going to compare it to our mean compactness. We're going to go ahead and run that. And we can see here the data, if you look at this, just eyeballing it, we put it in here, we have a lot of blue here, and we have a lot of orange here. And so these dots in the middle, especially like this one here and these here, these are the ones that are going to give us false negatives, and so we should expect this is your noise. This is where we're not sure what it is. And then B9 is, in this case, is done in blue, and malignant is done in 1. So if you look at it, there's 2 points based on these features, which makes it really hard to have 100% where the 100% is down here or up here. That's kind of the thing I'd be looking for when we're talking about cancer and stuff like that, where you really don't want any false negatives. You want everything, false positive, great. You're going to go in there and have another setup in there where you might get an autopsy or something like that done on it. Again, that's very data specific on here. So now let's go ahead and pull in and get our prediction in here, and we'll create our y prediction. We'll go ahead and run that. So now this is loaded with what we think the unknown data is going to be. And we can go ahead and take that and go ahead and plot it, because it's always nice to have some pretty pictures. And when we plot it, we're going to do the mean area versus mean compactness. Again, you look at this map and you can see that there's some clear division here. We can clearly say on some of the stuff that our y prediction, if we look at this map up here, and this map down here, we probably got some pretty good deal. It looks pretty good, like they match a lot. This is, of course, just eyeballing it. Really, you don't want to eyeball these things. You want to show people the pictures so that they can see it, and you can say, hey, this is what it looks like. But we really want the confusion matrix. And when we do the y test and the y predict, we can see in the confusion matrix here, it did pretty good. And we'll just go ahead and point that out real quick. Here's our 42, which is positive, and our 79, and if I remember correctly, I'd have to look at the data, which one of these is a false negative. I believe it's the 9. That's scary. I would not want to be one of those 9 people told that I don't have cancer and then suddenly find out I do. So we would need to find a way to sort this out. And there is different ways to do that. A little bit past this, but you can start messing with the actual Euclidean geometry and the activation measurements and start changing those and how they interact, but that's very advanced. There's also other ways to classify them, or to create a whole other class right here of we don't knows. Those are just a couple of the solutions you might use for that. But for a lot of things, this works out great. You can see here, maybe you're trying to sell something. Well, if this was not life dependent, and this was, if I display this ad, 42 of these people are going to buy it, and if I display this other ad, if I don't display it, 79 people are going to go a different direction, or whatever it is. So maybe you're trying to display whether they're going to buy something if you add it on to the website, in which case that's really a good numbers. You've just added a huge number of cells to your company. So that was our k nearest neighbors. Let's go ahead and take a look at support vector machines. So support vector machines is the main objective of a support vector machine algorithm is to find a hyperplane in an n-dimensional space, n is the number of features, that distinctly classifies the data points. And if you remember, we were just looking at those nice graphs we had earlier. In fact, let me go ahead and flip back on over there. If we were looking at this data here, we might want to try to find a nice line through the data. And that's what we're talking about with this next setup. So the main objective of support vector machine algorithm is to find a hyperplane in an n-dimensional space. N is the number of features that distinctly classifies the data points. To separate the two classes of data, there are many hyperplanes that can be chosen. Our objective is to find the plane that has the maximum margin, i.e. the maximum distance between data points of both classes. The dimensions of the hyperplane depends on the number of features. If there are 2 input features, then the hyperplane is just a line. If there are 3 features, then the hyperplane becomes a 2-dimensional plane. The line that separates the data into 2 classes is called as support vector classifier, or hard margin. And that's what I just showed you on the other data. You can see here where we look for a line that splits the data evenly. The problem with hard margin is that it doesn't allow outliers and doesn't work with non-linearly separable data. And we just were looking at that. Let me flip back on over here. And when we look at this setup in here, and we look at this data, here we go. Look how many outliers are in here. These are all these blue dots on the wrong side of the line would be considered an outlier, and the same with the red line. And so it becomes very difficult to divide this data unless there's a clear space. There we go. Therefore, we introduce soft margins, which accept the new data point and optimize a model for nonlinear data points. Soft margins pass through the data points at the border of the classes. The support vector machine can be used to separate the 2 classes of shapes. Here we can see that although triangles and diamond shapes have pointy edges, but we are able to classify them in 2 categories using a support vector machine. Let's go ahead and see what that looks like in a demo. We'll flip back on over to our Jupyter notebook. We always want to start with taking a look at the sklearn API, in this case the SVM SVC. There is a significant number of parameters because the SVM has been a lot of development in the recent years and it's become very popular. If we scroll all the way down to methods, you'll see right here is our fit and our predict. That's what you should see in most of the scikit-learn packages. So this should look very familiar to what we've already been working on. And we'll go ahead and bring in our import and run that. We should already have pandas, numpy, our matplot library, which we're going to be using to graph some of the things. A little bit different right here. You'll see that we're going to go ahead and bring in one of the fun things you can do with test data is make circles. Circles are really hard to classify. You have a ring on the inside and a ring on the outside, and you can see where that can cause some issues. And we'll take a look at that a little closer in a minute. Here's our SVM setup on there, and then of course our metrics, because we're going to use that to take a closer look at things. So we go ahead and run this. Whoops, already did. Once we've gone ahead and done that, we're going to go ahead and start making ourselves some data. And this part probably a little bit more complicated than we need. I'm not going to go too much in detail on it. We're going to make a mesh grid, and we'll see what that looks like in a minute. We're defining the minimums. You can see in here, create a mesh grid of points. Here's our parameters of x, y, and h. It's going to return x, x, y, y. You can also send a note to us. Make sure you get a copy of this if you want to dig deeper into this particular code especially. And we have a ymin, ymax, ymin, ymax, plus 1. Here's our mesh grid we're actually going to make, xx and yy. Plot the contours all the way through, and this is just a way of creating data. It's kind of a fun way to create some data. Here we go, plot contours ax, clf, xx, yy, and return an out. Add some perimeters here so that when we're doing it, we have our setup on there, train property, and then we'll go ahead and make our data. Just throw that right in there too in the same setup and run that. So now we have x and y. We're going to make our circles. We have n samples equals samples. In this case, we're going to have 500 samples. We went ahead and gave it noise of 0.05, random state 123. These are all going into, oops, go back up. Here we go. Make our mesh grid, make circles. There it is. So this is going into our make circles up here. And this is part of that setup on this. And then once we've gone ahead and make the circle, let's go ahead and plot it. That way you can see what we're talking about. Right now what I'm saying is really confusing because without a visual it doesn't really mean very much what we're actually doing. So let me go ahead and run this with the plot. And let's go back up here and just take a look. We've made our circle. We have our n samples equals samples. So we're going to have 500. We're going to have training property 0.8. Here's our data frame. We go and load it into the data frame so we can plot it. Groups, df group by label. This is kind of a fun way if you have multiple columns. You can really quickly pull whatever setup is in there. And then we go ahead and plot it. And you can see here we have 2 rings that are formed. And that's all this is doing, is just making this data for us. This is really hard data to figure out. A lot of programs get confused in this because there's no straight line or anything like that. But we can add planes and different setups on here. And so you can see we have some very interesting data. We have our zeros in blue and our ones in the yellow in the middle, and the data points are an XY coordinate plot on this. One of the things we might want to do on here is go ahead and find the min to max ratio set up in there, and we can even do, let's just do a print x so you can see what the data looks like that we're producing on this. There we go. So x equals x minus x min over x max minus x min. All we're doing is putting this between 0 and 1. Whatever this data is, we want a 0 to 1 setup on here. And if you look at this, all our data is 0.8, 0.5. That's what this particular line is doing. That's a pretty common thing to do in processing data, especially in neural networks. Neural networks don't like big numbers. They create huge biases and cause all kinds of problems. And that's true in a lot of our models. Some of the models it doesn't really matter, but when you're doing enough of these, you just start doing them. You just start putting everything between 0 and 1. There's even some algorithms to do that in the sklearn, although it's pretty, as you can see, it's pretty easy to do it here. So let's go ahead and jump into the next thing, which is a linear kind of setup. C equals 1.0. This is the SVM regularization parameter we're going to use. Models, here's our SVM. And let's go and scroll up just a notch. There we go. So here we are with our model. We're going to create the setup with the SVC. Kernel is linear. And we'll come back to that because that's an important setup in there as far as what our kernel is. And you'll see why that's so important here in a minute, because we're going to look at a couple of these. And so this one is, we're actually going to be changing how that processes it. And then our C, here's our 0.0, and then the rest of this is plotting. We're just adding titles, making the contours so it's a pretty graph. You can actually spend, this would be a whole class just to do all the cool things you can do with scatter plots and regular plots and colors and things like that. In this case, we're going to create a graph with a nice white line down the middle so that you can see what's going on here. And when we do this, you can see that as it split the data, the linear did just that. It drew a line through the data, and it says this is supposed to be blue, and this is supposed to be red, and it doesn't really fit very well. And that's because we used a linear division of the data, and it's not very linear data on there. It's anything but linear. So when we look at that, it's like, well, okay, that didn't work. What's the next option? Well, there's a lot of choices in here. One of them is just simply we can change this from the kernel being linear to poly. And we'll just go back up here and use the same chart. Oops, here we go. So here we go. Linear kernel. We'll change this to poly. And then when we come in here and create our model, here's our model up here, linear. We can actually just go right in and change this to the poly model. And if you remember, when we go back over here to the SVC, and let's scroll back up here, there's a lot of different options. Oops, even further. Okay, so when we come up here and we start talking about the kernel, here's the kernel. There's linear, there's poly, RBF, sigmoid, pre-computed. There's a lot of different ways to do this setup, and their actual default is RBF. Very important to note that. So when you're running these models, understanding which parameter really has a huge effect on what's going on. In this particular one with the SVM, the kernel is so important. You really need to know that. And we switched our kernel to poly, and when we run this, you can see it's changed a little bit. We now have quite an interesting looking diagram, and you can see on here it now has these classifications correct, but it messes up in this blue up here, and it messes up on this blue is correct, and this blue is supposed to be red. You can see that it still isn't quite fitting on there. And so that is, when we do a polyfit, you can see if you have a split in data where there's a group in the middle that's one kind of data and the groups on the outside are different, the polyfit or the polykernel is what's going to be fit for that. So if that doesn't work, then what are we going to use? Well, they have the RBF kernel. And let's go ahead and take a look and see what the RBF looks like. And let me go and turn my drawing off. And the RBF kernel, oops, there we go, RBF. And then of course for our title, it's always nice to have it match with the RBF kernel. And we go ahead and run this, and you can see that the RBF kernel does a really good job. It actually has divided the data up on here, and this is the kind of what you expect here was that ring. Here's our inner ring and an outer ring of data, and so the RBF fits this data package quite nicely. And that, when we talk about SVM, it really is powerful in that it has this kind of sorting feature to it in its algorithms. This is something that is really hard to get the SK means to do, or the k-means set up. And so when you start looking at these different machine learning algorithms, understanding your data and how it's grouped is really important. It makes a huge difference as far as what you're computing and what you're doing with it. So that was a demo on the support vector. Certainly you could have continued on that and done like a confusion matrix and all that kind of fun stuff to see how good it was, and split the data up to see how it vectorizes. The visual on that's so important. It makes a big difference just to see what it looks like and that giant donut and why it does circles so well, or your poly version or your linear version. So we've looked at some very numerical kind of setups where there's a lot of math involved, Euclidean geometry, that kind of thing. A totally different machine learning algorithm for approaching this is the decision trees. And there's also forests to go with the decision trees. They're based on multiple trees combined. The decision tree is a supervised learning algorithm used for classification. It creates a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. A decision tree is a hierarchical tree structure where an internal node represents features or attribute. The branch represents a decision rule, and each leaf node represents the outcome. And you can see here where they have the first one, yes or no, and then you go either left or right, and so forth. One of the coolest things about decision trees is, and I'll see people actually run a decision tree even though their final model is different, because the decision tree allows you to see what's going on. You can actually look at it and say, why did you go right or left? What was the choice? Where's that break? And that is really nice if you're trying to share that information with somebody else as to why. When you start getting into the why this is happening, decision trees are very powerful. So the topmost node of a decision tree is known as the root node. It learns to partition on the basis of the attribute value. It partitions the tree in a recursive manner. So you have your decision node. If you get yes, you go down to the next node. That's a decision node. And either yes, you go to, if it ends on a leaf node, then you know your answer, which is yes or no. So there's your end classification set up on there. Here's an example of a decision tree that tells whether I'll sleep or not at a particular evening. Mine would be depending on whether I have the news on or not. Do I need to sleep? No. Okay, I'll work. Yes. Is it raining outside? Yes, I'll sleep. No, I'll work. So I guess if it's not raining outside, it's harder to fall asleep where you have that nice rain coming in. And again, this is really cool about a decision tree is I can actually look at it and go, oh, I like to sleep when it rains outside. So when you're looking at all the data, you can say, oh, this is where the switch comes in. When it rains outside, I'll sleep really good. If it's not raining or if I don't need sleep, then I'm not going to sleep. I'm going to go work. So let's go ahead and take a look at that looks like in the code. Just like we did before, we go ahead and open up the scikit setup just to say what the decision tree classifier has. You have your parameters, which we'll look a little bit more in depth at as we write the code. It has different ways of splitting it. The strategy used to choose a split at each node, criterion, max depth. Remember the tree, how far down do you want it? Do you want it to take up the space of your whole computer with and map every piece of data, or the smaller that number is, the smaller the level of the tree is and the less processing it takes, but it's also more general, so you're less likely to get as in-depth an answer. And then of course minimal samples you need for it to split, samples for the leaves. There's a lot of things in here as far as how big the tree is and how to define it and when do you define it and how to weight it. And they have their different attributes which you can dig deeper into. That can be very important if you want to know the why of things. And then we go down here to our methods, and you'll see just like everything else, we have our fit method, very important, and our predict, the two main things that we use. What we're going to predict our x to be equal to. And we'll go ahead and go up here and start putting together the code. We're going to import our NumPy, our pandas, there's our confusion matrix, our train test split, decision tree classifier. That's the big one that we're actually working with. That's the line right here where we're going to be, decision tree, there it is. Decision tree classifier, that's the one I was looking for. And of course we want to know the accuracy and the classification report on here. And we're going to do a little different than we did in the other examples. And there's a reason for this. Let me go ahead and run this and load this up here. We're going to go ahead and build things on functions. And this is when you start splitting up into a team, this is the kind of thing you start seeing a lot more, both in teams and for yourself, because you might want to swap one data to test it on a different data depending on what's going on. So we're going to have our import data here, the data set length, the balance, and so forth. This just returns balanced data. Let me just go ahead and print, because I'm curious as to what this looks like. Import data. And it's going to return the balanced data. So if I run that, if we go ahead and print this out here and run that, you can see that we have a whole bunch of data that comes in there, and some interesting setup on here has, let's see, BRR. I'm not sure exactly what that represents on here. 111, 112, and so forth. So we have a different set of data here. The shape is 5 columns, 1, 2, 3, 4, 5. It seems to have a number at the beginning, which I'm going to guess BRL, a letter I mean, and then a bunch of numbers in there. 1111. Let's see, down here we got 555 set up on this. And let's see, balanced data. And since it said balanced data, I'm going to guess that B means balanced, R means you need to move it right, and L means it needs to be moved left or skewed to the left. I'm not sure which one. Let's go and close that out. And we'll go ahead and create a function to split the data set. X balance data equals data values. Y balance equals data values of 0. There's that letter. Remember, left, right, and balance. And then we're looking for the values of 1 through 5. And we go ahead and split it just like you would. X train, Y train set, random state 100. Test size is 0.3, so we're taking 30% of the data. And it's going to return your X, your Y train, your X train, your X test, your Y train, your Y test. Again, we do this because if you're running a lot of these, you might want to switch how you split the data and how you train it. I tend to use a bifold method. I'll take a third of the data and I'll train it on the other 2/3 and test it on that third. And then I'll switch it. I'll switch which third is the test data. And then I can actually take that information and correlate it, and it gives me a really robust package for figuring out what the complete accuracy is. But in this case, we're just going to go ahead. This is our function for splitting data. And this is where it kind of gets interesting, because remember we were talking a little bit about the different settings in our model. And so in here we're going to create a decision tree, but we're going to use the Genie setup. And where did that come from? What's the Genie on here? So if we go back to the top of their page, and we have what criterion are we going to use? We're going to use Genie. They have Genie and entropy. Those are the two main ones that they use for the decision tree. So this one's going to be Genie, and if we're going to have a function that creates the Genie model, and it even goes down here, and here's our fit train of the Genie model. We'll probably also want to create one for entropy. Sometimes I even just, I might even make this just one function with the different setups. And I know one of the things I worked on recently, I had to create one that tested across multiple models. And so I would send the parameters to the models, or I would send this part right here where it says decision tree classifier. That whole thing might be what I send to create the model, and I know it's going to fit. We're going to have our X train, and we're going to have our predict, and all that stuff is the same. So you can just send that model to your function for testing different models. Again, this just gives you one of the ways to do it. And you can see here we're going to train with the Genie, and we're also going to train with the entropy to see how that works. And if you're going to have your models going, two separate models you're sending there, we'll go ahead and create a prediction. This simply is our Y predict equals our whatever object we sent, whatever model we sent here, the CLF object, and predict against our X test. And you can see here print Y predict and return Y predict set up on here. And we'll load that definition up. And then if you're going to have a function that runs a predict and prints some things out, we should also have our accuracy function. So here's our calculate the accuracy. What are we sending? We're sending our Y test data. This could also be Y actual and Y predict. And then we'll print out a confusion matrix. Then we'll print out the accuracy of the score on here and print a report, classification report. Bundle it all together there. So if we bring this all together, we have all the steps we've been working towards, which is importing our data, by the way, is you'll spend 80% of your time importing data in most machine learning setups and cooking it and burning it and getting it formatted so that it works with whatever models you're working with. The decision tree has some cool features in that if you're missing data, it can actually pick that up and just skip that and says, I don't know how to split this. There's no way of knowing whether it rained or didn't rain last night, so I'll look at something else, like whether you watched TV after 8 o'clock, that blue screen thing. So we have our function importing our data set. We bring in the data. We split the data, so we have our x test and y train. And then we have our different models, our CLF Genie, so it's a decision tree classifier using the Genie setup, and then we can also create the model using entropy. And then once we have that, we have our function for making the prediction, and we have our function for calculating the accuracy. And then if we're going to have that, we should probably have our main code involved here. This probably looks more familiar if you're, depending on what you're working on. If you're working on like a PyCharm, then you would see this in throwing something up real quick in Jupyter Notebook. So here's our main data import, which we've already defined. We get our split data. We create our Genie. We create our entropy. So there's our two models going on here. There's our two models. So these are two separate data models. We've already sent them to be trained. Then we're going to go ahead and print the results using Genie index. So we'll start with the Genie, and we want to go ahead with the Genie and print our predictions, x test to the Genie, and calculate the accuracy on here. And then we want to print the results using entropy. So this is just the same thing coming down like we did with the Genie. We're going to put out our y-predict entropy and our calculations. So let's go ahead and run that and just see what this piece of code does. We do have, like, one of our data is getting a warning on there. That's nothing major because it's just a simple warning. Probably an update of a new version's coming out. And so here we are. We have our data set. It's got 625. You can actually see an example of the data set. B meaning balanced, I guess. And here's our 5 data points. 1111 means it's balanced. It's skewed to the right with 1112 and so forth on here. And then we're going to go ahead and predict from our prediction whether it's to the right or to the left. You can think of a washing machine that's banging on one side of the thing, or maybe it's an automated car where we're down the middle of the road that's in balance and it starts veering to the right, so we need to correct for it. And when we print out the confusion matrix, we have 3 different variables, R, L, and B. So we should see the 3 different variables on here. And you have, as far as whether it predicts, in this case, the balance. There's not a lot of balanced loads on here. And didn't do a good job guessing whether it's balanced or not. That's what I took from this first one. The second one, I'm guessing, is the right. So it did a pretty good job guessing the right balance. You can see that a bunch of them came up left unbalanced. Probably not good for an automated car, as it tells you 18 out of the 18 missed things and tells you to go the wrong direction. And here we are going the other way, 19 to 71. And of course we can back that up with an accuracy report on here, and you can see the precision, how well the left and right balance is, 79%, 79% precision, and so forth. And then we went and used the entropy, and let me just see if we can get, so we can get them both next to each other. Here's our entropy of our the first setup, our first model, which is the Genie model. 67, 18, 1971, 63, 22, 2070, pretty close. The two models, that's not a huge difference in numbers. This second one of entropy did slightly, it looks like slightly worse, because it did one better as far as the right balance and did, 4 worse on the left balance or whatever. So slightly worse. If I was guessing between these, I'd probably use the first one. They're so close, though, that it wouldn't be a clear choice as to which one worked better. And there's a lot of numbers you can play with here which might give better results depending on what the data is going in. Now, one of the takeaways you should have from the different category routines we ran is that they run very similar. You certainly change the parameters in them as to whether you're using what model you're using and how you're using it and what data they get applied to. But when you're talking about the scikit-learn package, it does such an awesome job of making it easy. You split your data up, you train your data, and you run the prediction, and then you see what kind of accuracy, what kind of confusion matrix it generates. So we talk about algorithm selection. Logistic regression, k-nearest neighbors. Logistic regression is used when we have a binomial outcome. For example, to predict whether an email is spam or not, whether the tumor is malignant or not. The logistic regression works really good on that. You can do it in a k-nearest neighbors also. The question is, which one will it work better in? I find the logistic regression models work really good in a lot of raw numbers. So if you're working with, say, the stock market, is this a good investment or a bad investment? So that's one of the things that it handles the numbers better. K-nearest neighbors are used in scenarios where non-parametric, no fixed number of parameters, algorithms are required. It is used in pattern recognition, data mining, and intrusion detection. So K means really good in finding the patterns. I've seen that as a preprocessor to a lot of other processors where you use the k-nearest neighbors to figure out what data groups together. Very powerful package. Support vector machines. Support vector machines are used whenever the data has higher dimensions, the human genome microarray. SVMs are extensively used in the hard handwriting recognition models. And you can see that we were able to switch between the parabolic and the circular setup on there, where you can now have that donut kind of data and be able to filter that out with the support vector machine. And then decision trees are mostly used in operational researches, specifically in decision analysis to help identify a strategy most likely to reach any goal. They are preferred where the model is easy to understand. I like that last one. It's a good description. Is it easy to understand? So you have data coming in. When am I going to go to bed? Was it raining outside? You can go back and actually look at the pieces and see those different decision modes. It takes a little bit more to dig in there and figure out what they're doing, but you can do that, and you can actually help you figure out why. People love it for the why factor. So, strengths and limitations. Big one on all of these. The strengths and limitations, we talk about logistic regressions. The strengths are it is easy to implement and efficient to train. It is relatively easy to regularize the data points. Remember how we put everything between 0 and 1? When you look at logistic regression models, you don't have to worry about that as much. Limitations, it has a high reliance on proper representation of data. It can only predict a categorical outcome. With the k-nearest neighbors, it doesn't need a separate training period. New data can be added seamlessly without affecting the accuracy of the model. Kind of an interesting thing because you can do partial training. That can become huge if you're running across really large data sets or the data is coming in. You can continually do a partial fit on the data with the k-nearest neighbors and continue to adjust that data. It doesn't work on high dimensional and large data sets. We were looking at the breast cancer, 36 different features. What happens when you have 127 features or 1 million features? And you say, well, what do you have 1 million features in? Well, if I was analyzing the legal documents, I might have a tokenizer that splits the words up to be analyzed, and that tokenizer might create 1 million different words available that might be in the document for doing weights. Sensitive to noisy data, outliers, and missing values. That's a huge one with k-nearest neighbors. They really don't know what to do with a missing value. How do you compute the distance if you don't know what the value is? The SVM works more efficiently on high-dimensional data. It is relatively memory efficient. So it's able to create those planes with only a few different variables in there as opposed to having to store a lot of data for different features and things like that. It's not suitable for large data sets. The SVM, you start running this over gigabytes of data, causes some huge issues. Underperforms if the data has noise or overlapping. That's a big one. We were looking at that where the SVM splits it and it creates a soft buffer, but what happens when you have a lot of stuff in the middle that's hard to sort out and doesn't know what to do with? That causes SVM to start crashing or not perform as well. Decision trees. Handles non-linear perimeters and missing values efficiently. The missing values is huge. I've seen this in, the wine tasting data sets where they have 3 different data sets and they share certain features, but then each one has some features that aren't in the other ones and it has to figure out how to handle those. Well, the decision tree does that automatically instead of having to figure a way to fill that data in before processing like you would with the other models. It's easy to understand and has less training period. So it trains pretty quickly. comes up there and just keeps forking the tree down and moving the parts around, and so it doesn't have to go through the data multiple times, guessing and adjusting. It just creates the tree as it goes. Overfitting and high variance are the most annoying part of it. That's an understatement. That has to do with how many leaves and how many decisions you have it do. The more you have, the more overfit it is to the data. It also, just in making the choices and how the choices come in, it might overfit to a specific feature because that's where it started at and that's what it knows. And it really is challenged with large data sets. They've been working on that with the data forest, but it's not suitable for large data sets. It's really something you'd probably run on a single machine and not across a data pool or anything.
Large language models, LLMs. If you ever wondered how machine learning can now understand and generate human-like text, you are in the right place. From chatbots like ChatGPT to AI assistant that power search engines, LLMs are transforming how we interact with technology. One of the most exciting advancements in this space is Google's Gemini or OpenAI ChatGPT, a cutting-edge large language model designed to push the boundaries of what AI can achieve. In this video, we will explore what LLMs are, how they work, and why models like Gemini are critical for the future of AI. Google Gemini is part of a new wave of AI models that are smarter, faster, and more efficient. It is designed to understand context better, offer more accurate responses, and integrate deeply into services like Google Search and Google Assistant, providing more human-like interactions. So we will break down the science behind LLMs, including their massive training datasets, transformer architecture, and how models like Gemini use deep learning innovation to change industries. Plus, we will compare Google Gemini to other popular LLMs such as OpenAI ChatGPT models, showing how each of these technologies is used to power chatbots, virtual assistants, and other AI-driven applications. By the end of this video, you will have a clear understanding of how large language models like Gemini work, their key features, and what they mean for their future AI. Don't forget to like, subscribe, and hit the bell icon to never miss any update from Simplilearn. So what are the large language models? Large language models like ChatGPT 4, Generative Pre-trained Transformer 4, O, and Google Gemini are sophisticated AI systems designed to comprehend and generate human-like text. These models are built using deep learning techniques and are trained on vast datasets collected from the internet. They leverage self-attention mechanism to analyze relationship between words or tokens, allowing them to capture context and produce coherent, relevant responses. LLMs have significant applications, including powering virtual assistant, chatbots, content creation, language translation, and supporting research and decision making. Their ability to generate fluent and contextually appropriate text has advanced natural language processing and improved human-computer interaction. So now let's see what our large language model used for. Large language models are utilized in scenarios with limited or no domain-specific data available for training. These scenarios include both few-shot and zero-shot training approaches, which rely on the model's strong inductive bias and its capability to derive meaningful representation from a small amount of data or even no data at all. So now let's see how our large language model trained. Large language models typically undergo pre-training on a board, all-encompassing dataset that shares statistical similarities with the dataset specific to the target task. The objective of pre-training is to enable the model to acquire high-level features that can later be applied during the fine-tuning phase for specific tasks. So there are some training processes of LLM which involve several steps. The first one is text pre-processing. The textual data is transformed into a numerical representation that the LLM model can effectively process. This conversion may involve techniques like tokenization, encoding, and creating input sequences. The second one is random parameter initialization. The model's parameters are initialized randomly before the training process begins. The third one is input numerical data. The numerical representation of the text data is fed into the model of processing. The model's architecture, typically based on transformers, allows it to capture the contextual relationship between the words or tokens in the next. The fourth one is loss function calculation. A loss function calculation measures the discrepancy between the model's prediction and the actual next word or token in a sentence. The LLM model aims to minimize this loss during training. The fifth one is parameter optimization. The model's parameters are adjusted through optimization technique. This involves calculating gradient and updating the parameters accordingly, gradually improving the model's performance. The last one is iterative training. The training process is repeated over multiple iterations or epochs until the model's output achieve a satisfactory level of accuracy on that given task or dataset. By following this training process, large language models learn to capture linguistic patterns, understand context, and generate coherent responses, enabling them to excel at various language-related tasks. The next topic is, how do large language models work? So large language models leverage deep neural network to generate output based on patterns learned from the training data. Typically, a large language model adopts a transformer architecture which enables the model to identify relationship between words in a sentence irrespective of their position in the sequence. In contrast to RNNs that rely on recurrence to capture token relationship, transformer neural network employs self-attention as their primary mechanism. Self-attention calculates attention scores that determine the importance of each token with respect to the other token in the text sequence, facilitating the modeling of intricate relationships within the data. Next, let's see application of large language models. Large language models have a wide range of application across various domains. So here are some notable applications. The first one is natural language processing, NLP. Large language models are used to improve natural language understanding tasks such as sentiment analysis, named entity recognition, text classification, and language modeling. The second one is chatbot and virtual assistant. Large language models power conversational agents, chatbots, and virtual assistant, providing more interactive and human-like user interaction. The third one is machine translation. Large language models have been used for automatic language translation, enabling text translation between different languages with improved accuracy. The fourth one is sentiment analysis. LLMs can analyze and classify the sentiment or emotion expressed in a piece of text, which is valuable for market research, brand monitoring, and social media analysis. The fifth one is content recommendation. These models can be employed to provide personalized content recommendations, enhancing user experience and engagement on platforms such as news websites or streaming services. So these applications highlight the potential impact of large language models in various domains for improving language understanding automation.
So let's start with the data science interview questions and answers. And the number one problem we would be facing is real world problem solving. And the question one is handling missing data in predictive modeling. So imagine you have given a data set where 30% of the data for a key predictive variable is missing. This variable is crucial for a predictive model. How would you handle this situation to ensure the integrity and performance of your model? And please describe your approach step by step. So starting with the answer, you can start with handling missing data set is a common challenge in data science, and it's important to address it carefully to maintain the accuracy of your model. And here's how you could approach this situation. The number one point could be identify the missing data. So first you need to understand where the missing values are in your data set. You can do this by using a simple code in Python with libraries like pandas. For example, you can use the data.isNull.sum function that will show you the count of missing values in each column. Then you can analyze the pattern, determine if there's a pattern to the missing data. Is it random or is it missing for a reason? This can affect your approach. If the data is missing at random, the methods you use might be different than if the data is missing systematically. So choosing a method for imputation. Let's see the next method, that is choosing a method for imputation. So if the missing data is numeric, you might replace missing values with the mean or median of that column. This is simple and effective, but can be used primarily when the data is missing completely at random. Then comes model-based imputation. Sometimes you can use other variables in the data to predict missing values using a regression model. This can be more accurate but is also more complex. Then we'll use the k-nearest neighbors KN algorithm. But before that, we have a code snippet here that could be used for the implementation of imputation. You could use Python or R. And now moving on, we'll see the k-nearest neighbors algorithm. So this method predicts the missing values based on how closely related the data points are to each other. So after imputation, it's crucial to check how your changes have affected the overall dataset and model performance. Sometimes filling in too many missing values can introduce bias. And then we have visualization. To help understand before and after the imputation, you could visualize the distribution of the variable using histograms or box plots. This helps in seeing how the imputation has changed the statistical properties of the data. And by following these steps, you can handle missing data thoughtfully and maintain the integrity of your predictive model. Now moving to the question number 2, that is based on evaluating model overfitting. So the question is, you have developed a predictive model, but you suspect it might be overfitting the training data. How would you test and address the issue? Please explain your steps and the techniques you would use. So you could start the answer by explaining what is overfitting. So overfitting is a common problem where model performs well on training data but poorly on unseen data, indicating it's too closely fitted to the training data's specific details and noise. So now we'll see a step-by-step guide on how to address this. The number one step is cross-validation. So one effective way to test for overfitting is by using cross-validation technique. Cross-validation involves splitting your training data into multiple smaller sets, that is faults, and then training a model on some of these sets and validating it on the others. So this helps you understand if the model's good performance is consistent across different subsets of data. For example, in Python, you can use the cross_value_score function from sklearn.model_selection. So this is the code, and this is the code snippet of Python that you can use for the cross validation. And here we are importing from sklearn, that is the module, and we are importing cross_val_score. And here we have used the cross_val_score function, and then we have printed the average cross validation score. And the next step we will do is running cross validation model. So this is your predictive model that you have already built using scikit-learn. And here's the X train. These are the X input features of your training data, and Y train, these are the output labels of training data. So we are running cross validation model here. This is your predictive model that you have already built using scikit-learn. So X train here, that means these are the input features of your training data. And Y train here means these are the output labels of training data. And CV equal to 5. This parameter tells the function to split the data into 5 parts, that is faults, and the model is trained on 4 of these parts, and the remaining part is used for testing. So this process rotates until each part has been used for testing once. And the printing results, that is score.mean. So this calculates the average of the scores obtained from each cross validation fault. This average score gives you an idea of how well your model is likely to perform on unseen data. A consistent score across different faults suggests your model is generalizing well rather than overfitting to the training data. So now moving to the next point, that is training versus validation error. So plot the training and validation errors as a function of training epochs or complexity of the model. A model that overfits will show a low error on training data and a high error on validation data as it trains further. Then we have pruning the model. If you confirm that the model is overfitting, consider simplifying it. This might mean reducing the number of parameters by selecting fewer features, using regularization techniques like lasso or ridge, or choosing a less complex model. After this step, we will move to regularization technique step. So these techniques add a penalty to the loss function used to train the model, which can discourage complex models that overfit. Then we have common methods that include L1, that is lasso, and L2, ridge regularization. And here's how you can add L2 regularization in Python. So this is the code snippet here. And what we have done here is we are creating the ridge model, and we have applied alpha equal to 1.0. So this parameter controls the strength of the regularization. A higher alpha value increases the regularization effect, which helps reduce model complexity and combat overfitting. The alpha value can be tuned to find the optimal balance between bias and variance. And now coming for the fitting the model. So model.fit, and in that we have X train and Y train that trains the ridge model on the training data. It adjusts the weight of the feature in X train to predict the Y train while also considering the regularization term. This helps prevent the model from fitting too closely to the noisy aspects of the training data. And then we are re-evaluating the model. After making adjustments, it's important to re-evaluate the model again using the same cross-validation technique to see if the issue of overfitting has improved. And then we have visualization. To help illustrate overfitting, you could create a plot showing the training and validation errors over the number of epochs or model complexity. So by using these techniques, you can identify if a model is overfitting and take steps to correct it, ensuring it performs well not only on the training data but also on new unseen data. So now moving to the next question, that is question number 3, and it is based on real-time data stream processing. And the question is, you are tasked with building a model to predict stock prices in real time. The data comes in every second and you need to update your predictions accordingly. Describe how you would set up your system to handle this type of data effectively, and what tools and techniques would you use and why. So you could start answering this question with handling real-time data. So handling real-time data, especially for something as volatile and fast-paced as stock prices, requires a robust system that can process and analyze data quickly and accurately. So here's how you could approach this. We will set up such a system and we will have some steps. So starting with the steps. So the first step is choosing the right tools. The right tool would be Apache Kafka. So this is a popular tool for handling real-time data that streams because it allows you to publish and subscribe to streams of records, that is data, and it can handle high throughput with low latency. Kafka acts as a buffer and manages the flow of data, ensuring that your system doesn't get overwhelmed. And you can also use Apache Spark. Especially Spark streaming is excellent for processing the data. It can process data in real time and perform complex operations like windowing, grouping data into chunks of a specified time period, and aggregating, that is summarizing data. So you can modify it and perform the predicting of stock prices. And then the step is data processing pipeline. And the first step comes here is ingestion. Data first enters the system, typically through Kafka, which collects data sent from the stock market. And then we do the processing. So Spark streaming takes over here. Here you can apply transformations and run your predictive models on the data. For example, you might calculate moving averages or other indicators that feed into your stock price prediction model. And then comes the output. Finally, the predictions are outputted. This could be to a dashboard for traders, an automated trading system, or even stored for further analysis. And then we develop the model. Now comes the model development. You would likely use a machine learning model that can update quickly and incorporate new data as it arrives. Models such as ARIMA for time series forecasting or more complex machine learning models like recurrent neural networks (RNNs) can be suitable. The model should be retrained or fine-tuned periodically with new data to ensure it stays accurate. Now we'll come to scalability and reliability. So ensure your system can scale as data volume increases. This might mean adding more servers or optimizing your data processing code. Implement monitoring to catch any issues early, like delays in data processing or model performance drops. And now we'll see the step, that is visualization and monitoring. Consider setting up a real-time dashboard that shows key metrics like prediction accuracy and processing time. This helps in quickly spotting when something goes wrong. By setting up your system with these tools and strategies, you can effectively handle the challenge of predicting stock prices in real time. So now we will move to the next question, that is question number 4, and this will be based on scalable data analytics. So we have covered 2 questions that were a bit code-based questions, and now we'll see other questions that would be based on scalable data analytics, or they might be on different areas. And with the 13th question, we will start again with the coding ones. So moving with the question 4, that is based on scalable data analytics. And the question is, given a scenario where your organization suddenly needs to scale its data analysis capabilities due to an influx of data that would be 10 times the normal volume, how would you handle this situation to ensure your data analytics processes remain efficient and accurate? What technologies would you consider and what steps would you take? So you can start answering this question with, handling a sudden increase in data volume requires a strategic approach to scaling your analytics infrastructure without compromising on efficiency or accuracy. So we'll see some steps from that you could effectively manage this scenario. That you would start answering the interviewer that we can start by evaluating the current infrastructure's ability to handle increased loads. This includes assessing your databases, servers, and analytical tools to identify potential bottlenecks or limitations. Then you could move to next step, that would be choosing scalable technologies. To manage the increased data volume, consider leveraging cloud-based solutions such as Amazon Web Services, Google Cloud Platform, or Microsoft Azure. These platforms offer scalable resources which can be adjusted accordingly to the data load, ensuring you only pay for what you use. Integrate big data technologies like Apache Hadoop for distributed storage and Apache Spark for fast data processing. These tools are designed to handle massive volumes of data efficiently and can scale up to meet standard increased demands. Now we'll move to the next step, that would be optimizing data processing. So implement data partitioning and indexing strategies to improve the efficiency of data queries. This will help in managing large data sets by breaking them into smaller, manageable chunks and speeding up search operations. And use real-time data processing frameworks like Apache Kafka or Apache Flink, which can handle high throughput and provide timely insights from large data streams. And the next step would be automation and monitoring. Automate routine data processing tasks to reduce the manual effort and speed up the analysis. This can be done through scripting or using workflow automation tools. Set up comprehensive monitoring systems to track the performance of your data processes. Tools like Prometheus for system monitoring and Grafana for analytics and monitoring dashboards are useful here. They help ensure that the system is running smoothly and alert you to potential issues before they become critical. And the next step will be regular evaluation and scaling. Continuously evaluate the performance of analytics infrastructure. As your data grows, keep adjusting and scaling your resources to maintain optimal performance. Plan for periodic reviews of your technology stack and infrastructure to ensure they remain aligned with your data needs and organizational goals. By following these steps, you can ensure that your data analytics processes are prepared to handle sudden surges in data volume effectively, maintaining the integrity and speed of insights. So this was all for the question 4. Now moving to the question 5, and this is based on integrating machine learning models into production. And the question is, you have developed a machine learning model that performs well in testing environment. Now you need to integrate it into your production environment where it will be used in real-time applications. What steps would you take to ensure the successful deployment and operations of the model in production? So we'll start answering this by successfully deploying a machine learning model into production involves several critical steps to ensure it performs as well in real-time operations as it does in testing. So you would have a clear pathway to make the interviewer understand. We will start with the pathway with the first step, that would be model validation. So before moving anything into production, revalidate your model's performance using a separate validation dataset. This helps confirm that the model generalizes well to new, unseen data. The next step will be preparing the production environment. Ensure that the production environment is ready to handle the model. This includes setting up the necessary hardware and software, ensuring that it can handle the expected load and that all dependencies are correctly installed and configured. Then the next step comes, that is model wrapping. Wrap your model in an API, that is application programming interface, making it accessible to other parts of your software infrastructure. Frameworks like Flask for Python can be used to create a simple web server that listens for data inputs and provides model outputs. Then comes the next step, that is deployment strategies. Consider using containerization tools like Docker, which can help encapsulate your model and its environment, ensuring that it works uniformly across different development and production settings. And then we'll use deployment strategies like blue-green deployment or canary releases to minimize downtime and reduce the risk of introducing a faulty model into production. And then comes the next step, that is monitoring and logging. Implement logging and monitoring to track the model's performance and health in real time. Tools like Prometheus for monitoring and ELK, Elasticsearch, Logstash, Kibana for logging help in quickly identifying and diagnosing issues in production. And then comes the next step, that is performance tuning. Monitor the model's performance over time. If the model's performance degrades or if new data shows different patterns, you may need to retrain or fine-tune the model to maintain accuracy. And after this step, there's a step for feedback loop. Set a feedback loop where predictions and outcomes can be compared. This feedback is crucial for continuously improving the model and catching any drift in data or changes in external conditions that affect the model. And after this comes a last step, that is legal and compliance checks. Ensure all the data used by the model in production complies with privacy laws and regulations. This is crucial for maintaining trust and legality, especially when handling sensitive information. So by carefully planning and executing these steps, you can smoothly transition your machine learning model from a testing environment to a fully functional component of a production system. So this was all about the question number 5. Now moving to the question number 6, that would be based on data-driven decision making. And the question is, your company wants to shift towards more data-driven decision making. You have been tasked with developing a strategy to implement this. What steps would you take to ensure that the data at all levels of the organization is utilized effectively to make informed decisions? And what challenges might you face and how would you address them? So you can start answering this by implementing a data-driven decision-making strategy that will require a comprehensive approach to ensure that reliable data is accessible and effectively used across all levels of the organization. And now we can develop and deploy this strategy, and similarly you could tell this strategy to the interviewer. So the number 1 step will be assessing current data infrastructure. Start by evaluating the existing data infrastructure to understand what data is available, how it is stored, and how it is currently used. This assessment will help identify gaps in data collection, storage, and access that need to be addressed. Now we'll move to the next step, that is developing a data governance framework. Implement a data governance framework that defines who can access data, how it can be used, and who is responsible for maintaining its quality. This framework ensures data integrity and security, which are critical for making reliable decisions. Now we'll move to the next step, that is training and empowerment. So train employees at all levels on the importance of data-driven decision making and provide them with the tools and knowledge necessary to analyze and interpret data. This might include training sessions, workshops, and ongoing support to ensure everyone can use data effectively. Now moving to the next step, that is implementing analytical tools. So deploy user-friendly analytical tools that can integrate seamlessly into the daily workflows of employees. Tools like Tableau, Microsoft Power BI, or even advanced Excel techniques can provide powerful data analysis capabilities without requiring extensive technical knowledge. After this, we'll move to the step that would be creating a centralized data platform. Develop a centralized data platform where all organizational data can be accessed and analyzed. This platform should be scalable and secure, providing a single source of truth for the organization. And then we have the promoting a data-driven culture. So foster a culture that values data-driven decision making. Encourage experimentation and learning from data-driven initiatives. Celebrate successes and learn from failures to continually improve the use of data-driven in decision making. And there would be some challenges and solutions for that. So one major challenge we know here is resistance to change, as some employees may prefer traditional decision-making methods. So address this by demonstrating the tangible benefits of data-driven decisions through pilot projects and success stories. So data silos can also hinder effective data use, promote cross-department collaboration, and integrate disparate data sources to overcome this challenge. After that, you can monitor and do continuous improvement. So by systematically implementing these steps, you can transform your organization into one that leverages data at all levels to make informed and effective decisions. And after answering in these steps, you could make the interviewer have a truth and a faith in you that you could make these models. Now move to the next question, that is question number 7, and that is based on handling large data set. And the question is, your project involves analyzing extremely large data sets potentially exceeding terabytes in size. What strategies would you use to manage and analyze such large data sets effectively? Describe the tools and techniques you might employ. And you could start this with answering that working with large data sets, especially those in terabyte range, presents unique challenges in terms of storage, processing, and analysis. So we'll have a structured approach to handle these challenges effectively. We'll start with the data storage, that would be use distributed file systems. Consider using a distributed file systems like Hadoop Distributed File System, HDFS, or Amazon S3. These systems are designed to store vast amounts of data across many servers, offering high availability and fault tolerance. And then comes the next step, that is data processing. Leverage big data processing frameworks. Tools like Apache Spark are ideal for processing large data sets because they handle distributed computing effectively. Spark can perform data processing tasks much faster than traditional disk-based processing due to its in-memory computing capabilities. And next we could start with efficient data sampling. So there are many sampling techniques that we can use. So when the data set is too large to handle, even with powerful tools, consider using data sampling techniques to reduce the size to a manageable level without losing significant insights. Ensure that the sample represents the whole data set accurately. And then comes optimization of data queries. Indexing and partitioning. Optimize your data queries by implementing indexing and partitioning. This can drastically reduce the time it takes to perform queries by limiting the amounts of data scanned. And then we can do scalable analytics. And then we'll move to the next step, that is scalable analytics. And in that we could start with the parallel computing. Use parallel computing capabilities of frameworks like Spark or Dask to analyze data across multiple nodes. This helps in scaling up your analytics operations to handle large data sets effectively. And now we'll move to the cloud-based analytical tools. So consider using cloud services like Google BigQuery or AWS Redshift, which are designed to handle massive data sets and complex analytics with ease. And after this step, we'll move to data cleaning and pre-processing. Here we will automate pre-processing tasks. We'll use automated tools to clean and pre-process data. This includes handling missing values, normalizing data, and removing duplicates, which can be particularly challenging with large data set. And after this step, we'll move to the step that will visualize large data set. So we'll use specialized tools. That tools could be Tableau or Power BI that can handle large data set by aggregating data and using efficient back-end technologies. For more detailed exploration, tools like Plotly or Bouquet can be used as they offer capabilities to interactively visualize large volumes of data. And after that, there would be step for regular maintenance and updates. That could be continuously monitoring the data quality. As new data comes in, you can continuously monitor its quality. And after this step, you could integrate all these strategies and tools into your workflow, and you can effectively manage and extract valuable insights from extremely large datasets, thereby supporting robust data-driven decision making. And you could answer the whole strategy to the interviewer. Now moving to the question number 8, that is based on optimizing machine learning models. And the question is, during model development, you have noticed that your machine learning model is underperforming. What steps would you take to diagnose the problem and optimize the model's performance? What techniques and tools would you use? So you can answer this by starting with the optimizing. And optimizing a machine learning model that is underperforming involves several steps to diagnose and improve its accuracy and efficiency. And here we will have structured approach to tackle this issue. And you could start this with the number 1 step, that is diagnosing the problem. Evaluate model metrics. Start by thoroughly evaluating the performance metrics of a model. For classification task, look at accuracy, precision, recall, and the F1 score. For regression task, consider R squared, mean squared error, that is MSE, and mean absolute error, that is MA. And then you can move to the next step. That is, use plots like ROC curves for classification models and residual plots for regression to visually assess where the model is going wrong. After that, we'll move to the next step, that is data quality and quantity check. Inspect the data. That is, sometimes the quality and quantity of data can be the root cause of poor model performance. Ensure the data is clean, well pre-processed, and sufficient. Look for issues like missing values, outliers, or imbalanced classes. And after this, we'll move to the feature engineering step, that would be experiment with creating new features or transforming existing ones to provide better predictive power. And then we have the next step, that is model tuning and configuration. After feature engineering, we'll move to the next step, that is model tuning and configuration. So hyperparameter tuning. Use techniques like grid search or random search to find the optimal settings for your model's parameters. Tools like scikit-learn's grid search CV or randomized search CV can automate this process. And there's a cross-validation that would implement cross-validation to ensure that the model's performance is consistent across different subsets of the dataset. And then we have the next step, that is trying different models. So experiment with algorithms here. If initial models are underperforming, try different algorithms that might be better suited for the problem. For instance, if you started with linear regression and it's not performing well, consider more complex models like random forest or gradient boosting machines. And after this, we have ensemble methods that we can use techniques like bagging, boosting, or stacking to combine the predictions of multiple models to improve overall performance. After this step, we have feature selection that includes reduce dimensionality. Use techniques like principal component analysis, that is PCA, to reduce the number of features, which might help in improving model performance by removing noise and redundancy. And then we have select important features. So use model-based technique to identify and keep only the most important features that impact the outcome. And then comes the last step, that is regular updates and retraining. So here you can monitor and update, that could be continuously monitoring the model's performance over time. As new data becomes available, update and retrain the model to adapt to any changes in underlying patterns. And after that, you could have a consultation and collaboration work with the other teams. And by methodically addressing each of these areas, you can diagnose why your machine learning model is underperforming and can take steps to optimize its accuracy and efficiency. So this was all about question number 8. So let's start with the question number 9. And this is based on handling unstructured data. So the question is, you are given a large amount of unstructured data, including text, images, and videos. What strategies would you use to manage and analyze this type of data effectively? Describe the tools and techniques you might employ. So you can start answering this question by describing that dealing with unstructured data can be challenging due to its lack of predefined format or structure. However, with the right strategies and tools, you can effectively manage and analyze it to extract valuable insights, and there will be an approach how you can do that. So we will discuss the approach here, and starting with the steps. So the number 1 step will be data categorization and organization. So the number 1 step in this step will be sorting and tagging. We will begin by categorizing the data into types. that will be text, images, or videos. Use tagging to add metadata, which helps in organizing the data and makes it easier to access and analyze later. After that, particularly for text data, we'll use natural language processing, NLP. We will employ NLP techniques to extract useful information from text. Tools like NLTK, Spacey, or even more advanced models like BERT can help you perform tasks such as sentiment analysis, entity recognition, and topic modeling. After that, we will do text indexing. We can use Elasticsearch or Apache Solr to index large volumes of text. These tools provide powerful search capabilities and can handle complex queries efficiently. And after that, we'll move to image data. And to structure image data, we'll use image processing. We'll use libraries like OpenCV for basic image processing tasks such as filtering and transformations. For more advanced image analysis, consider deep learning models using frameworks like TensorFlow or PyTorch. And then we'll feature extraction. Apply techniques to extract features from images, such as edges, textures, or key points, which can be used for further analysis or machine learning. And then we'll come to video data. And here we'll do video processing, and we'll use the tools like FMPEG that can be used for basic video processing tasks such as format conversion or extracting frames. For analyzing video content, look at machine learning models that can classify or recognize activities in the video. And after this, we'll move to temporal analysis. For videos, temporal components are important. Techniques like sequence modeling or recurrent neural networks, RNNs, can be useful to analyze sequences of frames for activities or events. And then we'll move to data storage and management. Here we'll use the given volume and complexity of unstructured data and use big data platforms like Hadoop or cloud services like AWS S3 for storage. These platforms can scale up to handle large data sizes and provide the necessary infrastructure to store and retrieve unstructured data efficiently. And then we have visualization and reporting. Custom dashboards that we'll create here. We will develop custom dashboards using tools like Tableau or Power BI, which can integrate different data types and provide a unified view of the analyzed data. And after that, we will do data summarization. Tools that provide summarization capabilities can help in considering large volumes of unstructured data into more manageable and interpretable forms. And after that, we'll leverage these strategies and tools and can effectively manage, analyze, and derive insights from unstructured data, which can be crucial for making informed decisions in various applications. And this is the path that you can explore and explain to the interviewer if this question has been asked. Now moving to the question number 10, and that will be based on scaling AI solutions in enterprise. And the question is, your company wants to scale its AI operations from a few initial pilot projects to enterprise-wide implementation. What are the key considerations and steps you would take to ensure the successful scaling of AI solutions across the organization? And what challenges might you face and how would you address them? So you can start answering this question with the scaling AI solutions. You could answer him that scaling AI solutions across an enterprise requires careful planning and strategic implementation to ensure success and alignment with business objectives. And there should be a strategic approach to implement this. So starting with the approach, and the number one step will be strategic alignment. So identify business objectives. Start by identifying the business objectives that the AI solutions are intended to support. This ensures that the AI initiatives are aligned with the company's strategic goals and can demonstrate clear business value. And then comes the stakeholder engagement. So engage stakeholders from various departments early in the process to gather input and build support. This helps in understanding diverse needs and ensures broader acceptance of the AI solutions. And after that comes the infrastructure and technology. So there's an option that is assess and upgrade infrastructure. Evaluate whether your current IT infrastructure can support the expanded use of AI. You might need to upgrade hardware, invest in cloud solutions, or adopt technologies that facilitate AI processing and data handling. And after that, we have standardization of tools. Standardize the tools and platforms used for AI development to ensure compatibility and ease of maintenance across the organizations. And after that, we'll move to data management. So robust data governance, that is to implement a strong data governance framework to manage enterprise data effectively. This includes policies for data quality, security, and compliance, especially important when scaling AI solutions that rely on vast amounts of data. And after that, we will come to data accessibility. So ensure that data is accessible across the organization, but also secure against unauthorized access. This involves setting up secure data lakes or warehouses that centralize data while allowing controlled access. And then we come to the next step, that is talent and training. So build AI competency, that is develop in-house AI expertise through training programs and hiring. So this build the necessary skills within the organization to develop, manage and scale AI solutions. And after that, you can also perform cross-functional AI teams. That could be forming cross-functional teams that include data scientists, IT professionals, and domain experts. So this fosters collaboration and ensures that AI solutions are developed with a comprehensive understanding. And after forming these collaborative teams, we'll move to scalable deployment models. So pilot test and phased rollout. Before a full-scale rollout, conduct pilot tests to gauge the AI solution effectiveness and integration capabilities. Based on feedback, adjust and then gradually deploy the solutions across the organization. And then we have modular and flexible design. So design AI systems to be modular and scalable, allowing for adjustments and expansions as needs. And then we'll monitor and do the continuous improvement. So there will be performance metrics that would establish metrics to regularly assess the performance of AI systems. We will monitor these systems to ensure they met expected outcomes and adapt as necessary. And after that, we have next step, that is addressing challenges. So there could be cultural resistance, that there could be employees that would be resisting to the changes, but we have to address this through continuous education and by showcasing successful AI use cases within the organizations. And by carefully considering these aspects and methodically implementing steps, you can successfully scale AI solutions across your enterprise, driving significant business value and innovation. And that's all for question number 10. Now we'll move to question number 11, and that is based on ethical considerations in data science. So the question is, in your data science projects, how do you ensure that ethical considerations are addressed? Describe the steps you take to identify and mitigate ethical risk in your projects. What frameworks or guidelines do you follow? So you could start answering this question with ethical considerations, that they're crucial in data science to ensure that the solutions and analyses do not advertently cause harm or bias. Here's how you can ensure that. So there are some steps and we will discuss those steps, starting with the number 1, that is educate on ethical standards. So stay informed about the ethical standards in data science, such as fairness, accountability, transparency, and privacy. Organizations like the Data Science Association and the ACM have codes of ethics that we refer to as guidelines. And then we have ethical risk assessment. Identify potential ethical issues. That would be at the beginning of each project, conduct a thorough assessment to identify any potential ethical risk, such as biases in data or impact on vulnerable groups. This involves reviewing the source of data, the methodologies used for data collection, and the intended use of the data analytics results. And then we have stakeholder analysis. Engage with stakeholders to understand the diverse perspectives and potential impact of the project. This helps in identifying ethical issues that may not be apparent from a purely technical standpoint. And then we'll move to mitigation strategies. Implementing bias mitigation techniques, we will use statistical and machine learning techniques to detect and mitigate biases in data. This might involve techniques like resampling, reweighing, or using algorithms designed to be fair. And then we have privacy preserving methods. Employ methods such as data anonymization, encryption, or differential privacy to protect individual privacy when analyzing sensitive data. Then we have other methods, that is transparency and explainability. There we have model explainability, and after that coming to documentation and reporting. So we have to maintain thorough documentation of data sources, model decisions, and methodologies. And then we have continuous monitoring and feedback. There you have to monitor outcomes and the feedback mechanisms should be applied. And then we have the panels, that is collaboration and advisory panels. There we have ethical review boards. So for complex projects, setting up or consulting with an ethical review board can provide oversight and diverse perspectives on the ethical implications of project methodologies. So by proactively addressing ethical considerations through these steps, you can ensure that your data science projects uphold high ethical standards and positively contribute to society while minimizing harm. So this was all about question 11. Now moving to question number 12, that is based on time series forecasting for business decisions. So the question number 12 is, you are tasked with forecasting monthly sales for a retail company using time series data from the past 5 years. What steps would you take to prepare and analyze this data to make accurate forecast? What specific tools or techniques would you use and why? So we can start answering this by time series forecasting. and we could address them that it's a powerful tool for predicting future events based on past data, especially in business context like retail sales. So we will have a structured approach here, and we'll start with data collection and cleaning. First, we will gather data and ensure that you have collected all relevant data, including monthly sale figures from the past 5 years, and also considering including external factors that might affect sales, such as economic indicators, holidays, and promotional activities. And then we'll proceed to clean data. We'll check for and handle any inconsistencies or missing values. And then we have data visualization. Here we'll plot the data. We'll use plotting libraries like matplotlib or seaborn in Python to visualize the data. This will help in identifying patterns, trends, and seasonality. And then we have decomposition of data. So there's a seasonal decomposition, and we'll use statistical techniques to decompose the data into trend, seasonally, and residuals. So this can be accomplished with tools like the seasonal decompose function from the stats models library in Python. And we'll understand these components separately and can improve the accuracy of our forecast. And then the next step is model selection and forecasting. So there are two models, that is ARIMA and SARIMA models. So we have to choose appropriate forecasting models based on data's characteristics. For instance, ARIMA, that is autoregressive integrated moving average. It is effective for non-season data, while SARIMA, that is seasonal ARIMA, that is suitable for data with seasonal patterns. And after choosing the model, we'll move to cross-validation. We will implement time series specific cross-validation techniques like time-based splitting to evaluate model performance. And this will ensure your model generalizes well on unseen data. And then we have model fitting and diagnostics. We will fit the model, that is by using the Cynimax class from stat models that will fit your model to the data. And then we will carefully select parameters based on AIC, that is Archaic Information Criterion, that scores or thorough grid research technique. And then we can do the diagnostics and forecast and validation. And after forecast validation, we'll move to iterative improvement. So there's a feedback loop that should be mandatory, and there should be a regular update for the model with new sales data and refining the model as needed. So this continuous improvement cycle helps adapt to changing patterns in sales data. And by following these steps and using these tools, you can create robust forecasts that help the retail company plan better and make informed decisions. So this was all about question number 12. Now moving to question number 13, that is based on customer segmentation using machine learning. So the question is, you are given a data set containing demographic and purchasing behavior data for a group of customers. Your task is to segment these customers into distinct groups based on similarities in their purchasing behavior and demographics. So what steps would you take to perform this segmentation, and can you provide a sample Python code snippet to illustrate the initial stages of data handling and model application? So we can start this by explaining customer segmentation, that it's a powerful approach to tailor marketing strategies and improve customer service by identifying distinct groups based on their behavior and characteristics. And here also we have a detailed approach for this task. So we'll start with number one step, that would be data exploration and pre-processing. So there will be initial exploration, that is beginning by examining the data set to understand the features available such as age, income, purchase frequency, etc. Then we'll look for missing values or anomalies and decide how to handle them. That could be using imputation. And then we'll move to feature engineering. We will create new features that might be useful for segmentation, such as customer lifetime value or average transaction amount. We'll also use normalization, that is normalize the data to ensure that one feature doesn't disproportionately influence the model due to its scale. We'll use standard scaling or min-max scaling as appropriate. So then we'll come to the next step, that is choosing the segmentation technique. And here we have k-means clustering. So this is a popular method for customer segmentation. Here we will decide on the number of clusters by using techniques like the elbow method or silhouette analysis to determine the optimal cluster count. And then we have model implementation. And in that we will use data preparation, and we'll prepare the data by selecting the relevant features and applying any final transformations. And then we have model fitting. We'll fit the k-means clustering model to the data and evaluate and interpret analyzing clusters. And after analyzing clusters, we'll move to the next step, that is strategic insights. We'll provide actionable insights based on cluster characteristics such as targeted marketing strategies for each segment. And then we have iterative refinement, that is feedback incorporation, and we'll use business feedback to refine the segmentation. If additional data becomes available, incorporate it to enhance the model. And now we'll see the sample Python code. So for this, first we'll import the libraries and modules. As you can see on the screen, we have imported pandas, random forest classifier, train test split, standard scaler, classification report. And after that, we'll load the data. And for that, we have used the pandas to read the data, that is read underscore SSV. And after that, we are processing the data, that is data pre-processing. We are handling missing values and using the forward fill or FIL to fill missing values in the data set. And then we are featuring scaling, that is normalizing the selected features, that is feature 1, feature 2 and feature 3 using standard scaler. And then we'll move to the next step, that is data splitting. We'll split the data set into training and testing sets. So that test size equal to 0.2 parameters specifies that 20% of the data will be used for testing. And then we'll train the model. We'll initialize and train a random forest classifier with 100 trees and a random state for reproducibility. And then we'll evaluate the model. We'll make predictions on the test set, that is x underscore test, using the trained model, and print a classification report showing precision, recall, F1 score and support for each class. So this code demonstrates the process of loading, pre-processing, training and evaluating a machine learning model, that is random forest classifier, for predicting equipment failures in a manufacturing plant. The use of techniques such as data pre-processing and splitting along with the random forest classifier highlights a standard flow for building predictive maintenance models. So this was all about the question number 13. So now moving to the question number 14, that is based on predictive customer churn. And the question is, you are tasked with developing a model to predict which customers are likely to churn from a subscription service. So what steps will you take to build this model, and can you provide a sample Python code to illustrate the data preparation and model training process? So we'll start answering this question about depicting what is predicting customer churn. So predicting customer churn is crucial for businesses to implement retention strategies proactively. And we'll have a detailed approach for building a predictive model for this purpose, starting with data collection and exploration. And in this, we will collect data. And after that, we will perform the exploratory data analysis, that is EDA. We'll perform an initial analysis to understand patterns and trends. And then we have feature engineering. We will create new features and derive new features that might influence churn, such as change in usage pattern or service upgrades. And then we'll handle the missing values if we found any. And then we'll encode categorical variables. We'll use techniques like one-hot encoding or label encoding for categorical variables. And then we have scale features to normalize or standardize numerical features to ensure they contribute equally to the model's performance. And then we'll select the model, that is, we'll choose the appropriate model and start with for the knowing handling binary classification task. That could be with logistic regression, random forest or gradient boosting machines. And after selecting the model, we'll train the model and evaluate it. So fit your model on the training data, and after that evaluate the model using appropriate metrics like accuracy, precision, recall, F1 score and ROC to gauge its performance. And then we'll optimize the model using hyperparameter tuning. We'll optimize the model parameter using grid search or random search to improve performance. And then we have feature importance, that is analyze and rank features by their importance in predicting churn to refine the model further. And then the last step is deployment and monitoring. We'll deploy the model. Once validated, deploy the model into a production environment where it can predict real-time churn. So after deploying the model, regularly monitor the model to ensure it remains effective over time as new data comes in. So now we'll see the sample Python code for this example. So starting with the importing of libraries, we will import pandas, numpy, scikit-learn, sklearn, TensorFlow, and the TensorFlow keras and callbacks. And after importing the modules, we'll start with data loading. We'll load the dataset from a CSV file named equipment_data.csv, and that too with the pandas data frame. And after that, we'll do the data pre-processing. We'll handle missing values, and for that we'll use forward fill to fill missing values in the dataset. And then we have feature scaling that will normalize the selected features, that is feature 1, feature 2, feature 3 using standard scaler. And after that, we'll use the data splitting. We'll split the dataset into training and testing sets, and the test size will be equal to 0.2. And this parameter specifies that 20% of the data will be used for testing. And after that, we'll start with building the model. First, we'll see sequential model that initializes a sequential model technique. And then we have dense layers that adds two dense layers with 64 units and ReLU activation function. Then we have dropout layers that adds two dropout layers with a dropout rate of 0.5 to reduce overfitting. After that, we'll do the model compilation. We'll compile the model using the Adam optimizer and binary cross entropy loss function for binary classification. And there will be an early stopping that will define an early stopping callback to stop training when the validation loss metric has stopped improving after 3 epochs. And after training the model, we will evaluate the model and evaluating the model on the test data and print the loss and accuracy metrics. So this code demonstrates the process of loading, pre-processing, building, compiling, training, and evaluating a deep learning model using TensorFlow and Keras for predicting equipment failures in a manufacturing plant. So the use of techniques such as data pre-processing, dropout, regularization, and early stopping helps in building a robust deep learning model for predictive maintenance. So that's all with question number 14. Now we'll start with question number 15, that is based on deep learning in NLP. And your question is, you are tasked with developing a sentiment analysis model using deep learning to understand customer opinions from reviews. So what steps would you take to build this model, and can you provide a sample Python code snippet to illustrate how you would pre-process data and train a simple deep learning model? So we'll start answering this with sentiment analysis. That sentiment analysis using deep learning allows businesses to gauge customer sentiment from text data like reviews or comments effectively. And we'll have a detailed approach for building a sentiment analysis model. We'll start with data collection and cleaning. We will collect the data, gather a substantial data set of text reviews and their associated sentiments, typically labeled as positive, negative, or neutral. And then we'll clean the data, pre-process the data by removing noise such as HTML tags, special characters, and stop words. And we'll normalize the text by converting it to lowercase. And then we have text pre-processing. We'll convert text into tokens, words, or phrases. And then we have vectorization that transforms tokens into numerical format using techniques like word embeddings or TF-IDF, that is term frequency inverse document frequency. And then we'll use the padding. And then we have the option of model selection. We'll choose a model architecture based on a basic approach and use a RNN or more advanced architecture like LSTM, that is long short term memory, or GRU, that is gated recurrent units, which are effective for sequence data like text. And then we have model training. We'll compile the model, define the model architecture, and compile it with the loss function suited for classification like categorical, cross entropy, and an optimizer like Adam. And then we'll train the model, we'll fit the model on our pre-processed data. We'll evaluate and optimize it. Evaluating model performance, here use the metrics such as accuracy, precision, recall, and F1 score to assess the model. And then we have hyperparameter tuning. We'll optimize the model by adjusting parameters like learning rate, number of layers, and units per layer. And then coming to deployment. We'll deploy the model and integrate the model into the existing review processing pipeline so it can automatically classify new reviews. So let's see the sample Python code, and we'll have a basic approach for that. Here we'll import NumPy, TensorFlow, sequential, embedding LSTM, dense dropout. So embedding converts positive integers, that is indexes, into dense vectors of fixed size. And LSTM, that is long short term memory layer, that is used for learning dependencies in sequence data. And then we have dense, that is a regularly dense connected NN layer. And then we will import pad underscore sequences. And after that we have the data set and the sample text data representing customer reviews that will store in variable text. And then we have labels that has binary labels indicating sentiment, 1 for positive, 0 for negative. And now we'll start with the pre-processing of data. Here we have declared that tokenizer. We will initialize a tokenizer that will help only the top 1000 most frequent words. And then we have fit underscore on underscore text, that is update the internal vocabulary based on the list of text. It essentially creates a dictionary of word to index pairs. And then we have text to sequences that will transform each text in text to a sequence of integers. And then we have pad sequences that will ensure all sequences have the same length by padding shorter sequences with zeros up to the maximum length. And then we'll start building the model. Here we have sequential model that will set up a linear stack of layers. And then we have embedding layer that will map each word index to an embedding vector of size 64. So the input length is set to 10, that is the length of the input sequences. Then we'll start with LSTM layers. So two LSTM layers are added. The first one returns sequences to allow the next LSTM layer to process these sequences. And after that, we have the dropout layer that applies dropout with a rate of 0.5 of the first LSTM layer to reduce overfitting. And after that, we'll come to dense layer that has output of a single scalar that represents the predicted sentiment and using sigmoid activation to output a probability. And now we'll start with model compilation and training. So we'll configure the model for training and we'll use binary cross entropy as the loss function that is suitable for binary classification, and the Adam optimizer and tracks constantly accuracy as a metric. And then we have the fit that trains the model for a specified number of epochs, that is iterations or the entire data set. And then we'll predict the model, that is after training the model can predict the sentiment of the reviews in the data set. This is useful for checking how the model performs on the training data itself. So this breakdown explains each step of the coding process, detailing how the data is prepared and how the model is configured. And then we'll compile it and use for training and prediction. So its detailed explanation should help in understanding how to implement a simple LSTM model for sentiment analysis in TensorFlow. Now moving to the question number 16. So let's start with question number 16, that is based on anomaly detection in transaction data. So the question is, you are tasked with identifying unusual transactions in a company's financial data that might suggest fraudulent activity. So what steps would you take to develop an anomaly detection model, and can you provide a sample Python code snippet to illustrate how you would pre-process the data and apply an anomaly detection technique? So we'll start answering this with anomaly detection technique. That is, anomaly detection is essential for preventing fraud by identifying transactions that deviate significantly from typical patterns. And now we'll see the structured approach to building an anomaly detection model for transaction data. We'll start with data collection and cleaning, and we'll collect all the compiling transaction data, which should include details like transaction amount, time, user ID, and transaction type. Then we'll move to feature engineering and develop features that capture the essence of transactions, such as time of day and the day of the week. And then we have data normalization. We'll use scaling techniques such as min-max scaling or standardization to ensure that the model is perfectly normalized. And then we have choosing the anomaly detection technique. So here we have to choose the technique which is effective for high dimensional data sets and works for isolating anomalies instead of profiling normal data points. After choosing the anomaly technique, we'll train anomaly identification. We'll fit the chosen model to the data, and the anomalies that would have been chosen will be those transactions that the model identifies. And after this, we come to the last step, that is review and action. Here we have manual review, that is transactions flagged as potential anomalies should be reviewed manually to confirm fraudulent activity. And then we have continuous improvement. That is, we can regularly update the model with the new data and feedback from the review process to improve accuracy. And now moving to the prediction, that is after training the model, we can predict the sentiment of the reviews in the dataset. And this is useful for checking how the model performs on the training data itself. Now we'll see the Python code to see how you can set up this model for anomaly detection. We'll start by importing the libraries and module, and after that we'll load and prepare data. That is, we'll load transaction data from a CSV file into the pandas data frame. And after that, we'll convert the transaction time column to date time format, which allows the extraction of additional time-based features. And after that, we'll perform feature engineering that will extract the hour of the day from the transaction time column. This feature can be important as transactions occurring at unusual hours may be indicative of fraud. And then we'll move to the normalization of data. This will apply standard scaling to the amount and hour of the day feature. This normalization process involves subtracting the mean and dividing by the standard deviation for each feature, ensuring that the feature contribute equally to the analysis and improving the performance of many machine learning algorithms. And after that, we'll start with anomaly detection with isolation forest. That's a technique. We will initialize an isolation forest model with 100 trees, that is n estimators equal to 100, setting the proportions of outliers, that is contamination, to 1% of the data. So this parameter is crucial as it influences the threshold of marking an observation as an anomaly. Then we'll fit the model to the scaled amount and hour of the day data and predict the anomaly status for each transaction. And then we'll start with filter and display anomalies. We'll filter out transactions identified as anomalies, that is anomaly equal to -1. We'll display these transactions which can be reviewed manually to determine if they represent actual fraudulent activity. So this code snippet provides a systematic approach to detecting anomalies in transaction data, leveraging the isolation forest algorithm's ability to handle complex and high-dimensional dataset effectively. So the pre-processing steps ensure that the data is appropriately formatted and normalized for optional model performance. So this was all about question number 16. Now moving to question number 17, and that is based on integrating machine learning models into web applications. And your question is, you have developed a machine learning model to predict real estate prices based on various features like location, size, and amenities. How would you integrate this model into a web application to allow users to get real-time price predictions? Can you provide a sample Python code snippet to illustrate how you would prepare the model for integration and handle user requests? So starting with the approach, that is integrating a machine learning model into a web application, this will involve several steps to ensure the model is accessible and perform well in a live environment. So here's how you can approach this task. We could divide into steps, and we'll start with number 1 step, that is model preparation. We'll finalize and save the model. So once your model is trained and validated, save it using a format that can be easily loaded into a web application. So Python's pickle module or TensorFlow's save model format are commonly used for this purpose. Then we can use web application backend setup. For this, select a suitable web framework. So Flask is popularly known for its simplicity and effectiveness in integrating Python-based machine learning models. And after that, we'll develop the API. After developing the API within your Flask app, that you can receive user inputs for model features, load the model, make prediction, and return the result. And after this, we'll develop the UI. We'll design a user-friendly interface. We'll create a simple and intuitive UI that lets users input the feature like location, size, and submit them for prediction. And after that, we'll move to the deployment phase. We'll use a cloud platform like Heroku, AWS, or Google Cloud to deploy your Flask application. And then we have the maintenance and updates. We'll monitor and update regularly for the performance and use the model as needed based on user feedback. So now moving to the Python code and see how this model can be created. So here we'll start importing the libraries and module, and we are using Flask, Pickle, and JSONify. And we will start with app initialization. We'll initialize a new Flask web application. That would be a special variable which gives Python files a unique name to differentiate between them when they are imported into other scripts. And after that, we'll load the model. So loading a pre-trained machine learning model from the file system. So this model is assumed to be saved in the same directory as this script. So the model is loaded in RB mode, which stands for read binary. And after that, we'll move to API route and prediction function. So we will define an API endpoint at predict that listens for post request. This is the URL that the front end of the web application will call to send data to the backend. And after that, we'll start with predicting the function. And here we have extract features that retrieves data sent into the JSON format from the post request. That is request.get_JSON, and the force we have set it as true here, and forcefully formats the request data into JSON, ensuring compatibility. And then we'll extract the relevant features, that is location, size, and amenities from the JSON object and store them in a list as expected by the model. And after preparing the features, we'll make the prediction. We'll use the loaded model to make a prediction based on the provided feature. And then we have the return prediction method. Here we will convert the prediction result into JSON format using JSONify and send it back to the client, and this will ensure that the response can be easily handled by the client application. So this was all about the question number 17. Now moving to the question number 18, that is based on analyzing. And now we'll move to the question number 18, that is based on analyzing geospatial data. And your question is, you are tasked with analyzing geospatial data to help a city improve its public transportation system. The data includes GPS coordinates of bus stops, ridership numbers, and traffic patterns. What steps would you take to analyze this data, and can you provide a sample Python code snippet to illustrate how you might visualize bus stop location and ridership? So you can start answering this question that geospatial data analysis can provide critical insights into how effectively a public transportation system serves its city and guide improvements. And there's a detailed approach for this, and we can start with data preparation And in this, we will do data collection and data cleaning. And after this step, we will move to the next step, that is exploratory data analysis. And in this, we will have statistical summary, we will generate descriptive statistics, and then we have correlation analysis. And after moving that, we have geospatial visualization, that is mapping bus stop. We'll plot the locations of bus stop on a map to visually assess their distribution across the city. And after that, we have heat maps that will create ridership data to identify hotspots and areas with potential service gaps. And after geospatial visualization, we'll move with spatial analysis. We have proximity analysis that will analyze the proximity of bus stop to key areas like commercial centers or residential areas. And now moving to the fifth step, that is optimization and recommendation. So we'll have a route optimization that will suggest modifications to route based on traffic patterns and ridership demand. And the policy recommendations that will provide actionable recommendations for improving bus frequencies. Now moving to the sample Python code where we can define this model and use it accordingly. And here we will start importing the libraries and modules. And here we will start with importing GeoPandas and matplotlib.pyplot. And after importing, we'll start with data loading. So we will declare a variable bus underscore stops and load the bus stops data from a shapefile. So shapefiles are popular geospatial vector data formats for geographic information system software. And then we have the ridership that will load ridership data from a CSV file which includes columns for longitude, latitude, and ridership levels. And after that, we'll create geodata frame that will convert the ridership data frame into a geodata frame. And this step involves creating a geometry column from the longitude and latitude columns. And then we have the plotting one. Here we will plot the graphs that would be figures and axes and create a figure for the single subplot with a specified size that is 10 cross 10 inches. And then we have city underscore map.plot. It is assumed that there is a base map of the city loaded as a geodata frame named city map. This is plotted first with the light gray color to serve as a background for the other layers. So this was all about question number 18. Now moving to question number 19, that is based on predictive maintenance using machine learning. And your question is, you are tasked with developing a predictive maintenance system for a manufacturing plant that relies heavily on automated machinery. So the data available includes machine operational parameters, maintenance history, and failure incidents. What steps would you take to develop a predictive model, and can you provide a sample Python code? So you can start with predictive maintenance that is essential in manufacturing as it helps prevent equipment failures, reducing downtime and maintenance cost. And here you would have a detailed approach or predictive model for this, starting with data collection and integration. Then you can do EDA, that is exploratory data analysis, and then we can perform feature engineering and then move to data pre-processing task, and then the selection model and training. And after that, we have model evaluation and deployment technique that we can do for the model using appropriate metrics such as precision, recall, and F1 score. So this was all about question number 19. So now move to question number 20, that is based on personalization using machine learning. And your question is, you are tasked with developing a machine learning model to personalize content recommendations for users on a media streaming platform. The data available includes user demographic details, viewing history, and ratings. So what steps would you take to build a model for personalized recommendations? And can you provide a sample Python code for that? So you can start answering this with creating a personalized recommendation systems. This would be essential for engaging users by providing content that is relevant to their interest. And there will be a systematic approach or personalized content recommendation. We'll start with data collection and integration. And after that, we'll perform EDA, that is exploratory data analysis. And then we have feature engineering. In this, we'll interact features, and the temporal features will include time-based features to capture trends and seasonality in viewing behavior. And then we'll select the model, that is by collaborative filtering and hybrid models. And then we'll train the model and validation and implement and monitor them.
Thanks for completing Data Science full course by Simplilearn. You've gained a solid foundation in one of the most critical fields today. With your new data science skills, you're ready to tackle real-world problems, make data-driven decisions, and explore new career opportunities. Keep learning, stay curious, and get ready to make a difference in the world of data.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.